speakers could explore the necessary time to prepare their talk and record the same. Still, a few could not make it. Professor Adi Ben Israel is the one who eagerly intended to join us till a few days back and wanted to deliver a talk on the developments of generalized inverses. But the limitation of his energy stopped him from completing his preparation. Still, we do not want to miss him in this occasion and like to listen to him talking on the topic. We will have his recorded talk following this informal inauguration. Speakers list consisting of many from across the globe, and it consists of Steve Kirkland delivering Hans Schneider lecture, Abraham Berman from Israel, Andre Leroy from France, TSSRK Rao, Jain, Adi Ben Israel, and Apurva Kare are joining from USA. Sean Follett, George P.H. Stan are joining from Canada. Other invited speakers from India are Professor Saras Sane, S. Armugam, N. Ekamaram, S. Sivakumar, R. Balaji, Shivaramakrishnan Siva Subramaniam, Murali Srinivasan, B. Rajaram Nandini Nilakantan, and Tirthankar Bhattacharya, and many more. Professor Arvind Lal, simply Lal for most of his senior friends and other colleagues, and Lalda for younger friends and colleagues. He is no more with us. He was very active member in our organizing committees since the beginning from 2012. In his memory and to honor him, we will have a session dedicated to him on 17th afternoon, for which Sukantapati, Professor IIT Guwahati, is the organizer. With this, I end my briefing and request Professor Bapat to come forward and give his briefing, and Raksha and the team to take over for the Ben Israel's lecture.
Okay.
Thank you.
Okay, thank you, Prasad, and for this introduction. So I'm very happy to welcome all of you to this first day of ICLAA. I gave an inaugural talk on the first day. I think there was some technical problem, so perhaps the talk did not go through properly. But I'm again pleased now today the technical situation is much better, and I'm very happy to welcome all of you. So as Prasad has explained, the background is that this activity started back in 2012. Actually, the real background is the development of linear algebra and matrix theory in the Indian context, because some individuals in India as well as some institutions have been very active from the beginning in the area of matrix theory, linear algebra and related fields, and not to mention the giants in the field who started the area essentially like Professor C.R. Rao and followed by Professor S.K. Mitra, Professor C.G. Khatri. So these are the names who established matrix theory as one of the main disciplines, or whatever you call it, linear algebra or matrix theory, as one of the main disciplines underlying statistics, applied statistics, and many other areas. And this was recognized the world over that time, that the development of linear algebra. And perhaps our activity took off from there, that later on some other areas came into the picture like graph theory and so many other areas where, because of the advancement of neural networks and artificial intelligence or whatever, the linear algebra became a very important tool in all these areas, and one doesn't have to now emphasize the role of linear algebra. So I think our activities picked up from there, and we started getting more and more people interested in these areas because the linear algebra area has both the advantages of a very beautiful theory as well as immense applications. So that is how it grew. And as Prasad mentioned, the family really started growing. If you see the MathSciNet genealogy project, you will see the generation after generation they're coming forward. And even today, there are at least, I would say, close to 100 active people in India in this area at various levels, from the senior level all the way up to PhD students. So it is very nice to see the area growing, and our responses to our conferences has been exactly a reflection of that activity. So the conference is very successful, the series is very successful, of course, no less than the very efficient organization by Prasad and his team at Manipal, and people are looking forward to this activity. I think let's not get discouraged by this temporary setback of pandemic and so on. The activity has already taken root, and it is not going to die down, and it will continue, and we will get more and more participants. And I'm really pleased to see that many more very pure and very deep mathematicians are getting associated with the conference, with the activity. And as the word spreads, I think many more people will get to know about it. So I think I will not give too much of introduction, as I have already done so on the first day. So I again welcome all of you, and let's hope to have a very wonderful conference this time. Thank you.
Professor Prasad, please unmute yourself.
I'm only requesting you to proceed, Raksha.
Yes, sir. Thank you, sir. Thank you, Professor Bapat, for speaking few words. So to begin the session for ICLA 2021, we have we will play a recording of Professor Adi Ben Israel, who is a Professor Emeritus Management Science and Information Science from Rutgers Business, New Jersey. He has been a visiting professor at many institutes, universities across the globe, including India. He was awarded by Fulbright Professorship in India, held a distinguished chair in mathematics, University of Delaware, and has served as professor and chairman of Applied Mathematics Tech, New York. Uh, Unfortunately, he couldn't join us for this ICLA 2021, but we have his recordings. So I request the team to play the recording.
My lecture, matrix volume and application. The
Participants, we are playing the recording soon.
we have a non my lecture, matrix volume and application. The volume of a m by n matrix of rank R is defined as the square root of the sum of squares of the determinant of its maximal non-singular submatrices, and 0 if the matrix is 0. Equivalently, the volume of the matrix A is the product of its positive singular values. Definition 1 applies also to non-numerical matrices such as Jacobian. Y volume, every unit cube in the range of A transpose is mapped by A into a parallelopiped in the range of A of volume vol A. Similarly, every ball of volume 1 in range of A transpose is mapped into an ellipsoid of volume vol A. So every volume that can be approximated by cubes or rectangles or whatever, boxes, therefore is mapped by A into a volume which is the original volume times the volume of A. Special cases, if we have a non-singular matrix W, the volume of the parallel pipe spanned by its columns is the determinant of W. It is a signed volume because the determinant can be positive or negative. The volume of W is the absolute value of the determinant. If the matrix is of full column rank, then the same parallel pipe, the volume is given by the gram determinant, and the volume of W is equal to the square root of the determinant W transpose W. Now, if a matrix is square, the determinant can be 0, but the volume can be still positive. For example, if you take the 2 by 2 matrix of ones, the determinant, of course, is 0, but the volume is 2, the square root of 4. And in fact, the unit cube in the case of this matrix is just the range of A transpose is just a line, and the unit cube is the unit vector on that line, and it is mapped into a vector twice the length. The minimal norm least square solution, which is the Moore-Penrose inverse of A times the vector, the right-hand side B, is a convex combination of the basic solutions. The basic solutions are when you restrict the equation AX equal B into the maximal non-singular submatrices and the corresponding portion of the right-hand side. The convex weights of this combination are proportional to the determinant square of Aij of a maximal non-singular submatrix. And because the sum of them is just the volume square, this is the weight. And the corresponding result for the Moore-Penrose inverse is that the Moore-Penrose inverse is a convex combination with the same weights of the inverses of the basic matrices, that is non-singular, maximal non-singular submatrices, padded with enough 0 to make this compatible. A full rank factorization of A is CR, where C is of full column rank and R is of full row rank. Example, singular value decomposition, QR, etc. And we have an interesting result that the volume of A is equal to the product of the volume of its factors. So it's the volume of C times the volume of R. This follows directly from definition 1, and in fact, we can use this to prove the equivalence of the two definitions. Both the volume and determinant are best understood in a setting of multilinear algebra. So let V be a finite dimensional linear space over a field F. The exterior or wedge product is an operation from V times V to V that is anti-commutative. The scalar comes out and it is distributive in both variables. Now the case exterior power of V, denoted wedge KV, is simply the space of all exterior products of K elements from V, and in particular the dimension of wedge K Rn is n choose K. compound matrix comes next. It is the matrix representing the linear transformation from the exterior, the K exterior product of V to the K exterior product of U. And it is defined by CKA, the linear transformation represented by that matrix, times the exterior product of X1 to XK, equal to the exterior product of AX1 to AXK. So the compound matrix is CKA is M choose K by N choose K, and it is of rank RK, R choose K, and in particular CRA is of rank 1. Now, if A is N by N, then CNA is just the determinant of A, as we can see in this relation that the exterior product of AX1 to AXN is the determinant of A times X1 through Xn. And this is for all n vectors in Rn. If the matrix is m by n of rank R, then the absolute value of CRA is the volume of A. And the same relation for any R vectors has plus minus vol A in front. The compound matrix allows us to define some intermediate volume. So the K volume will be just the Frobenius norm of CKA, or equivalent in terms of singular values, it is square root of the K symmetric function of the square of the singular values. And these have also interesting volume interpretation, but they are beyond this lecture. Let's look now at the singular value decomposition of A. I write it in minimal form so that 0 singular values will be deleted together with the corresponding columns of U and V. So in particular, U and V are not unitary matrices, but just the columns that correspond to the positive singular values. The columns of U are orthonormal bases of the range of A, etc. The corresponding singular value decomposition for CRA, A is of rank R, is this. The metric CRA, sigma, the metric sigma comes out as the volume of a number. The vectors U, the matrices U and V come out as U wedge, V wedge, and these are the exterior products of the columns of the matrices, and they are also the Grassmann or Grassmann-Plücker coordinates of the range of A and the range of A transpose. And now move to the differential geometry of surfaces. This stuff is 200 years old by Gauss, given by Gauss. On the left, we have a part of the XY plane. On the right, we have a part of a surface obtained by mapping XY plane into the surface by the mapping phi. And we define three objects, E, F, and G. E is the dot product of the X gradient of phi with itself. G is same for the gradient phi y, and F is the mixed dot product. The first fundamental form of Gauss is the length element ds, and in fact ds squared is a quadratic in dx and dy, with E, 2F, Gs coefficients. But we are interested here in the area element dA, and we can write it, we can simplify it as the square root of Eg minus f squared dx dy. And in particular, the area of phi u for any set u on the left is the integral over u of the square root of Eg minus f squared dx dy. And this is due to Gauss. And the connection with the previous, with the present lecture is that the square root Eg minus f squared is the volume of the Jacobian J phi in the background. And to show this, keep the same picture. And consider the mapping phi that takes xy into xy and z, which is itself a function small f of xy. The Jacobian is 3 by 2, and there it is, and its columns are phi x and phi y before. Eg minus f squared, if you do the arithmetic, is 1 plus fx squared plus fy squared, and it is just the volume square of the Jacobian using our definition. So we can write dA as the volume of j phi dx dy. So this is for the area element dA, and in general the area of phi u on the right is an integral over u in the left of that volume times dx dy. So this is the preparation for the change of variable formula in integration. The unit normal at the surface must be perpendicular to phi x and to phi y, and therefore it must be proportional to minus fx, minus fy, and 1. But it is normal, it is unit vector, so we have to divide by the Euclidean norm, and it is just the volume of the Jacobian. So this is the formula for the unit normal, and we get the same formula for an n-dimensional surface. And now we move to change of variables integration, the formula given by Jacobi in 1840. We have an integral over the set phi u of a function capital F. Okay, and instead we sometimes prefer to do the integral over u of a more complicated expression, but it may be actually a simpler integration. So on the right you see the composition of capital F and phi and the absolute value of the determinant of the Jacobian. Now if u and phi u are in spaces of different dimensions, then we cannot use A because the Jacobian is not square. However, if the Jacobian is a full column ranked throughout U, then we can replace the absolute value of the determinant by the volume and get this formula, which is the change of variables formula for integration between spaces of different dimensions. In particular, if m is equal to n, and I should add that the Jacobian is non-singular, then the volume is just the absolute value of the determinant, and B reduces to A. Okay, here is an illustration. I have to integrate a function capital F on the surface S, and in particular on a portion phi u. And this integral is the same as the integral over u below of the function, and now the function does not mention z. Instead of z, we have fxy, and we have the volume of the Jacobian is 1 plus fx squared, square root of 1 plus fx squared plus fy squared. When we have a vector field and we want to integrate it over the surface S, the same formula gives us integral over S of f ds, and on the right you have the integral over u, and here we have the inner product of f and the unit normal to the surface times the volume of the Jacobian times dx dy. And here is a magic trick. The volume is the square root of 1 plus fx squared plus fy squared. The unit normal has the same square root in its denominator, so we get a wonderful cancellation, and the integral of f ds over s is the integral over u of a simpler expression, and the square root disappeared. Application to probability. Let x1 to xn be random variables with a joint density f of x, fx, h from Rn to R, a well-behaved function in particular, it must depend on some of the variables. So we assume that dh, dxn, the partial of h with respect to xn, one of the variables, call it xn, is not zero. And it is required to find the density of the random variable y, which is h of x1 to xn. So we solve for the variable xn in terms of y, and we call this h inverse. So xn is h inverse of y given all the other x's. Change variables from x1 xn to x1 xn minus 1 y, so we still have n variables, and calculate the determinant of the Jacobian, and it is the partial of h inverse with respect to y. The Jacobian has the first n minus 1 rows, the same as the identity matrix. So the determinant is just the bottom right element, which is partial of h inverse dy. And we can write the density of y using the Jacobi formula. So it is the integral over the variables x1 to xn minus 1. And we have the determinant of the Jacobian. Alternatively, we can structure our variables differently. We can say that x1 to xn will be phi of x1 to xn minus 1, and the function phi is x1 to xn minus 1, followed by xn, which is h inverse of y x1 xn minus 1. Then the surface integral of the density of x over vy is the surface where the random variable y gets the value small y. So the integral of fx over that surface is then using the volume expression, the integral of fx, the density of x, times the volume of the Jacobian, times dx1 dxn minus 1. And here we have a nice result that if the ratio of the two scales we used, one of them was the partial of h inverse with respect to y, and the other one was the volume of the Jacobian. So if the ratio of these two does not depend on the x's, may depend on y, but not on the x's, then the density of y is that expression, a, comes out of the integral because it does not depend on x, times, and now we have a much simpler expression, the integral of the density of x over the set vy. This is where the random variable y has the value small y. Now, why would this condition be satisfied? Well, it is satisfied for some very useful functions. For example, the linear combination of the variables, the linear combination of the x's, sum of x squared, or the exponential of the sum of x of the xi's. So for these three functions, perhaps others, we can get very simple expressions for the density of the function of the random variables. Check the condition for the function for the sum of squares. So when y is sum xi squared, we can solve for xn as plus or minus square root of y minus the sum of squares of all the others. And then the partial of this with respect to y is simply plus or minus 1 over 2 the square root. Similarly, the volume of the other Jacobian will be square root of 1 plus the sum of squares of the partial of h inverse with respect to xi. And when we simplify, we get square root of y divided by the same square root. And therefore, the partial of h inverse with respect to y divided by this is simply 1 over 2 square root y. It is independent of the xi's, and therefore the density of sum xi squared is expressed in terms of the integral of is the density of f with respect to x on the sphere of radius square root of y, because on that sphere, the sum of xi squared is equal to y. Okay, this correlates this result. And now let's look at a strange example. I calculate here y is the sum of square of two independent, identically distributed random variables uniform in 0, 1. And here is what the density looks like. It is constant from 0 to 1. And it is, after this, it goes down according to minus arc cosine of 1 over square root y. So it is pi over 4 from 0 to 1. So if we have a conditional density, that is, I add a condition that the value of y must be less than or equal to 1, I get a uniform distribution from 0 to 1, which is very strange. Before I explain this geometrically, my good friend Yishai Weissman from the Technion was moved by this example to calculate this density of y for all n. And in fact, this is the only one that is pathological in this sense. And here is a geometric explanation using the formula. What we do is that we calculate the length of this arc, of this quarter of a circle, and divide by 2. This is why we get here pi over 4. So when y is less than 1, we get the full quarter circle. But when y is greater than 1, then we only get part of the quarter circle, and this is the part that appears in the formula pi over 4 minus the arc cosine. Okay, now since the volume was first announced, there are many applications. One is for face recognition, where we have an atlas or album of faces, and we have a new face, and we ask, is it included in the album? And the answer is yes, if the volume of the difference between the new face and one of the faces in the album is less than epsilon, where epsilon is fixed, and no otherwise. And in fact, this method was checked, compared with 4 other methods, and it is better when you have little information. So this expresses the green, the accuracy is replaced by the green line. There are other applications, and I listed here some of them. I also have a bibliography that consists of 100 plus items, some with PDF links and other links. And if you are interested, please let me know, and I'll send you the full slides of this lecture with the bibliography and some other stuff I could not cover in the allotted time. Thank you for your attention.
Thank you. Now the next session will start exactly at 10:15. Small announcement. Parallel session for IWMS and ICLA is going on right now. So IWMS events are taking place in Professor George P.H. Stan Hall, and ICLA events are taking place in Professor C.R. Rao Hall. From 12 o'clock onwards, we will be having a common session for both IWMS and ICLA. Please join Professor C.R. Rao Hall after 12 o'clock. Thank you.
Raksha.
Yes, sir.
Raksha.
Hello,
It is time to start.
welcome back everyone. In this technical session, we have with us Professor Sharad Sane from Chennai Mathematical Institute, Chennai. He is a former professor of IIT Bombay. Currently, he is an adjunct professor in Chennai Mathematical Institute, Chennai. He is awarded as Fellow of Indian Academy of Sciences, Bangalore, Coimbatore. His area of interest are graphs, cryptography, discrete mathematics, graph theory, discrete geometry, coding theory, etc. Today, he will be talking on the topic on the riser designs and riser conjecture. Welcome you, sir. Another speaker of today's session is Professor Murali K. Srinivasan from Department of Mathematics, Indian Institute of Technology, Powai, Mumbai. He will be delivering a lecture on Q analogues of the CAT matrix and the adjacency matrix of the MQ. I now request Professor R.B. Bakrat from Indian Statistical Institute Delhi Center to chair the session. Sir, over to you, please.
Okay, thank you. So I now request our first speaker, Professor Sharad Sane, to deliver his talk on riser design and the riser conjecture. Over to you, Professor Sane. Yeah, so will it be a recording or is he present?
No. Is he not there?
Okay, he is there. Yeah, okay, please go ahead. Yeah.
Outset, I would like to thank the organizers,
Okay.
Manipal University. I think is the second time I'm giving a talk in ICLAA. Thanks a lot for the invitation and hope our associations will also continue. I'm now located in Chennai from Mumbai, where I shifted almost 3 years ago. And thanks a lot for all that. Okay, having said that, let me allude to this topic. This is a topic that presumably connects a reasonably hard problem in combinatorics, theory of block designs with linear algebra. And see the connection as we progress. But the thing is, this is a conjecture that has been outstanding for quite a long time. Also, it was made by a fairly leading linear just those days. Someone who long ago wrote a book on combinatorics, but mainly worked, a lot of his work was in linear algebra, namely H.J. Reiser. Reiser wrote a book on combinatorics. This came in 1950s. And in fact, the conjecture is also made there in that book. So let me go further. So this is what the scheme of the things is going to be. Basically, in order to understand the problem, what is a lambda design, or what is now an accepted term called riser design, because he made the conjecture on riser designs. One has to understand what a symmetric design is and some ideas about the symmetric designs. Then the basic result, and then towards the end, I'll allude to main results in this area that are known. So it's a very fascinating conjecture. Perhaps a solution would come out in the next few years, maybe in decades, but it should probably be using both combinatorics and linear algebra. So this is the idea on some idea on symmetric designs. Before I do that, let me kind of highlight the importance of the topic. And this is a book, in fact, when I finished my PhD in 1980s, that's when the book came. I finished my PhD in 1978, but the book came around 1980 or 82. And this is a book, Studies in Combinatorics, published by the Mathematical Association of America. The book has something like 8 or 10 chapters, each written by a different person, expert in his area. So the thing on block designs is written by someone called Marshall Hall, quite a well-known combinatorialist, number theorist in those days, who is also no more. But the preface is written to this book, Studies in Combinatorics, by Giancarlo Rota. And I'll read this out. Block designs are generally acknowledged to be the most complex structures that can be defined from scratch in a few lines. Progress in understanding and classification has been slow and has proceeded by leaps and bounds. One ray of sunlight being followed by years of darkness. The subject has been made even more mysterious, a battleground of number theory, projective geometry, and plane cleverness. This is probably the most difficult combinatorics going on today, says Rota in 1980s, 1983, 84. This probably remains true even now. I mean, it is considered a special area in combinatorics. Though it has also taken help, as Rota himself says, it has taken help from many other areas, including number theory, quite a lot of number theory, as also linear algebra. A lot of techniques used are linear algebraic in nature. So here it is. By block design, one understands a collection of points, distinguished subsets of the point set. So we have a V set, a set of order V, a distinguished family of subsets of this set. Generally, it's these are called blocks. And with the property that every block has the same size, namely generally that's the parameter k is what is written here. And along with the property that every 2 points are commonly contained in precisely lambda blocks, in exactly lambda number of blocks. So there are 3 basic parameters here. V for the size of the point set from which all the points are coming. K for the block size. Every block has the same size k. And every pair of points is commonly contained in exactly lambda blocks. This is a famous inequality called the Fisher inequality. So just a quick look at the proof of Fisher inequality. So this is a first application of linear algebra technique in this area. Statistician Fisher, the inequality is alluded to Fisher. N for the point block incidence matrix, a good enough example of this situation when all the blocks have same size, which is what we expect, is when k is equal to 2. When k is equal to 2, the resulting thing is one can take it to be a complete graph. Complete graph on V vertices has the property that every pair of points is in a unique block because my blocks, excuse me, are edges. They're nothing but edges. And therefore, because this example is ubiquitous, this is to be discarded. It's not to be taken into account. Because for every V and k equal to 2, we can construct this. N is the point block incidence matrix of the design. You put a 1 whenever a point is on a block, and you put a 0 when a point is not on a block. What you then see is, of course, as a consequence, a two-way counting is what is required here. We go back again. V for the number of points, K for the block size. If a point occurs on R blocks, then a two-way counting will produce an equation of the kind R times K minus 1 equal to lambda times V minus 1. Lambda and V are fixed here, and K is also fixed, because of which R, the replication number of a given point, it does not depend on the chosen point. It's independent of the chosen point. It just depends on these three numbers, Vk and lambda. Which is what you see here. And then transpose refers to inner products of, so this matrix on the left is basically just the inner product of, it just records the inner product of any two rows. On the diagonal, you have R, the replication number of a point, and on the off diagonal, you have a lambda on. So this is a matrix in which you have R on the diagonal and lambda on the off diagonal. That matrix is non-singular because R is larger than lambda, and that's because V is bigger than K. And therefore, it's invertible. This matrix is invertible. One can actually see that these are the eigenvalues. The lead eigenvalue Rk with multiplicity 1, and the other eigenvalues R minus lambda. All of them have multiplicity V minus 1. In particular, so this already says that the rank of N transpose, which is less than or equal to rank of N, and therefore the rank of N, the number of rows here is V, and number of columns is B for N. Therefore, because you have as many as V, the rank is V. V is less than or equal to B. That's exactly what the previous slide said. We always have V less than or equal to B. Then you address the situation when V is equal to B. When V is equal to B, the matrix on the left, the matrix N itself is a square matrix. And because N transpose is invertible, N, which is now a square matrix, is also invertible. You have this other information, Nj, the all-one matrix, is equal to Kj. In addition, you also have J times N, also equal to Kj. Therefore, that, and N is invertible. And therefore, pre and post multiplication, the standard thing here by N, tilts this equation in the other direction. Instead of N transpose, I compute N transpose N. And I see that the right side is just the same. It is just the same as the right side for this equation of N transpose. Conclusion that I draw then is, if I, so the combinatorial, one interpretation of this combinatorially is that this matrix N transpose, which is gotten by making points into blocks and blocks into points. So look at a situation where you just convert the till this exactly the other way around. It satisfies the same equation as the one satisfied by N. And that prompts this definition. A design with V equal to B is called a symmetric design. This is what was generally called SBI-BD, symmetric balanced incomplete block design by statisticians. Incidentally, the word symmetric here has to be understood little carefully. It does not mean that the incidence matrix is symmetric. That is not true. Incidence matrix is just a square matrix. When one is not saying here that though N transpose is symmetric, it's not true that N is symmetric, even if it is even though it's a square matrix, it's not necessarily true that it's a symmetric matrix. So the terminology is stuck on here. Design with V equal to B is called a symmetric design. Fisher inequality essentially asserts that the dual, and this dual here, the word dual is used with lot of meanings. The dual here is exactly what I just said. You make points into blocks and blocks into points. The resulting object is also symmetric design. So this is what should generally be called combinatorial dual. It's a combinatorial dual. It's not a matrix. It's not dual in the algebraic sense. In fact, what we have is this is a lot of characterizations for symmetric design. Number of points is equal to number of blocks. That is what the first characterization is saying. That's the definition. R is equal to K. Every point is replicated the same number of times, which is the block size. So there is a combinatorial symmetry here. Any two blocks intersect in lambda points. The dual of D is also symmetric design. There are many reasons for studying symmetric designs more than block designs in general. Lots of problems are interesting. One can ask the question, I give you the parameters V, K, and lambda. They determine the other parameters, namely R and B, the number of blocks. Suppose the necessary conditions here are satisfied. The necessary conditions here come from combinatorics, the two-way counting. They're all consequences. Both the equations that you get, they're consequences of two-way counting. For example, the equation like R times K minus 1 is equal to lambda times V minus 1 says that necessary condition is K minus 1 must divide lambda times V minus 1. These objects, the symmetric designs are more studied. They are more studied than other designs. The problems are interesting for all kinds of designs, but one focuses more on symmetric designs. There is an inherent combinatorial symmetry there, which I will not have time to get into. Also, these have better connections with group theory, number theory, and other similar objects. And therefore, they are more studied. They are of considerably more interest because they interest people in working in other areas as well. So that's an occasion to look at word of symmetric designs. I'm basically going to look at two examples. The first of these comes from matrices. Hadamard matrix of order 4T has entry +1, -1 with the property that every two rows are orthogonal. This is a square matrix. It's an n by n square matrix in which all the entries are +1 and -1, and every two rows are orthogonal to each other. In terms of matrices, this will simply mean that H times H transpose is n times identity. N multiplier n is equal to 4T, the order of that matrix. What one observes is many things here. I can multiply a row uniformly, all the entries on that row by -1. There's no harm by doing that. So you can swap all the entries from +1 to -1 on any row. I can do that for every column as well. That's not going to change the inner product of rows. By doing this, I can convert H into what is called a standard form. So the top row consists of all +1s. In fact, in addition, I can make the first column also to consist of +1s. Now you delete the first row and first column. change minus ones to zeros and ones remain as ones, we get the incidence matrix for a symmetric design, 4t minus 1, 2t minus 1, t minus 1. This is called a Hadamard symmetric design. This procedure is reversible. It requires a little soiling of hands. This is reversible. I give you a 0, 1 matrix, 4t minus 1 by 4t minus 1, with the property the binary matrix, in which all the row sums are 2t minus 1. All the inner product between any two rows is t minus 1. Then you can suitably border this. You can add an extra row. The first row and first column, they can be suitably added. And then changed in the original, the matrix was binary, convert 1, 0 situation to a +1, -1 situation. This is typically what is done in other areas allied to this object. Namely, Hadamard matrices have a key role in many, many things in coding theory. This is a very standard conversion, where you change the binary setup of 0, 1 to, which is an additive setup, where you are going modulo 2 additively. You convert that to multiplicative setup, +1, -1. But now everything is done multiplicatively. And this change is, in terms of algebra, both the groups, one is an additive group, the other one is a multiplicative group. Therefore, this is only a notional change in so far as algebra is concerned. But so far as coding theory is concerned, this change is not notional. It is not notional. It's very important. Many constructions of codes depend on this notional conversion. Typically, things such as simplex codes, etc., they are constructed using Hadamard matrices of right types. That order, what one can prove by taking the inner products of, you can assume that the first row consists of all +1s, and then you take the inner, what it means is the row number 2, row number 3, etc., must have exactly n upon 2, half of them must be +1, and the remaining must be -1. Then you take the inner product between the second row and third row. Therefore, there are 4 variables one can set up, write 3 equations, and that will show that number of things where the pluses match, number of things where it is +1, -1, they're all equal. And therefore, that will show that if my order of the Hadamard matrix is not 2, then it's a multiple of 4. This is a very long-standing conjecture in the theory of Hadamard matrices. Namely, it's very widely believed that Hadamard matrices exist for every order, which is a multiple of 4. I think the latest on this was below the order 4000. There is something like only 37 odd entries where the existence is not known. No counterexample to this conjecture is known, and nobody believes that there will be a counterexample. In fact, using composition techniques, many orders of Hadamard matrices can be captured very easily. One is a Kronecker product technique. The standard way of looking at it is what is called doubling technique. From a Hadamard matrix of order 2, you can get one of order 4, and therefore one of order 8 and 16, etc. Incidentally, Hadamard matrix of order 32 was used in the first lunar mission. So the code gotten from it was actually used there. So Hadamard matrices by itself is a very big area. For our purpose, they give rise to a symmetric design. And these are associated. They are in fact called Hadamard symmetric designs. Yet another example that I would like to look at is this. the special example for Fano plane. A projective plane is gotten by looking at a field with Q elements, taking as points the points of the projective geometry, two-dimensional, and as lines or as blocks the lines of this projective geometry. In terms of vector space, it's a three-dimensional vector space. Therefore, as points, you take all the one-dimensional subspaces. As lines, you take all the two-dimensional subspaces. And incidence by belonging, the set theoretic belonging. This gives a projective plane. This gives a projective plane. That's a symmetric design. Nothing to check here. In fact, there is a point line duality here, the standard algebraic duality, point line duality under the usual inner product that one can define. And that says that this is a symmetric design. In fact, this can be replicated, this construction, this can be mimicked for higher dimensions as well. So the point hyperplane incidence structure, hyperplanes as blocks, points as points of the projective geometry, they give symmetric design. This is generally called a projective design, in fact. And this has parameters of this form, q power n plus 1. That's because the vector space dimension is n plus 1. That's the size of a hyperplane. And that's a space with codimension 2. Many constructions, so these are two important families. In fact, they're most important among the families of symmetric designs that are known. Existence question of symmetric designs is the question of constructing a 0-1 matrix satisfying the matrix equations. Algebraic number theory has been employed in order to answer this existence question. And the relevant seminal result, this is known as the Brach-Reiser-Chola theorem. Unfortunately, the BRC theorem works only in one direction. That is, it provides us with only necessary conditions. These conditions may not be sufficient. For example, it's not known whether there is a projective plane of order 12, but it is known thanks to Brach-Reiser-Chola theorem that if Q is the order of a projective plane such that Q is congruent to 1 or 2 modulo 4, then Q is a sum of 2 integer squares. So in particular, any number of the form 6 modulo 8, elementary exercise in the handling numbers, any number of the form 6 modulo 8 cannot really be written as a sum of 2 squares. So there are no projective plane. There's no projective plane of order 6 or 14, etc. Extensive search for almost 200 hours of the then very fast Cray computer those days. It actually took something like 190 days in 1980s to show that there is no projective plane of order 10. This search also involved intersection with other areas. And this, if you look at the paper published by these authors in 1980s, it actually uses coding theory and then in turn various weight enumeration ideas. Therefore, it's not a purely combinatorial proof. In addition, it also used 200 hours of computers available on those days, the fastest Cray computer. There have also been a large number of new constructions of new symmetric designs. The recent times here is last 20 years or so, based on the work of this Indian mathematician who lived in Africa for a long time. He's no more, Dinesh Rajkondlia. Ion in the last decade constructed new families of symmetric designs. Many of these were open questions for a long time. About 23 infinite families of symmetric designs are known as of now. This doesn't mean that there will not be any more. The classification problem is considerably harder. And that is, I'll allude to this a little more, and then will go to the riser design. When lambda is, these are all the known constructions. When lambda is 1, it's a question of existence of what is called projective plane. And this always exists whenever Q is a prime power. So these are infinitely many in number, because the prime powers are infinitely many. When lambda is 2, such a thing is called a biplane. The parameter V then turns out to be K choose 2 plus 1. These are known to exist for small values of K. 3, 4, 5, 6, 9, 11, 13. No other examples are known, nor is it known that none of them will exist. When lambda is equal to 3, all the known examples have K bounded by 15. So the situation gets more and more tight. When lambda is equal to 4 or bigger than or equal to 4, all the known examples have K bounded by a quadratic in lambda. It's lambda square plus lambda. And that led mathematician Marshall Hall to make that conjecture: for every lambda at least 2, there exist only finitely many symmetric designs. A stronger thing will be to give a bound on K actually. So this is not even a polynomial bound, it's even a quadratic bound. So it's much stronger than the previous conjecture. And he made both the conjectures. Both of these are unsolved as of now. Okay, thanks mainly to the difficulty in constructing symmetric designs, Riser mooted the idea of riser designs. He did not call them riser designs. That's why in brackets in parentheses I've written lambda design. Because Riser thought that it maybe that from riser designs one can construct a symmetric designs. And we'll see the connection, how riser design is connected with a symmetric design. That was initially the idea that Riser had. It's actually quite an ingenious idea, very ambitious plan. So in a combinatorially dual setup, consider a configuration with equally many points and blocks. I want to use V there, so that should be, instead of N, that should be V, with the property that all blocks are proper subsets of the point set and have sizes strictly larger than lambda. Every 2 blocks intersect in lambda points. So in terms of incidence matrix, let's see what is happening here. In terms of incidence matrix, what is happening here is I have a square matrix, a binary square matrix, equally many points, and namely V points and V blocks, with the understanding that every 2 blocks intersect in lambda points, which translates to N transpose into N, having entry lambda on all the off-diagonal positions. Example of this situation is, of course, a symmetric design. In fact, we can make a further, as all the blocks have same size, or every point is replicated same number of times. Then the configuration that we get has to be a symmetric design. So there's nothing new about this. The symmetric designs are exactly those configurations that have, in terms of matrices, they correspond to square binary matrices, equally many points and equal as many blocks as points, with the property that every N transpose N is equal to lambda on all the off-diagonal positions. It's just that a symmetric block design, symmetric design requires one to have the same column sums, or equivalently the same row sums. This is not an assumption anymore. So are there examples of incidence structures, as we defined, that are other than symmetric designs? This will require that we have at least 2 block replication numbers or at least 2 block sizes. Woodall, a British mathematician, Riser, American combinatorialist, they constructed families of such configurations from symmetric designs themselves. So from a symmetric design, one can construct such an object. What is done here is you fix a block X of that symmetric design, construct a new configuration D prime, whose blocks are, so X is fixed here, that block X is fixed. Now you change each Y to a Y prime by taking its symmetric difference with X. It requires a little bit of checking that, so now what has happened here is I fixed my block X, so X dash X prime is equal to X. Whereas for any Y which is not equal to X, Y prime is this symmetric difference taken with X. The resulting configuration clearly will have as many blocks as points, that's very clear, because for each block I get a new block, except for X. It's just that Y intersects X in exactly lambda points. So Y minus X will have size K minus lambda. X minus Y will also have size K minus lambda. And therefore, the left side set here, Y prime will have size 2 times K minus lambda. This gives an incident structure with V prime equal to V and lambda prime equal to K minus lambda. Now what will happen is every 2 blocks, instead of intersecting in lambda points, they will, it's quite clear that Y prime intersects X itself, which is fixed, in the points of in exactly K minus lambda points. Because those are exactly the points in X minus Y. They are there in X and they will also be there in Y prime. Therefore, lambda prime is K minus lambda. Any 2 blocks now intersect in K minus lambda points. But now what has happened is we have 2 block sizes. Therefore, this is not a symmetric design. The block sizes now are 2 times K minus lambda, as also 2 replication numbers. Notice that except in the degenerate situation, when K is equal to lambda, K is equal to 2 lambda, the resulting incident structure is not a symmetric design. And that prompts, so this is what Riser himself called lambda design. Slightly a misleading term because one has to go through this combinatorics. But now the accepted term is Riser design. It is called Riser design. Incident structure with equally many points and blocks, in which every 2 blocks intersect in the same number of points. This is called a Riser design. If it has at least 2 replication numbers. The requirement that it has at least 2 replication numbers makes certain, it makes very certain that this cannot be a symmetric design. Well, then Riser himself asked the question, is it true that every Riser design must come from a symmetric design in the manner that I just described on the previous slide? Is it necessarily true that every Riser design must arise in this manner only, and there is no other way it could be constructed? If that is really the case, then there is a kind of equivalence there. That just means that existence question of symmetric designs and Riser designs is equivalent. That gives an equivalence between these 2 things. It's not that there are more Riser designs than those that are symmetric designs. They just go hand in hand. So this is definition of Riser. It's called a type 1 Riser design if it is obtained from a symmetric design exactly in the manner that is described in the previous slide. So by taking symmetric differences. The point here is now this is a very wild kind of thought, because riser design gets defined just by the constraint that you have a binary square matrix, equally many points and blocks, with the property that you have at least two row sums, or equivalently at least two column sums, in which every two columns have exactly lambda ones in common. Equivalently, n transpose n will have lambda on the all the off diagonal positions. There have been attempts to show that a riser design comes only in that manner. Let me go to the next slide. This is a conjecture. The lambda design conjecture of Woodall and riser independently, the conjecture was made by both of them. Every riser design is a type 1 riser design. What's a type 1 riser design? It is one which is obtained from a symmetric design exactly by a process, the riser-Woodall process, the symmetric difference process that I just described. What you'll have to do is, for a riser design to have come from a symmetric design, I'll have to reverse this procedure. I'll have to entirely reverse this procedure. I'll allude to this a little later. Kind of a combinatorial procedure where from primes, from y prime, I should be able to get y, which perhaps can also be handled in via matrices, but presumably the level of difficulty is same. That's the lambda design conjecture, or what we'll call the riser conjecture, riser design conjecture. Every riser design is a type 1 riser design. And basically what prompted riser to make this is, of course, riser was probably not in the habit of just throwing in conjectures. He proved probably the most fundamental result on riser designs was proved by riser. He himself proved that. He strongly believed in the validity of his conjecture. The conjecture has also been verified for values of lambda at least up to 100. To the end of proving the conjecture, the most fundamental result was proved, as I just said, by riser himself. This result states that any riser design has exactly two row sums. It has exactly two row sums. All the known proofs of, sorry for the repetition of the word proofs, of this result are linear algebraic in nature. The one that is given here is more modern. This is from the book by Ionin and M.H. Srikhande. And this is essentially based on some change of basis argument. The original proof that riser gave is equivalent to this. He used matrices. He actually made an outright use of matrix. It's a question of taste and choice here. So the proof that is more modern actually uses vector spaces. It actually does use right kind of vector space. D is a riser design, then D has exactly two replication numbers. So this is a theorem of riser and Woodall. R1 not equal to R2. In fact, this is quite important, such that R1 plus R2 is equal to V plus 1. Total number of points plus 1. So it's a pretty tight situation. R1 and R2 are not arbitrary numbers. Their sum has to be the total number of points or total number of blocks plus 1. Okay, let me quickly go over this proof. The vector space, so this is formally spanned by linear functions g in n variables, x1, x2 to xv, each variable corresponding to points. points of the riser design. So this is a linear function. Rather, the first term is first term on the right, the first summand on the right is linear. By adding a b, you take some fixed field, therefore it's an affine function. So v is then, because the variable say I can take any value in the field, as also b. So this is v plus one dimensional vector space. Incidentally, the confusion between n and v is because authors use both n and v for this. It's a v plus one dimensional vector space with a natural basis that consists of v functions xj and the constant function, everything equal to 1. We already have a riser design D over that set S. Label the points in S by from 1 to V naturally, then G is given as above. T subset of S. Then I compute G of T, the support. So this is a linear functional. We thus express T in its binary form, and then G of T is nothing but G evaluated at each xi equal to 1 for I in T and xi equal to 0 for I not in T. The proof then essentially consists of finding a different suitable basis and a clever use of a change of basis formula. All you need to know here is change of basis formula. But it achieves something. What in fact they show through this is that you will have two constants, R1 and R2. Rather, instead of R1 and R2, it is R1 minus 1 and R2 minus 1, whose sum is V minus 1. For them, there is a quadratic that one can obtain. One can get a quadratic which depends only on V and lambda, such that the coefficients, they are in V and lambda. And therefore, because it's a quadratic, the sum of the roots is V minus 1, as I just said. The product of the roots is also known, and therefore they get uniquely determined. They get uniquely determined. That is the constancy of these two numbers. So you cannot really have 100 replication numbers for a riser design. There are exactly two replication numbers whose sum is V plus 1. In fact, I'll get into this few minutes later. So results here at a glance. A student, Riser in fact himself proved the validity of the conjecture for small values of lambda. There were PhD theses written. In fact, Kramer and his students also wrote a number of PhD theses on this problem. Till 1980s, values up to lambda equal to 10 or 20, these are actually proved, where they proved that the riser design conjecture is true. This was the first paper in that direction where infinitely many values were covered. Singhi and Srikhande proved the conjecture when the index lambda is a prime number. Unfortunately, this has not even been generalized to prime power. So it's not as easy as it looks. Ceres, considerably later, almost 20 years later, proved the truthfulness of the conjecture when lambda is twice a prime number. Arjun and Srikhande developed a new approach to the design conjecture that led to new results for certain parameter values. In fact, they approached this from a, their results prove the conjecture for certain values of V rather than lambda. They prove the validity of the conjecture. This is also incorrect, the last line. V is a prime number plus 1. It's a prime number plus 1. One has to look at these situations carefully. V is combinatorially the number V strictly dominates the number lambda. Therefore, if you fix up V, the number of situations that you have to handle is only finitely many. On the other hand, if you fix up a lambda, the number of situations that you have to handle is not guaranteed to be finite. That's clearly not true, because we can take infinitely many values in that case. So one has to be careful here. I mean, the strength of a result depends on these considerations. So in that sense, the results of Singhi and Srikhande, Ceres, they're much stronger than the results where you put a constraint on V instead of lambda. Okay, in the last few minutes, I'll now allude to recent work, recent meaning the last 2 to 3 years work. 2020, this person, Tushar Parwekar, he got his PhD thesis with me. This was the last thing that I owed to IIT Bombay. So his PhD thesis was finished in 2020, just last year. I think it's, forget now, it's probably a year and a half ago. So this is a symmetric difference. The symmetric difference has size of A plus size of B minus 2 times the intersection. That if a design is of type 1, then it has, what is an average block? Average block is, there are two lambda is the right kind of size for a block. In order for a riser design to be of type 1, recall the construction that we had here. Size of one block is K, and size of all the other blocks is 2 times K minus 1, 2 times K minus lambda. Now you call that 2 times K minus lambda, which is your new lambda. That is your lambda prime for the riser design. So it is of type 1 if you call such a block an average block. So all the blocks should be average blocks except for one. And therefore, if at all there is a hypothetical type 2 riser design, what's a type 2 riser design? Type 2 riser design is something that has not been constructed. So far, riser conjecture itself says that there are no type 2 riser designs. You cannot really have type 2 riser designs. But if at all there is a type 2 riser design, it must have at least 2 non-average blocks. So this is a very elementary observation. D is a riser design of order V and index lambda. It is known that it has 2 invariants, R1 bigger than 2. I just said that. Every point has a replication number, either R1 or R2. This technique is there in Singhi Srikhande original paper, in fact, which is a seminal work on this area. For every prime, the conjecture is true. What you do is you look at the GCD of R1 minus 1 and R2 minus 1, that is customarily called G. C and D refer to R1 minus 1 divided by G and R2 minus 1 divided by G. Then the right row, this is going to be a reasonably messy thing. R1 minus 1 divided by R2 minus 1 is equal to C upon D, with C and D now co-prime to each other because you have gotten rid of the GCD. Write A for C minus D. Then any two of C, D, and A are actually co-prime to each other. The point set is partitioned into 2 subsets. Thanks to the riser result, one can talk of those points whose replication number is R1 and those points whose replication number is R2. Those sets are E1 and E2 respectively. Small e1 and small e2 are sizes of capital E1 and capital E2. Then E1 plus E2 is equal to V, and R1 plus R2 is V plus 1. So that block is large, average, or small if size of A is greater than 2 lambda, equal to 2 lambda or less than 2 lambda. A block which is not an average block is to be called a non-average block. While writing their papers, Ionin and Srikhande made that conjecture. For any riser design on V points, there is a bound on V, linear lower bound. This more or less corresponds to the Hadamard situation, 4 lambda minus 1. In fact, this is true. Such a bound, conjectural bound, is also made for symmetric designs. And for symmetric designs, this bound is almost like the Hall bound, Marshall-Hall conjecture. So this is what is proved in the paper I have. I'll display the references to those papers after I discuss these results in the next few minutes. Write capital D for E1 minus R2. So there are two situations where here when D is equal to 0 and when capital D is equal to minus 1, the riser design conjecture stands proved in that situation. So this is a bound that is proved in our paper. We also prove that riser designs with number of points at most lambda square plus lambda plus 1 and rho is equal to lambda or rho is equal to lambda minus 1. They're all of type 1. We prove that riser designs, this is like the Ionin-Srikhande result where it's 2 power n plus 1 points. That's also of type 1. This is the first paper. In fact, the papers I'm referring to, they have titled Riser-Woodall conjecture number 1, number 2, and number 3. In fact, they're published in succession, one after the other. The following 3 results are also proved. The number of, yeah, I think that just said that. The second paper actually deals with properly computing, explicitly computing inverse of incidence matrix of a riser design. It is to be believed, this is a natural assumption, that since symmetry designs have incidence matrix which is non-singular, same thing should hold for riser design as well. But an explicit computation was not done. This is quite an interesting paper from linear algebra point of view. This result actually uses calculations on minors that was made in much earlier paper of K. Miller on the formula for inverse of sum of matrices that appeared in Mathematics magazine, 1981. Paper also has an explicit formula for the ratio in terms of other riser design parameters, including V and lambda. The third paper deals with a combinatorial idea of block complementation. This is more algebraic in nature. It's a more algebraic construct. What one can do is, one can see that the block complementation procedure that was employed by Riser to construct riser designs, all of which, because he starts from a symmetric design, the resulting riser design is a riser design of type 1 necessarily. That's the definition. But if you apply the complementation process, the symmetric difference process, to any riser design, the parameters R1 and R2 don't change. They are invariant. They are actually invariant. The replication numbers remain invariant for this entire equivalence class. And this was observed earlier, but this is more crystallized in the third paper of ours that I'm alluding to. Every riser design in the equivalence class of D is of type 1. If the equivalence class contains one symmetric design, then they're all of type 1. The entire equivalence class has objects, all of them of type 1. If one of them is type 1, all of them are type 1. Another strong characterization, if you have a riser design of order V and index lambda with two block sizes, such that one block size is the average block size, then it is necessarily a type 1 design. So if you don't have both large size and small size blocks, then the riser design, this is the hypothesis, then the riser design conjecture is true. It holds under this hypothesis. I'm getting close to my time. So these are the three papers. These are not all that recent anymore. All of them, 2020. The first one is in Journal of Combinatorial Designs. This is not given number 1. Some results on riser design conjecture should be called number 1. It's in the journal JCD. The second one, called number 2, linear and multilinear algebra. This has an explicit computation of the inverse of incidence matrix of a riser design. And the last one, that's published in the Journal of Algebraic Combinatorics, the same year, 2020. Incidentally, this was the last thing that I finished before personal memory, before I left IIT Bombay. The work got finished in 2020, though I had left IIT Bombay in 2018 itself, end of 2018. And the main references, other than these three papers, which are more recent, are the seminal works in this area. Avanin and Srikhande, M.A. Srikhande. This is a book, Cambridge University Press, Combinatorics of Symmetry Designs. Number 2 is good reference. In fact, that's quite a good reference. Matrix approach, linear algebra and applications. Reiser's original paper is number 3, the extension of theorem of De Bruijn and Erdős. Fourth paper is also Reiser. That's the 5th paper by Serres, where he proves the validity for lambda equal to 2 times p. P is prime number, both of them. Singhi and Srikhande paper is the last paper. And thank you very much for listening to me. I'll stop here. Thank you.
So I thank the organizers for their invitation to lecture.
Sharat Sani has not joined us.
Okay.
Yeah,
Okay.
I spoke to him. That he's busy now, and he'll be joining us later.
Okay, so we can move on to the second talk, or that is.
He may join by the time.
Yeah, so we'll go to the.
Yeah, sure. We'll go to Murali.
Okay, the next speaker will be Murali Srinivasan.
Yeah, right.
Okay, so now we will have the talk by Murali Srinivasan on the Q analog of the incidence matrix. Okay, so over to Murali Srinivasan.
So I thank the organizers for their invitation to lecture in this conference. So this is joint work with Subhajit Ghosh, who is at Bar-Ilan University now. And let me. So let me begin with some well-known matrix, which is the adjacency matrix of the N cube. I will define it formally soon, but just let's look at the two pictures. So here I have drawn the 2 cube and the 3 cube. So 3 cube has 8 vertices, all 0, 1 vertices, all 0, 1 vectors of length 3. So there will be 8 vertices, and the 2 cube will have 4. And the adjacency matrix is you take the, let me illustrate for 2. So you take the 4 cross 4 matrix with each row and column will be indexed by vertices of this cube, and you put a 0 or a 1. Each entry would be a 0 or a 1. So it will be a 1 if one of the entries is changed from a 0 to a 1 or a 1 to a 0. For instance, if you look at the third row, so 1, 0. So if we change a 1 to a 0, so 1, 0 is connected to a 0, 0, or it's connected to a 1, 1. And similarly for the other rows. So in the 3 cube case, it will be an 8 cross 8 matrix. So let me define this more formally. So let me go back. So instead of the 0, 1 vectors, I would think of it as subsets of an n set. So each subset of an n set has a characteristic vector, which is a 0, 1 vector. So I can as well index the rows and columns with subsets of an n set. So let Bn will denote the set of all subsets, and Bnk will denote the set of all subsets of size k. And then you define a Bn cross Bn matrix. So a row is, suppose the row is indexed by x and the column is indexed by y. So then what is the entry in x row, y column? So it will either be a 0 or a 1. So you either add an element to x or subtract an element from x. So it's a 1 if y contains x and the size of y is 1 more than x, or if y is contained in x and size of y is 1 less than x. So either we add an element to x or we subtract an element from x. So in those two cases, you put a 1, otherwise you put a 0. So that's precisely what happens in the 0, 1 vectors, right? So either you change a 1 to a 0, in which case you have subtracted an element from x, or you change a 0 to a 1, in which case you have added an element. So this is the matrix. Now this matrix comes up in lots and lots of applications, which I will not be discussing today. So what one needs is to know the eigenvalues and eigenvectors of this matrix. So that's also very well known and classical. So let me just recall the result without going into the proof. It is a very standard proof available in all books. So there are n plus 1 eigenvalues. So remember, it has 2 to the n. It's a matrix of size 2 to the n, but it has only n plus 1 eigenvalues, and they are all integers. They are n minus 2k, and k is going from 0, 1 to n. And the multiplicity of n minus 2k is n choose k. So if you add all the multiplicities, you get sigma over k of n choose k. That will be 2 to the n. And you can also write down canonical orthogonal eigenbasis for each eigenvalue. So if you take the eigenvalue n minus 2k, so you can write down n choose k orthogonal eigenvectors. And moreover, the indexing set for the eigenvectors is also quite natural. For every subset of the n set, you can have an eigenvector. And if the subset has size k, the eigenvector will have eigenvalue n minus 2k. So in some sense, even the eigenvector, the multiplicity also gets some sort of a combinatorial interpretation. You can index the eigenvectors by these subsets. So this is all very classical results. So what we are going to do is we are going to give a Q analog of this result. I will explain what that is. And we'll also consider two applications where this matrix comes up. And we hope more applications are found. In the NQ case, there are literally several applications. So right now we have found two and we hope we get more later. So what is this Q analog? So let Q be a prime power. And so BQN would be the set of all subspaces of the vector space FQN. So FQN denotes a column vector with n components whose entries are from the finite field FQ. And so this is an n-dimensional vector space over FQ. It will have lots of subspaces. So let BQN denote the set of all those subspaces. And BQNK would be those subspaces which have dimension K. Now, another standard bit of notation is KQ, K sub Q or KQ would denote 1 plus Q square up to Q raised to K minus 1. So if you put Q is equal to 1, KQ is actually K. So KQ can be thought of as the Q number or a Q analog of the number K. And the number of subsets of dimension K is denoted NKQ and is called the Q binomial coefficient. So let me define the matrix. So MQN, so this will be the Q analog of the matrix Mn. So MQN would be a BQN cross BQN matrix. So this is a huge matrix. So Bn cross Bn was 2 to the n cross 2 to the n. This will be even larger. So the number of subspaces doesn't have a closed formula, but it's something like Q to the n square. That's the order of total number of subspaces. So MQNXY, what is the entry? So if y is contained in x and dimension y is dimension x minus 1, then you put a 1. If x is contained in y and dimension y is 1 more than dimension of x, then you don't put a 1, but you put a q to the k, where k is the dimension of x. So remember in the q is equal to 1 case, it was all a 0, 1 matrix. Here it's not. So if x is contained in y and y has 1 more dimension than x and x a dimension k, then that entry is q to the k. Of course, if y is contained in x and the dimension is 1 less, then you put a 1. Otherwise, it's a 0. So let me try to explain why is this, what's the motivation for this definition? So remember, Mn was a 0, 1 symmetric matrix with all row sums were n in Mn, because remember, if you consider row x, either you add an entry or you subtract an entry. So every element is either in x, in which case you delete it. If it's not in x, you add it. So the number of changes you can make is n. So every row will sum to n. So it had 3 properties, 0, 1 symmetric and row sum n. So now the way we have defined MQN, it is not 0, 1, it's not symmetric. But it does have some property. The third property is true. That is, the sum of all the entries in a row is fixed. So let us see how. So let's take a subspace X of dimension K. So how many contain it of dimension 1 more? So that is the number of subspaces which cover this. You can easily count. So X has q to the k vectors, and the whole vector space has q to the n vectors. So the number of vectors outside X is q to the n minus q to the k. Now in a given subspace, all multiples will also be there. So if you take a vector outside q to the n minus q to the k and take the subspace generated by adding that to X, you will get the other q minus 1 vectors also you will get outside on that line. So you have to divide q to the n minus q to the k by q minus 1, which is 1 plus q square up to q to the n minus k minus 1. So this is n minus kq. So the number of subspaces which cover X is n minus kq. Now the number which is contained is, you can check similarly. So the total number of vectors in X is q to the k. Total number of non-zero vectors is q to the k minus 1. You divide by q minus 1 because you are only counting subspaces. So this is the number of one-dimensional subspaces, which is same as the number of k minus one-dimensional subspaces. So this is kq. So the sum would be, once it's up, you have to multiply by q raised to k. So q raised to k into n minus qk plus kq. So that's the row sum of the entries of X, which is same as nq. So that's independent of k. So that's the reason for putting the q to the k. You get all the row sums equal to a fixed number, which is nk. So it does have all row sums equal. Now it's not symmetric, but it is very close in the sense of a scaling. That is, a diagonal similarity of this matrix is symmetric. So let's see how that is. So take a diagonal matrix, the BQN by BQN. Now the diagonal entry corresponding to the subspace X is square root of q raised to k choose 2, where k is the dimension of X. So now let's look at the diagonal similarity dq, mq, dq inverse. Okay, so what's the entry in row X? Column Y. So let's say X has dimension k and Y has dimension R. So if you want the entry in row X and column Y, so when you multiply, so let's assume that, so this would be q raised, so square root of q raised to k by 2 into mqxy. So mqxy is non-zero only in two cases. Either y contains X or y is contained in X. So if y contains X and has dimension 1 more, then that entry is q raised to k. So you get the first case is square root of q raised to k by 2 into q raised to k into square root of minus k plus 1 by 2, because r must be k plus 1. So that is square root of q raised to k. Now if y is contained in X, then the entry mqxy is 1 and dimension of, and r is k minus 1. So that is q raised to k choose 2 into 1 into q raised to minus k minus 1 choose 2, which is square root of q raised to r. So if X is contained in Y, then the entry is q raised to k. That is, it's a minimum of dimension X, dimension Y. If Y is contained in X, then it's q raised to R, which is also the minimum of dimension X, dimension Y. Independent, I mean, if X is contained in Y, then you put the dimension of X. If Y is contained in X, you put the dimension of Y. So this makes this matrix symmetric. The entry is, the dimension should differ by 1, and then you put square root of q raised to the minimum dimension. So this matrix is symmetric and therefore is diagonalizable with real eigenvalues. So mqxy is also diagonalizable with real eigenvalues. So our main result is, what are these? So mqn has n plus 1 eigenvalues, and for every k between 0 and n. And the eigenvalue is n minus kq minus kq. And what's the dimension? The multiplicity of n minus kq minus kq is nkq. So the corresponding q binomial coefficient. And if you look at the matrix dn, mn, and dq inverse, we can write down an orthogonal eigenbasis for that. So Now, before going to the proof of this is much more involved than the Q is equal to 1 case. For instance, if you look at item 3, in the previous case, the multiplicity was n choose k, and we could index the eigenvectors by subsets. So here one would think that it's possible to index the eigenvectors by subspaces of dimension k, but that's not the case here. So the eigenvectors can be indexed by a set, which is much more involved, and it involves the irreducible characters of the additive group FQN. So this theorem is more difficult than the Q is equal to 1 case. So before saying something about the proof, we actually have two proofs. The first proof only gives the first two parts. It gives you the eigenvalues and the multiplicity, and it does not give the eigenvectors. And the second proof proves this by writing down the eigenvectors. So before discussing some things about the proof, maybe I'll only discuss the first proof and that too later. So first, let me give you two applications of the main theorem. Okay. So the first thing is Q and the log of a famous tree counting formula. So let's look at the n cube. So the n cube is a regular graph of degree n. Every 0, 1 vector of length n, you can change a 0 to a 1 or 1 to a 0. So you can change in every coordinate. So the degree is n. And it's since the degree is n and you know the adjacency eigenvalues, you also know the Laplacian eigenvalues. And then by the matrix tree theorem, you can get the product of the non-zero Laplacians is the number of rooted spanning trees. So this is a famous formula. So the number of rooted spanning trees in Cn, that's denoted by tau Cn, is the product of the non-zero Laplacian eigenvalues. So the Laplacian eigenvalues are 2k. So n minus 2k, which is 2k, when k is going from 1 to n, with multiplicity of n choose k. So this is the product formula for the number of rooted spanning trees of the n cube. So for a long time, the only known proof of this was using eigenvalues. Essentially the proof I just told you. And some time ago, maybe 10 years ago, in 2012, there was a first non-algebraic proof of this, which was probabilistic. That was found by Bernardi. And so till today, there is no purely bijective proof of this result. So this is a famous product formula. So now our main theorem allows us to give a Q analog of this, which is slightly, let me state it here. So what you do is you have to define the CQN. So you have to define the graph CQN, which is, let me go back, sorry. So CQN is, so the vertices are all the subspaces of BQ in BQN. And then you put an edge between two subspaces, X and Y. If either X is contained in Y and dimension Y is dimension X plus 1, or Y is contained in X and dimension Y is dimension X minus 1. So in other words, you take the poset of subspaces and make its Hasse diagram into a graph. That's about it. So that's called the Q analog of the n cube. It's exactly same as the set case, except that you have subspaces for the vertices. Now, so we want to count rooted spanning trees, but we have to do a weighted count to get the corresponding Q analog. So let me define what is the weight of a rooted spanning tree. So take TQN, let TQN denote the set of all rooted spanning trees of the graph CQN. Now, once you have take a rooted spanning tree T, Now orient every edge towards the root. So that's given any vertex, given any edge, you can orient it towards the root. Suppose the edge is xy. If you go from x to the root, if you go via y, then you route it from x to y. Or if you go from y to the root, and if you go via x, then you route it from y to x. So orient everything towards the root. So suppose e to the xy is an oriented edge, where that means x to y is the arrow is from x to y. Now we say that E is spin up if dimension of y is equal to dimension of x plus 1, and spin down if dimension of y is dimension of x minus 1. So the weight of the tree is sum of the dimensions of x over all spin up edges xy. Okay. So take a rooted tree, orient every edge, look at the spin up edges. The spin up edges means it's going, the orientation is from x to y, then dimension of y is more than dimension of x, one more. Then sum their dimensions of all the spin up edges. That's the weight. So the Q analog of the theorem is that if Q raised to weight of T over all rooted spanning trees is given by this product formula. Product over k from 1 to n, 1 plus q raised to n minus k into kq raised to nkq. So of course, if you put q as 1, the right hand side will become 2k raised to n choose k, product over k, and this will become the number of rooted trees in the n cube. So this is not the usual Q analog in the sense that Q is not a variable here. Q is this is true for every fixed prime power. So you're not taking the rooted spanning trees in the cube and associating a statistic and Q counting. This is actual counting of trees in an infinite family of graphs, but the counting is weighted. It's not just counting every tree once. But nevertheless, when Q is 1, you do recover the previous result. And this proof is, once you have the eigenvalues of that matrix, MQN, this follows almost directly if you use Stutt's directed matrix 3 theorem. So this follows from that. Now let me go to the second application. So this, some of it is not yet complete. We are working it out, but I can tell you a few things. So this is a Markov chain with the state space BQN. With all subspaces. So I want to define this Markov chain first. So before that, here is a definition. So given a subspace W in say a vector space V, by a complement we mean another subspace U such that V is equal to W direct sum U. So there will be more than one complement. Now it's easy to see if dimension of V is K, say V is FQN, and W is K dimensional, then it has Q raised to K into N minus K complements. That's an easy counting argument. So here is our Markov chain. Suppose you are at a subspace, you are at a state X, so some subspace X. So you choose some one-dimensional subspace P uniformly at random. Now, if this P is not contained in X, then the chain moves to span of X union P. If P is contained in X, then P will have a complement in X. There will be more than one complement. Choose one of them uniformly at random. Then the chain moves from X to Y. So if you imagine Q is equal to 1, then it is just the random walk on the hypercube, because choosing a one-dimensional subspace is like choosing an element. If it's not in the set X, you add it. If it is in the set X, the complement is unique, so you just delete it. So this is just the usual hypercube random walk when Q is 1. When Q is not 1, then you will have to, once it is inside, then you will have to choose a complement. Now, what's the transition matrix? It's not difficult to see. I'll skip this. That the transition matrix is precisely MQN over NQ. 1 over NQ, MQN, where MQN is the matrix we wrote down. And of course, this is a bipartite situation. So you can, to avoid parity problems, you can consider the lazy version of this. So you can take half of the identity plus 1 over NQN, MQN. So call it NQN. So it's a lazy version of this. And so we know all the eigenvalues of NQN because we know all the eigenvalues of MQN. It is quite easy to see that this NQN is reversible, essentially because the transition probabilities only depend on the dimensions. They don't actually do. Suppose you are a subspace of dimension X, then regardless of which one you are, the transition probabilities are the same, going out of X. And so that will essentially end up showing that it is reversible. Then you can get its stationary distribution using Q binomial theorem. Call it pi, then pi x is equal to q raised to k choose 2 divided by pqn, where pqn is this 1 plus product of 1 plus q to the k going from 0 to n minus 1. So the spectrum is easy to get since we know for MQ. So you can see the spectrum becomes, for the lazy version, 1 minus kq into 1 plus q raised to n minus k by 2nq, where k is between 0 and n, and multiplicity is nkq. Now, note an interesting fact. So look at the spectral gap, that is the gap between the top and the second largest. It turns out to be here, when k is 1, you put k is equal to 1. So you get 1 minus 1 plus q to the n minus 1 by 2nq. So the spectral gap is 1 minus of that. So it is 1 plus q to the n minus 1 by 2nq. Now when q is 1, this is essentially 1 by n, right? Because 2 by 2n is 1 by n. But when for general q, this is actually bigger than q minus 1 by 2q, because of this, what I just wrote down here, q minus 1 into 1 plus q to the n minus 1 by 2qn minus 1. So you can drop the 1 from the top and drop the 1 from below, because then you can, so it's greater than or equal to q minus 1 over 2q. So this shows that it's independent of n. So there is a large gap here. So that shows that, okay, so let me say something about mixing, but I'll not be able to define it. So since the gap is large, one expects that the mixing, okay, let's see. So let pi min denote the minimum value of the stationary distribution pi x over all x. Now, general theory for irreducible, reversible, lazy chain shows that the mixing time is less than or equal to log of 1 over epsilon times pi min into 1 over the spectral gap. Now, this gap is constant. It is independent of n. And pi min was, if you look at pi min, so you get, when x is 0, so you get 1 over pqn. So pqn will be q raised to some n choose 2, right? It's that will be a top term. So this will be 1 over that. So you will get q raised to n choose 2 log of that. So this will be order of n square. So if you fix epsilon, say epsilon is 1 by 4, then for the total variation distance to become less than epsilon, you require order of n square steps, because pi minimum is very small. Now, interestingly, if you look at q is equal to 1, then the gap was, I'll explain here, the gap was 1 over n. So 1 over that would be n here. And the there the stationary distribution is uniform. So it's 1 over 2 to the n. So there will be 2 to the n. So that will also be n square, but n coming from the first term and n coming from the second term. Here all the n square is coming from the first term because pi min is really small. Now in the q is equal to 1 case, you could show, though it's order n square the mixing time, one can show using upper bound lemma that actually mixing is order n log n. And in fact, you can make more precise statements. You can also show cutoff in the q is equal to 1 case. Now, so far in the q bigger than 1 case, we have been able to show that mixing time is order n. This gives the n square, but using the upper bound lemma, you can actually show it's order n. So to use upper bound lemma, you need the detailed knowledge of eigenvectors. So that means it's our second proof of the main theorem is needed, which I will not go into today. So let me just finish with some outline of the first proof, some main steps. So here we need the Kac matrix, which I have not defined so far. So the Kac matrix is a tridiagonal matrix, n cross 1 cross n cross 1, with zeros on the diagonal, 1, 2 to n minus 1 on the subdiagonal, and n minus 1, n minus 2 on the superdiagonal. The following, that this kn has it has n plus 1 eigenvalues, and they are n minus 2k. K goes from 0 to n. So these are the same eigenvalues as that for the n cube. And he also wrote down the eigenvectors explicitly. So you can see these references for an interesting bit of history on this problem. So all these papers work directly with the matrix Kn. So you can also give an easy proof using the bigger matrix, the adjacency matrix of the n cube, and restricting it to the invariant subspace of the radial vectors. That's a standard method of proving this. So now what we do is we have to define a Q analog of a Kac matrix. So this is our definition. So 0 on the, it's a tridiagonal matrix, n plus 1 cross n plus 1, 0 on the diagonal, 1q, 2q to nq on the subdiagonal. And on the superdiagonal, nq, q into n minus 1q, q square into n minus 2q, and q raised to n minus 1 into 1q. So, and then this, the direct proof given by Kac and others can be extended to get a proof of this. This theorem, that the eigenvalues of kqn are n minus kq minus kq. Now, another interesting sidelight is we have been unable to write down the eigenvectors explicitly for this matrix. For the bigger thing, we have been able to write down for the cube, for the mqn, but not for kqn. In particular, the proof by Kac has, it goes through to some extent, but the last few steps are not, it doesn't go through. So that's an interesting problem here, to write down explicitly the eigenvectors for this matrix. And then the last step is, once you have the eigenvalue of the Kac matrix, then you have to use a little bit of algebra. So you use the what is called the Q analog of the SL2C commutation relations. Then we can show that MQN is similar to a block diagonal matrix, where the blocks are Q to the K, KQ, n minus 2K. So this is the Kac matrix multiplied by Q to the K. And each such, for k between 0 and n by 2, and each such block appears nkq minus n choose k minus 1q times. So this requires a bit of work. So once you show that, then we know the eigenvalues of kq n minus 2k. So we also know for q to the k times z. And if you work it out, it'll so q raised to k into n minus 2k minus iq minus iq. So that is n minus iq minus iq. And then you sum over various k's, you will get back the eigenvalues you wanted. So that's the first proof, and the second proof involves writing eigenvectors. So that's more involved, and I will not be saying anything about that. Thank you.
Yeah, so is Murli present here?
Yeah, I'm here.
Yeah, okay. So are there any questions from the audience? Okay.
Even Subhajit is here.
Okay, okay.
You can ask Subhajit also.
Yeah, so are there any questions? Yeah, I just wanted to just related to, is there any analog of the recent sensitivity conjecture to this Q analog?
No, I have no idea. I haven't thought about it. Or rather, I don't see anything directly, but I have to understand the sensitivity thing first.
No, I mean, the problem can be easily stated. That means if you take a subgraph induced by so many, more than half the vertices, in the case of the hypercube, then the largest degree is bounded by some square root of n. That's the conjecture, sensitivity conjecture, which was recently proved by a very easy interlacing argument. So similar statement will be there for the Q analog, I'm sure. Whether it has application.
Actually, the problem is this graph is not regular, that CQN. So that's why we had to do this. The matrix is not just the 0 1 matrix. You have to put that Q raised to K. So some things are, they don't go through so easily simply because the Q analog of the cube is not regular. You'll have to change things. Instead of counting, you have to do a weighted counting and things like that. So I'll have to look at it. I cannot say.
Okay, because one thing that helps there is that the hypercube, the usual hypercube, the eigenvalues are very spread out, as you said. But when you can make a similarity and immediately bring them down to a narrow margin, narrow range. That was one of the, and you also have something related to similarity. So that step may have an analog. That's why I thought you can just look at the.
I'll look at. I've heard of this Huang's proof.
Right. Yeah. Easily.
I will have to look at it. Yeah.
Okay. Yeah.
Thank you. Yeah.
Any other?
ಹೇಗೆ ಹೌದಾ?
Okay, so if not, then let us thank Murli Srinivasan for a very interesting talk and conclude this session. Thank you very much.
Yeah, I'm just checking whether Professor Sane is there among the audience. Umashankar?
He has not joined yet.
He has not yet joined?
No, sir.
Raksha?
Sir, he has not joined.
You ask others to put off the mic. Lots of echo. Yeah, Professor Sane told me some time back that he'll be having a class and he'll be joining after the class. Probably he has not yet come out of the class or some problem is there. So we can wind it up. If anybody is having question, they can just write an email to him and get the clarification. Professor Papat.
Yeah, from my side, I think I'm done. So we can conclude this session and you can move on.
Right.
Yeah, thank you very much.
Raksha.
Thanks a lot, professors. Thank you, Professor Murli Srinivasan and Professor Sani for the lecture. And also I thank Professor Bapat for chairing this session. chair session for this one now, if Professor Sane has not joined.
Yeah, as I mentioned, he must be having some problem. Okay, please get Anish in. Yeah, he is trying to get connected through mobile.
Introduce next speaker. So in the next session, we have with us Professor Anish Sarkar from Indian Statistical Institute, Delhi. He is an associate professor in Stat Math Unit. His areas of interest are percolation theory, random graphs, extreme value theory, etc. Today he will be delivering a talk on Hack's law in a drainage network model, a Brownian web approach. And shall I play the video, sir? Sir, please unmute yourself.
He may join through mobile. He's having some problem.
Okay, sir. So we will start playing the video.
Yeah, he may join in any time. We can proceed with this recorded talk. And as Professor Sane is not available, maybe I'll take that responsibility now. Please.
Good morning, everyone. It's a pleasure to give a talk in this conference. The topic of my talk is actually based on joint work with Kumarjit Shah, who was my PhD student, and Rahul Roy, who was my supervisor. So three generations, and the the topic is on directed random networks, and a particular model that we want to discuss here. And it's a model which is fairly well studied in drainage network. It's called actually Howard's model, which we will come in a minute. And so we want in this talk to discuss about one empirical law which is studied in the morphology of river networks, drainage networks, and we want to place this in a rigorous mathematical framework and study, show that actually there is a mathematical model which shows a similar behavior as predicted by the Hack's law. So the Hack's law is an empirical law, and here we are going to sort of give some kind of theoretical justification. And the papers, as I have pointed out, there are three papers based on which this is given, which are this Analysis of Applied Probability in 2003, Analysis of the Institute of Ari Poinkar in 2016, and Analysis of Applied Probability in 2016. And there are other works which are involved, which these are works on which three of us have worked. Rahul Roy and myself, and with Srila Gangopadhyay in 2003, Kumarjit Shah, Rahul Roy, and myself in these last two papers. Okay, so let's start with this. So main model that we are going to study is based on something called river networks, and it's a physical thing, and it's studied in the drainage, and there are a lot of geological studies based on this. Geomorphology, it is called the geomorphology. So as you can see, we have given a physical literature. So essentially, it's a spanning tree in a defined in a lattice of arbitrary size and shape. That is the sort of description for a river basin network. And it's quite well studied model. And as you see that it started initiated in 1945 by Horton. These are all physical literature, or in the physics literature, not in mathematics. So Horton, and this there are list of, and there are many empirical laws that have been studied. And then Scheidegger proposed a model, sort of first mathematical model in 1967. And there are heuristics why this should happen. And I will quickly describe the Scheidegger model in a minute. Okay, so let's now sort of there are many models which have been proposed, and if you want to find in the geological literature, it would be Rodriguez and Rinaldo. That's the fractal river basin. This is a very nice book, though it's written from the physics point of view. But there are very nice models. And a lot of mathematical problems are there, which one can formulate and study. Most of these models are just some kind of network which is given by this network of. I mean, they're proposing river basin, how these things, the water flows, etc., etc., many other things, and then geometry of a river network, and it's a PhD thesis of MIT. And we will not go into this. We'll just take the models and we will study them. Okay. So let me quickly describe the mathematical version of the Scheidegger model. So the Scheidegger model is studied on the infinite oriented lattice. Okay, oriented lattice, it is so essentially the lattice that you could say two-dimensional lattice, which is often denoted by Z2 even. So that is Z2 even, two-dimensional lattice, and it is just a orientation. So you just orient this two-dimensional usual lattice in the 45-degree angle. Okay, and to describe this is, you can say M and N, this pair of vertices, so that M plus N is even. M plus N is even. So for example, if this is the origin, and then so essentially it is defined so that there is a direction you can impose on this. So you can think of this is the think of that this is the XY axis is kind of this. So this is 0, 0. So they and then so essentially you can, and then the XY axis has from here, it has come here. So that's the kind of intuition that you should have. And the since we are studying river networks, there should be a gravity. And in general, so that is the sort of direction that we will impose. Okay. So what is the model? The model is very simple, and a probabilistic model. Of course, everything has to be probabilistic model. So what is the model? And each vertex, you choose either the left edge or the right edge in the upward direction. So let's go back and say, for example, each vertex, either you choose this one. Oops, page up. This vertex or this vertex with probability half. Okay, and you do it from every vertex independently of others. So essentially, you have some from everywhere. Either you choose the left edge or the right edge. Okay, and you put these edges on this network, and this gives you a graph. That's all essentially, and that is the sort of graph we can we want to study. So for example, now let's another thing that we have to talk about is that what happens. So for example, you think of, say, this edge, and there may be this vertex may have chosen this edge, and this vertex may have chosen this edge. So what happens to these two edges when they come together? They will go together. So from here, this vertex will choose one of these two, and both of this direction will go here. So this is what is essentially meaning that two streams or rivers essentially come and meet and they join together. Okay, and they go as one. So that is the kind of understanding that you should have. So let's just quickly show a figure. So for example, from this point and this point, so somehow I have taken the gravity upwards, but it's sort of so from this point and this point, and you go here and you join here. By the way, I have not drawn other points. So for example, from here also, either you may have taken this edge or this edge. Maybe you have taken that edge, and then from this edge and from here, or maybe this edge and this edge, and etc. So whenever you see this, we have drawn just from 2 points, the sort of or 3 points, the how does the graph look like? But this would be drawn from every vertex of this. And this is a finite part, and we will take actually the infinite lattice Z2 even, and we will put down these directions, and that would give you a directed. So because the paths are going upwards, a directed graph. Okay. So few things that we quickly talk about this. So this is what is Scheidegger model, and few things very quickly we can talk about. So this is essentially what is called a Scheidegger river. So essentially this is a river, this is a river, they join and they go together, and here there is a river which is going, and then this river joins here and they go together, and so on. These two rivers joining and they go together, etc. Okay. Now, so the model that we want to talk about is so this is a model where so I go back to here. This is a model where you think that sort of every vertex is a source of water. Okay, which is the case if you think of the plain land. This is a kind of plain land with a little bit of slope. That is the case, but this is not the case. This is not the case when you think of where there are a lot of the high gradient movement. So this is what is called the Howard's model of headward growth. So how do you define this model? So this model you take just d-dimensional lattice. So here we have drawn everything in 2 dimensions. So everything I will talk about in 2 dimensions. And you think, okay, not all points are points of source, or not all points or all vertices are not a source of water. Okay, so there are only few vertices which are source of water. So from that vertices, you can sort of originate a stream. You cannot originate a stream from any vertex. So for example, here these green points which are, so how do you choose the sort of some with some probability p? This would become actually there's no, as long as p is between 0 and 1, the qualitative picture there is no difference. So therefore any p between 0 and 1 is good enough. So you take with some probability p, you toss a coin for every vertex, independent tosses. So say for example, this is success, you declare this is a source of water, this is success, this is a source of water, others are failures, so these are not source of water. And you do it for every vertex, and you get a sort of the vertices which are source of water. Okay, and the next you will define the network. So how do you go to define the network? Is that every vertex will choose from every vertex. Now by vertex I mean every open vertex. So is there called open or source of water or whatever. So green vertex. Every green vertex will choose another vertex which is in the next level. So think of the gravity growing this in gravity in this way increasing. So the slope is in this direction. So from here it will go to the next. So this is higher in gradient. So therefore it will go from here to the next level of gradient, which is here. And then from here we will go to the next level. From here we will go to the next level. And this will choose in a particular way from where I should go to where, from which point I should go. So not all channels here are open. So there are only channels which can go from a source of water to another source of water. So for example, so how is this done? So for example, what it will do is that from any vertex, it will look at the vertex which is exactly above it in this picture. So, and you see if this is that's a source of water, or that's open vertex, green vertex, you will connect to it. So for example, here I will see that. If not, then I will choose see the next pair of vertex. So this is closed, then I choose see the next pair of vertex. If there is one open, we will connect to that. If there are both of them open, so that is I have a choice, I can connect to here or I can connect to here. So for example, that's a situation like here. So for example, this one is closed, and here I have two vertices next to the next level. So it has a choice, either it can connect to this one or to this one. Now you can define a rule. For example, the simplest rule would be you choose randomly with one of these two. So we toss another coin with probability half. You choose, if head, I connect to the right. If tail, I connect to the left. And we keep on doing this. So for example, from here, so I see if the first level, there's no, in the second, and there is not first level. First, in the next level, the immediate point is not connected. The points which are at distance 1, they are not also open. Okay, but in the points which are not in the distance 2, both of them are open. And this point, this vertex has again a choice, and again it tosses a coin. And this time, for example, it chooses to connect to the right one. Here, for example, it chose to connect to the left one. So this will connect like this. And what's this sort of thing is that there, in this case, what can happen? Many points can come and join together. Okay, so confluence can happen of more than two rivers can come at a point. So, for example, so I am not here. I have not. So, if, for example, this was not there, this point, so think of that this vertex was not there, and so this and this was, then this had a choice of connecting to this one and maybe this one, and it chose to the left. So there would have been 3 things coming at this vertex, and that could have happened. Okay, and this is called the Howard's model, and we were going to study a thing about this. So we were going to study a few things about this. Okay, so what is that we can say? So, for example, it is now. Let's go back to the. In fact, let's go back to this previous picture itself. So, from every point, I have exactly one edge going up. So. This is infinite in this direction. In this upward y direction, this graph is infinite, and this cannot have a loop. In order to have a loop, there must be from some point. It has to have 2 edges going up. So every component of this graph must be a infinite tree. So those are things that we know. Okay, so for so I have said these 2 models. It would have been 2 models. So there actually I described another model which I erased, and I forgot to change this. So there's 2 models, that so Scheidegger model as well as this Howard's model. What we can show, for example, d equal to 2 and d equal to 3, the graphs that we, so if you sort of go back and look at this graph, infinite graph, on this vertex set of open edges, or in the Scheidegger case, in this sort of all infinite vertex set, you look at this the graph that is formed. So in that, so when d equal to 2 or d equal to 3, there is exactly one tree. So this, remember that each component is a tree. So what we are saying essentially that all components must sort of meet, and that happens with probability 1. Okay, so this is a strong statement, essentially saying about the geometry of this network. So there are only one infinite directed random tree in direction 2 and 3, and direct dimension 4, you will have infinitely many disjoint trees. Here I must say one thing. So you may be wondering how I can define sort of, I've described this 2-dimensional picture, how we can take the 3-dimensional picture. So 3-dimension, essentially we should think of this 2-dimension as 1 plus 1 dimension. 1 dimension, this dimension here to the y direction here, is taken essentially as the time, you can think of as a gradient coordinate. Okay, and in 2-dimension also, what you will do, xy coordinates you will take as the sort of position, and the z coordinate as the gradient coordinate. So that is the thing. So you will move in the z direction. Always you will move in the z direction, z to z plus 1, to z plus 2, z plus 3, and so on. And so essentially what we can define these pictures in any dimension. So that is the thing that I just want to say. So there in dimension 2 and dimension 3, there is exactly one tree, and dimension 4 onwards, there are infinitely many disjoint trees. So this network is indeed a forest with infinitely many directed trees. And there is another thing which is a very interesting question that we can ask. Oops. Okay, so we see that, okay, I have a sort of infinite tree going in this direction, in the upward of y direction. So if I look at, okay, sort of all things that would coming to here, if I follow each of them, so for example, this one, I know this starts here. This one maybe starts here and stops here after that, and this again here and stops here, etc. So, but it may be possible that some other thing has that it is going up to the negative direction of y infinity. Okay, is it possible? The answer is no. So there is no y infinite tree almost surely with probability 1 for any dimensions. So if we look up, so if we think of this, so this is what it is sort of generally the question that are asked. It is sort of you think of all this rainfall are happening here. Okay, so what the amount, so each of these things have to drain certain water, and all these things drain water is drained through this. So is it a finite amount of drainage in this? So in other words, this number of vertices which contribute to this, so which are essentially, so we can think of these are previous generation, these are another generation up, these are 2 generations up, these are so 1, 2, 3, 4, 5. So if you look at the union of all such generations which are ancestors of these birds, union of all ancestors, is it a finite or not? If it is finite, then this water is finite. So essentially the Hackett's law is about the amount of water that is passed through this, which is proportional, which is of course here it would be number of vertices. You can think of every vertex as it contributes unit to amount of water, so number of vertices, and versus the length of this. How far? So I know that it is finite. How far does it go? So essentially, how far does it go with the number of vertices? So that is the kind of relation, and they have a relation. So which I'll show one or two pictures, and we'll talk about it in a minute. Okay. So there are no bi-infinite trees, and there are infinite. Only one tree in 2 dimension and 3 dimension, and dimension 4 onwards there are infinitely many trees. So we only so a quick word about the proof. So if you look at the so let us go back to this Scheidegger model. So Scheidegger models, let's say I start the model from here, start the river from here. So I move here to or here. So if you think of this is the time direction, and then this is going up by 1 with probability half, or going down by 1 with probability half. And then from here again you do independently. So if I have moved from to here, and I will again move up one by 1 with half probability, and move down by 1 with half probability. So this is, think of this as the time. Okay, so this is at this position +1 at the next time point, this position -1 and then here, and the position +1. So this essentially is nothing but what is called a random walk in probability. And the interesting thing to note, that if I look at this random walk, so I start from here and I start from another random walk from here, until they meet, they actually, so if I think of this random walk, this uses the coin toss of this, and this one uses coin toss of this, and then the coin toss of this one, up to this one, right? All these things. Okay. And this random walk uses this one. So these are disjoint set of coin tosses that they are using, and the coin tosses are independent. So therefore, these 2 random walks are independent. So 2 random walks, if they are independent, they will, in 2 dimensions, they will meet with probability 1. So this the proof is done essentially, and the rest of the thing is dressing up, nothing more than that. In 3 dimension also the same thing happens. Okay, Scheidegger model is very simple. It is just sort of a collection of independent random walks. If you think of 2 things starting at the same level, so independent random walks until they meet, and when they meet, they coalesce and they go together. So you can from here you can say many things about the Scheidegger model. Most of the things that we are going to say, not most of the things, some of the things that we are going to say about the Scheidegger model. So we talked about the Scheidegger model, and as we said, random walk in 1 dimension. Essentially, this is property of random walk in 1 dimension and 2 dimension are recurrent, and hence 2 random walks, distinct random walks, will meet with probability 1, and 3 or more dimensions, they are transient. Hence, with positive probability, they will not meet. We have countably many such random walks who are starting, so therefore you will have infinitely many of them which will not meet. So essentially, that is the proof for Scheidegger model. For the Howard's model, it's much more difficult. So I will just quickly say we will not prove anything. So if you look at, for example, 2 rivers which are starting from a given distance, let's call their distances Z0, Z1, Z2, Z3, Z4, etc. So essentially, so the distance, if they meet, the distance becomes 0. So the distance, what we can show that this distance actually is a non-negative martingale, and with it is also a Markov chain, and it's a 0 as the absorbing state. So martingale convergence theorem will say that this will converge, and since it's the Markov chain, 0 is the absorbing state, therefore it would mean that Zn will become 0 with probability 1. So this requires a little bit of martingale and Markov chain argument. This not very difficult. The argument is to show that this is essentially a martingale. which you have to write down the expectation, etc. And it's not such a difficult task. For 3-dimension, it's a much more involved thing. We have to sort of, again, the Markov property is there, because whatever is happening a dimension up, which it depends on a coin tosses on the next level. So these are independent coin tosses. So Markov property will be there. The main thing that you have to show that essentially 0, 0, 0 is absorbed. So you just take the XY positions, forget the time. So that is encoded in the Zn will have a so essentially, if you think of the time as XYN, and then you take Zn to be XY, essentially that is the kind of thing that we are talking about. And so two rivers are let's say x1, y1, and n, and x2, y2, and n at time at the nth level, and you take the difference, and that is a Markov chain Zn. Okay, so essentially you want to show that if they meet, they will become a they will join. So if they meet with probability 1. So so you just again, Markov chain is there. You just modify this Markov chain with probability 1, so that it becomes an absorbing state. From absorbing state, you make it a just a standard recurrent state, and you have to use a Lyapunov method. So you have to define a Lyapunov function, and so essentially what is known as the Foster's criteria. And coming up with this criteria is not coming up this function is not such a straightforward thing, and it involves a lot of calculations. So we will not go into the details of any of these things. And the higher dimensional thing, essentially the things we have to show that when you can use a coupling method and show that if they are sufficiently far away in d dimension, so that is set d equal to 4, so that is 3-dimensional random walk, with positive probability they will go away. They will be even farther and farther distant, and you can modify, you can sort of do this inductively, so that with positive probability such a thing will keep on happening. And this induction kind of thing would say that with a positive probability, the two rivers, they are sufficiently far away, they will not meet with positive probability. And therefore now after that, the same argument, since there are infinitely many positions you are starting, there would be infinitely many distinct trees which do not meet each other. Again, these are very technical, and I will not go into details of this. Now, coming to the main thing that we have to talk about is something called Hack's law. So essentially, as I said, they studied this Hack's law as a drainage system, and various parts of Virginia and etc. And they observed something called the Powell law relation, which is the length of the river. So length of the river is sort of, as I have spoken, is looked at from the, I will show some pictures immediately. And with the area, it sort of drains to the power 0.6. Okay, that these two are such a relation holds. And they have various river networks. They have computed, and they have sort of, these are physical, they have just collected data and checked, and this has come between in 0.54 to 0.7. And here, so Mandelbrot also mentions his sort of the Hack's laws to strengthen this kind of reverse length to the power 1 by d, etc. So there are many other things which are related. For example, there is something called a Hurst exponent of fractional Brownian motion, and this essentially looks at so remember that the Mandelbrot came to this fractal things from the study of Nile River Basin, and the Nile River Basin where he proposed that L is a perpendicular width of the river, and L is the L perpendicular is the length. Okay, length of the smallest rectangular region. So I will show a picture in this. So this is the kind of thing that we were talking about. This is the L, and this is the L perpendicular, and this is a picture of a Fela river basin. So essentially, this is the amount of this is a kind of all vortices which drain through this point. So you want to talk about this length, so length of this versus this area, or which is essentially you take as the number of vertices. So what is the kind of proportional thing that, is there a proportional thing that we can come up with? And indeed this model, though it is a very simple model, describes a similar thing that let me just say. So let us formulate this in terms of the Hack's law mathematically, what we want to say. So let's say I have a vertex xt through which I want to see. And as I have said, so this side, this is infinite. The amount of water which comes through this is a finite, because this is not bidirectionally infinite. So this is a finite part. So number of total number of vertices that we can see here is essentially the nxt, or this is exactly. So if I go up to this, this is the area that we can think of, the area that drains through this point. Okay, so nxt, the total number of points, is the role of the area, and the height, where after which it ends, this river ends in this direction, the maximum distance after which it does not have any ancestor. So that is called the length, lxt. So lxt is the height, and the nxt is the number of vertices. So what we want to talk about is there a relation between these two probabilistically? Okay, and Hack's law essentially says something like this: lxt is proportional to nxt to the power h, where h is called the Hack exponent. Okay, now what we prove in this, the proofs are, the argument is very technical, but we want to say mathematically. So if you see the length and any vertex, these are translation invariant. So think of 0 0 as your so xt as 0 0. So take L00 and N00 to the power 1/3, and if you scale this by n, of course this this belongs to a Borel set in 0 infinity cross 0 infinity, and from there you have to remove the 0.00. This is for technical reasons, because at 0 0 you may have this measure may not be finite. Okay, so essentially you are saying that if the length and the number of vertices, so length is proportional, scaled, length is as it is, and the number of vertices is scaled to the power 2/3 instead. So what is the number that we are suggesting? So going page up, this h, we are suggesting that this should be 2/3. If you scale this, then when you scale this as n, and this probability belongs to a large set nb. So this belongs to nb, and then that probability you have to scale it to go to a proper limit, and that converges to a non-trivial thing. And this is the only value. This is the only value. 2/3 is the only value for which you get a non-trivial limit. Otherwise, you will get a trivial limit. So, for example, if you take any alpha, which is so alpha is, if alpha is less than 2/3, this probability will go to 0. Alpha is greater than 2/3, this probability will go to a one-dimensional constant. So you see that this has only tau. Okay, there is no lambda. Okay, So it becomes a one-dimensional thing. So it's a flat. It's a it's a two-dimensional probability, but it becomes one-dimensional. That is the relation of this the contribution of this goes away. So only thing that the scaling which makes sense in this is when h equal to 2/3. So therefore, essentially, this is what we are saying, that there is actually a scaling. The scaling and so we have described, say, mu b, and the mu b has an expression which is mu b is given by a density function under Brownian excursion. This is a complicated expression. We will not go into this, and this is a constant depending on p. And this happens for any p. So that's why I said p is not very important. So just going back to this, so L00 and n to the n00 to the power 2/3, this together will go to a non-trivial limit. Otherwise, it will not go to a non-trivial limit. So this is what you would expect. That so therefore we would want to say that this h is actually 2/3, which is 0.67. So it is all in this. If you look at the figures that they have computed, 0.54 to 0.67. So even though this model is such a simple model, this corroborates a lot of the physical description. Okay, and let me not go into this Brownian meander and Brownian excursion. This will become much more technical. Let me just go into the idea of this proof. And the idea of the proof is that you go to a limiting distribution to compute this. Okay. So essentially, something which we are going to call a Brownian wave. And Brownian wave intuitively is a collection of one-dimensional coalescing Brownian motions, which are starting from every point xt in the space-time plane of RT. Now, every point xt, so there are essentially uncountable number of coalescing points. So uncountable number of coalescing Brownian motions. So there are a lot of technical difficulties. So there are many ways people have started, and if finally this Fontes, so Aratia and Toth and Warner, even actually Varadan had a model for similar models, and so those we are talking about this. But the approach that we're going to use is given by Fontes, Isopi, Newman, Ravi Shankar, and later Sun and Swarth, Romfeng Sun and Jan Swarth. So we are using this approach, and then Beristeki and Garba and Sen, they had also given another way of studying this, and probably we can also follow that. But this is the most standard way of studying. Now it has become more standard way of studying the Brownian wave. Okay, so essentially what you were going to say that you start from diffusive scaling of coalescing random walks starting from every vertex of the space-time plane lattice Z2. And what is that space-time lattice Z2? This is, I should not say Z2, this should be saying Z2 even. And what is that? It is exactly the this Scheidegger model. So they start with this model, and so in a certain sense you can define paths, and this converges in a, so there is a non-trivial way of defining a limit. So so as more formally, so essentially you think of Brownian wave as a random variable which takes values in the space of compact sets of paths. So the random variables are essentially a compact set of path, and this compact set, this sort of set is actually a Polish space when you give it a suitable topology. Okay, so once it's a Polish space, and then you can use the standard theory of weak convergence to prove various things. So for example, we were using that notion, then we can show the one-dimensional coalescing systems, various one-dimensional coalescing systems converge to the Brownian web. And so there are two things that we want to say here, both. So, okay, so let's not get into this compactification of paths, etc. Essentially, this is how you identify paths. So, so let's not get into this. Okay. So the theorem that Fontes and Isopi, etc., proved is that there exists a unique random variable called, which is they call the Brownian web, on a suitable space. So the space, for defining the space, you have to do all this work that which I skipped all this work that you have to do, a suitable space, and where you will have this, that for every deterministic z, there's a unique path pi z. Okay, and you take, so now you take a finite set of deterministic points z1, z2, zk. For every z, there is a deterministic point, and there are finite, almost surely the finite collection. So this with probability 1 from each I have a Brownian, which each I have a path. So pi z1, pi z2, pi zk, there are paths, and this are distributed as coalescing Brownian motions, as it in the sense that when they each of them perform Brownian motion, and when they meet, they coalesce. So go together. Okay, and if I take any any bounded set of Z1 not bounded set, any deterministic countable dense set D. So for example, for rationals, and you start from the Brownian the paths from there, and you take the closure in the space. Okay, so that's this is identifying property of the Brownian web. So that is the Brownian web. So there are many nice properties of this theorem, of this setup that Fontes etc. proved. So this is in 2004 Annals of Probability. Okay, so in some sense, this is sort of, even though there are essentially, this is saying that essentially there are uncountably many Brownian motions, but still it is determined by a sort of skeletal set of countable Brownian motions you can start. Okay, so that's the kind of argument that is given by this paper. Okay, now the approach that we have taken is that we want to study this river network. So one thing that we will have to show that Brownian this path set up. So if you look at this collection, now you can think of this as a paths in the path space. So with a little bit of effort, this is not very difficult. You can make it a member of this particular path space that we had just sort of quickly brushed under the carpet, and we can make it in the member of this. So these things, it makes sense to talk about the river networks in that in the Brownian web path. But that is not enough. What we need is another set of paths going in the reverse direction, and that is what we are going to call is a dual Brownian web. Okay, so there is a another set of path which goes in the and this has been also studied by Brownian web. So there's a community study, we have huge community now studying this Brownian web, and in this case, what we are going to say is essentially this. So look at this as this. For example, this is the one path in the direct direction. So I just want to say how you define this Brownian web. So I look at, for example, between these two open points. So these are previously green. Now we have drawn it red. And in the middle, I put a point of the dual. Okay, and then I look at the next where it came from. For example, it came from here. And it came from here. Between these two also I put a nearest another point of the dual, and we connect it like this. So for example, this I had connected, and this so between this I have put another point, between these two I have put another point, between these two I have put another point, and this. So every pair of them I have put a blue point, which is the points of the dual. And if this is going in the upward direction, the dual points will come in the downward direction. And now to observe this, so let us observe this. So for example, I look at this point. Which all vertices drain through this? So this is exactly the set of vertices, this, and this one, right? All these vertices which drain through this. So in order to study this, essentially what we will see that this is given by the if I look at the dual from this two from the left of this vertex and the right of this vertex, where they meet, all the vertices in between, all the open vertices in between, they will drain through this. Okay, so dual is taken by this. And what we have proved essentially, so the dual graph ensures, so this is what exactly again we were saying. So dual graph ensures that the dual also again does not intersect any direct path, and it does not have a circuit. And whenever a cluster, so this is what we call a cluster of this vertex, all the vertex which come here, the cluster finishes the dual, the left dual and the right, left dual path and the right dual path. So exactly this one and this one, they will meet. Okay, so that's what it is saying in the dual definition of dual. And okay, and what we can show here, for example, that this dual paths is also a Markov chain, and it's a martingale, and a lot of properties that we can show. And after we proved this, actually Sun and another Ramphingson and another I'm forgetting his name now, they came up with sort of a more generic kind of thing, that this way of defining, our way of defining a dual works for almost every set of non-crossing paths. Okay, so in that case also, if you take the dual, this will work the way that we have described. Okay, and so we consider the piecewise linear paths that we have defined. And so far, which is just saying that you connect. So think of this path as a piecewise, where it has gone, just connect them, and then now you define as a function of t. Okay, the t is going this way or this way, whatever way you want to think. Okay, so you define the piecewise linear path, and you scale this by as we know the first direction, the x direction. So here, page up. In the x direction, this is the space and this is the time. So we need to converge to a Brownian, so you need a diffusive scaling. So Brownian diffusive scaling, the time should be scaled by n, and the space should be scaled by root n. Okay, so that is what you have done. The space is scaled by sigma root n. Sigma is a variance part, and the time part would be scaled by root n. And this is what is the scaled path. And what we are able to show is an appropriate topology, which we have brushed under this carpet, that if you look at this direct path as well as the dual path, this will converge to the Brownian wave and its dual. Okay, so therefore, so now we'll come to what we have been saying, what I have just described. So you think of so if you look at, I want to look at this xt, and the lxt is this height, and you look at the Brownian motion, that is one Brownian motion from here, and so in the limit, these are all going to be Brownian motion, and this is another Brownian motion. You take the difference of this, So these are two independent Brownian motions. So difference is also another Brownian motion, and this is the Brownian motion. And between, so essentially, when I scale, these two will become. This is distance, a finite distance. So when I scale by n, this will come to the same point. So essentially, you start from 0, and after a random time, you again hit 0, and that is exactly what is known as the. So there, the difference of the flanking Brownian motion is what causes a Brownian excursion, and these two paths that which enclose this CXT. So what we are finally, so if I go up there, so if you look at this number of vertices here, which is proportional, so essentially that's how many vertices are there. If you you can add them, that is the area. And you look at the number of vertices, that is p times essentially how many open points, so which is p times this for large enough n, or large enough n, this would be proportional to open with open probability. And so therefore this results in the excursion of the Brownian motion area under that, and p fraction of them will contribute to the contribute to the number of vertices here. And L is the length of the Brownian, then will be the time when it hits 0. So that's how you formulate this, both the problems together, and bring it to a Brownian motion. And so essentially, this is what it is saying. These paths will enclose the cluster. So the distribution of the area will become the area, which is, this is the expectation of W0T. W0T is the Brownian excursion, and this is plus is going up. So area under the Brownian excursion, and this is scaled. So what we want to do is to sort of think of this as 1, and then what is the how does this follow, and that from the Brownian motion and excursion properties, this comes out to be 2/3. Okay, so I will stop here, and thank you very much for your attention.
Thank you, Anish. Anish, are you in a position to come on the screen? Yeah, Anish. Yeah, thank you. Anish, thanks a lot for coming and delivering this talk. You have taken lots of pain in preparing these slides and recording this talk and communicating.
Unmute.
Before leaving, I'll just explore if there is any question from our set of audience. Raksha, explore if there is any question from audience over there. Anything from virtual audience, please? You can raise your hand and.
Participants, any questions? I think we don't have any questions.
Probably everyone is looking at gate. Time for lunch. Okay. Shivkumar, you had any? I saw you coming up.
Yeah. No, nothing specific. I just wanted to see what's going on. Nothing specific.
Okay, you are welcome.
Yeah.
So if there is any, there is no specific question, then while winding it up, and we thank Anish again for taking all this trouble and joining us. Okay, Anish, be with us, particularly on last day, that is on 17th, for the last session.
Unmute
You are
yourself.
muted.
Yeah.
You are muted, Anish.
Okay. Okay. Thank you. I will be there in last session.
Yeah, please make sure. Okay then, bye.
Thank you, Professor Anish Sarkar, for delivering a talk, and thank you, Professor Prasad, for chairing the session. Now let us have a lunch break. Afternoon session will start exactly at 2 o'clock.
Good afternoon, Arup.
Yeah, just a minute. Let me get my headphone. Can you hear me?
Good afternoon.
Can you hear me?
Can you hear me?
Yeah, I can hear you. Can you hear me?
Can you hear me?
Yes.
No. Oh, sorry.
Yeah.
My speaker is not ready.
Okay. I can hear you. Can you hear me? Can you hear?
Yeah, now I can hear you.
Okay. Good. Yeah. Okay. I was getting anxious.
Earlier, I thought I am not reachable.
So shall I share my screen? Because sometimes that...
Wait. Who is the chairperson? They will initiate.
Okay.
Let me check.
Professor,
Still 3-4 minutes are there.
Yeah. I just wanted to check everything is okay. Yeah.
Simo is the chairperson.
Yes,
Let me
I know
see
him.
whether he is there around.
Yeah. Okay.
Yeah, Simo is here.
Yes, I am ready.
Yes.
Yes. Thank you.
I can relax.
Should I say good morning or good afternoon?
Good morning, very morning.
Still morning. Yeah.
Yes.
hello.
Raksha, you want to say something? Are you coming in?
I was testing. Raksha?
So, I'll come back in 1 minute.
No problem. I'm just.
We'll start exactly at 2.
Yeah, speak something. Yeah. But you're not audible, Raksha. Some problem?
Hello. Hello. Can you hear me, sir?
With break.
Hello.
Yeah. Now I can hear you.
So, are we going to start now, sir?
No, when time is up, you can. Professor Arup is away for a minute. The moment he comes, we can start.
Okay, sir.
Yes.
Raksha, please.
Yes. So welcome back, everyone, to the afternoon session.
Yes. Should I share my screen?
Hello.
Yes.
Sorry, sir. There was some issue here.
Oh, okay. Can you hear me now?
Yes, we can hear you, sir.
Okay.
But
should I go ahead and share my screen?
let me just give a short introduction.
Sure.
So, this session we have with us Professor Anand, Indian Statistical Institute, Kolkata. He has been associated in Academy of Sciences, Statistical Methodology, Indian Journal of Pure and Applied Mathematics, and many more. He was an elected member of International Statistical Institute, Bernoulli Society Council member. He has got SS Bhatnagar Award in the Mathematical Science, India's Government of India, the most well-known yearly scientific honor for Indian scientists below 45 years. His areas of interest are information economics, moral hazard problems and incentives, large dimensional time series, resampling in time series, asymptotes of autocovariance matrices, etc. Today he will be delivering a lecture on special measures of empirical autocovariance matrices of high-dimensional stationary processes. Welcome you, sir. To chair the session, I request Professor Simo Puntanen to take over.
Thank you. I will simply say that the screen is yours, Professor Bose.
Thank you, Simo. Thank you,
And you
Simo.
may share it even.
Yes, good to see you again. Yeah.
Okay, yes.
Yeah. So let me share. Yeah.
Okay.
Window. No, something is wrong here. So let me try again. Yes. Okay, success. Let me see. I need to enlarge this. All right. Can you see the screen now, Simo? Hello.
Yes, it's okay.
Okay, very good.
Fine.
Yeah. Okay. Thanks. So thank you, Simo, and the other lady who introduced me.
Screen is not.
No, not okay. Is it okay now?
Yes, we can
She
see
is
you.
Raksha.
Hello.
Yeah, screen is not visible. It's
Not
blank.
visible.
It's visible, sir.
Yeah, Manju, I think there is some problem at in your laptop or in your display. Others can see it. Simo, can you see
Yes,
it?
Maybe.
yes, we can see it. Yes.
Okay. Okay. All right. So let me go ahead, and I think Manju's screen will take care of itself very soon. All right. So I'm going to talk about spectral measures of empirical autocovariance matrices. So this is something that I've been doing for more than 5 years, in addition to other things. And there are a lot of problems, interesting problems in this area, and we have solved some, and others are there waiting to be
So
solved.
can you zoom out a little bit, because
Zoom out. It's too big.
not fully visible.
Is it now?
The sides are cut off a little bit.
Okay. Is it okay now?
Yeah, now it is perfect, sir. Yes.
Okay, very good. Okay. Without much ado, let me begin. So what is a random matrix? Before that, I think, yes. Okay, all right. A matrix, all whose entries are random variables. So that is, the entries are drawn according to some given probability measures. Even though often you assume additional structures in the entries, we'll see some of them in this talk. The study of random matrices has become important in mathematics, for example, operator theory, non-commutative probability, also in statistics, for example, inference for high-dimensional data, on which I'm going to spend some time today, particle physics, and wireless communications. One of my friends tells me from wireless communications how the development of the 5G a crucial ingredient in that was high-dimensional random matrices, because you basically have several antennas as transmitters and receivers. So that is an ideal setup for random matrices results to be used. I don't know much any further details, but he tells me that it's very crucial. And this has become so important that there is a new journal since 2012 called Random Matrices Theory and Applications, which publishes all kinds of research in random matrices or areas connected to that. So here is an outline of my talk. I'll first briefly mention some historically important random matrices and results. And some of you have, or many of you might have seen some of these slides before. I apologize for being repetitive there. And some of you might have also seen the main topic, maybe some different kinds of results, but similar. So the second item on my agenda is high dimensional time series and sequences of sample autocovariance matrices. In particular, I'll talk about what is called the bulk of symmetrized sample autocovariance matrices, because as we know from studying these matrices that if you have symmetric matrices, then things are relatively easier. The results and problems for matrices in general, which are not symmetric or non-Hermitian, are always much more difficult. Because as you know, if you perturb a non-Hermitian matrix, the corresponding perturbation in the eigenvalues, it's not like a nice smooth function. So that makes it harder to study non-Hermitian matrices. But I have one or two results that I'll mention for in general for sample autocovariance matrices, which are not necessarily symmetric or Hermitian. So let me begin with some very basic examples, and I assume that there will be some students in this in the audience, so especially for their benefit. Of course, many of these examples would be very well known to experts or people who work in matrices or random matrices. So the earliest example that you could think of random matrix is a 2x2 contingency table. For example, yes or no counts of having cancer versus being a smoker or not. And you can of course have more options for the two traits. Okay. Second example is what is commonly known as the data matrix. So if you have p-dimensional vector observations, and if you have n such samples, and you arrange them these observations n times p observations in a form of matrix, then that is usually called a random matrix. And of course you assume for the structure on the columns, so the columns might be assumed to be independent, and within the columns there might be some covariant structure and so on. But in general, this is called a data matrix. Manju, I think your speaker is on, so can you please switch off your microphone? So usually P is fixed, and the number of observations n is allowed to grow. And in high dimensional statistics, the dimension P of the observations is also assumed to be large. So to get a theoretical framework, you assume that P goes to infinity as well as n goes to infinity. And quite often you assume some relative growth of this n and p. Sometimes you assume that p does go to infinity, but at a much smaller rate. Sometimes you assume that they have the same rate, and so on. Example 3, this is a very familiar example, which almost every student in statistics, of course, would know, that in multivariate statistical analysis, the unadjusted p by p sample covariance matrix is very important. So if you have the data matrix X and you take X star, so star will always denote the transpose or the conjugate transpose if the entries have complex numbers or complex variables. So when the entries are Gaussian, for example, S is called a Wishart matrix. And way back in 1928, this was defined by Wishart and its properties were studied. But due to whatever reasons, statisticians or probabilists have not worked in random matrices for a long time. And on the other hand, the physicists were working quite a bit in different kinds of random matrix. And they had come to these random matrices from the nuclear physics or particle physics point of view. Anyway, I think now the statisticians have again tuned in, and they are working in high dimensional data. And they are using these random matrix results or using them for applications. So in any case, S is called a Wishart matrix, and then the joint density of the eigenvalues can be calculated and used for statistical inference. Now, when P is fixed and n is large, of course, certain limit theorem arguments are available and can be used to study the large sample properties of S, including the asymptotic normality of its eigenvalues. On the other hand, when P is also large, this behavior is very different. So there are, of course, as I mentioned, there are different scenarios of P by n can be converging to a constant, and that constant could be 0 or non-zero, and so on. But generally speaking, the behavior of its eigenvalues is very different. For example, the Marchenko-Pastur law for the bulk of the eigenvalues, or the Tracy-Widom law for the extreme eigenvalues of sample covariance matrices there. So these are very different kinds of results compared to the central limit results available when the dimension P is fixed. So some other random matrices, some of them I'll show you some simulations. Of course, I'll not mention any results there because our main focus is autocovariance matrices, and so I'll go to that. But before that, I just want to give some brief simulations and some brief definitions of these matrices to get you interested. So the Wigner matrix, as I mentioned, was introduced in nuclear physics in 1955. I'll give you more definitions later, the precise definitions. The Toeplitz matrix with IID entries. This was studied by a probabilist, or actually two probabilists in 2005, and you can see the gap is about 50 years took to somebody trying to study a different kind of random matrix. But this Toeplitz matrix, as we know, is important in time series and also in operator theory. The Hankel matrix again is related to the Toeplitz matrix, and its properties were studied in 2005. In the IID matrix, where you assume that all the entries are IID random variables, that has connections to non-commutative probability. And the beta matrices in particle physics, which are really extensions of the sample covariance matrix, in the sense that you can write down as I mentioned, if the entries are Gaussian, you can write down the joint density of the eigenvalues. And you look at that form of the joint density and you generalize that form by adding a parameter beta, which makes it a non-Gaussian observations or variables. So that those are called beta matrices. And then finally, I'll spend some time on the autocovariance matrices for high-dimensional stochastic processes. As I mentioned, I started looking into these matrices in 2014. And there are lots and lots of problems there if you're interested. Some of them are very hard. So what should we study if you have a random matrix? Now, of course, matrix is a linear transformation and whose features are captured by the behavior of its eigenvalues. So what behavior of the eigenvalues do we study? First of all, we can study the bulk behavior of the eigenvalues. I'll define it precisely because I'll need this definition later. For example, there is the semicircle law or the Marchenko-Postel law that I mentioned earlier. And the extreme eigenvalues, there is the Tracy-Widom law or our familiar to statisticians, the Gumbel law is there. One can study the gaps between the eigenvalues, and there are what are called determinantal point processes, which are kind of stochastic processes with specific features, which arise as the distribution of gaps of certain eigenvalues of some matrices. The joint behavior of several sequences of random matrices is also important. For example, it is useful in non-commutative probability and gives rise to or is connected to the notion of what is known as free independence. Unfortunately, I will not be able to go into those in this talk. And there are finally, last but not the least, there are applications. And applications of random matrices in statistics and other areas is sort of relatively new. And this is a very fertile area for someone who is interested in large dimensional data to get into. So what is the bulk how is a bulk of a random matrix, or for that matter, any matrix defined? So suppose that RP is a P by P random matrix with eigenvalues lambda 1 to lambda P. Then the empirical spectral distribution of RP is a probability distribution that puts mass 1 over P at each of these eigenvalues. So this is exactly like the empirical distribution of observations. So if I have x1, x2, xn as observations, then the empirical distribution of that is the probability that puts mass 1 over n at each of these xi's. So for example, that is used in kernel density estimates and the Kolmogorov-Smirnov statistics and so on and so forth. So the empirical distribution acts as the estimate of the population distribution. So taking a cue from that, this is how the empirical distribution of the eigenvalues are defined. Of course, these lambdas are not independent or IID, as is the case in usual statistics, but one can define this empirical distribution function, which sort of tracks the behavior of these eigenvalues. And one should realize that this value P will change, the dimension of the matrix will change, and so that the entire empirical spectral distribution will change as P changes. because the entries are random, the eigenvalues lambda1 to lambda p are also random, and so this is a random probability distribution, just like the empirical distribution function. So it is a random probability distribution. Now, if this distribution, the empirical spectral distribution, if it converges as p goes to infinity to some probability distribution, then that limit is called the limiting spectral distribution. Because we are dealing with a random quantity, that convergence can be in more than one sense. But let me slide over that issue and just say that the limit is called the limiting spectral distribution. Of course, the limit can also be a random probability distribution, but in our case, in all the examples that I've mentioned, the limit distribution is going to be a fixed probability distribution. This is called convergence in the bulk, since any finite number of individual eigenvalues do not matter for the limit. They're exactly the same as in the empirical distribution function case. If you change 20 or 30 or 1,000 observations as n goes to infinity, the behavior of the empirical distribution will not change. So that is why this is called the bulk behavior of the matrix. So having defined that, now I can go back to some of the matrices that I had mentioned before and tell you a little bit more about them. So the Wigner matrix is a symmetric matrix, so there is no structure in the matrix except that you assume symmetry, and you assume that the entries are IID random variables, and it was used as a model in nuclear physics. And of course, there are many variations of this matrix where you assume that they are not IID but independent, or they are triangly independent, and so on and so forth. Let's not go into those. So for us, the Wigner matrix is a matrix which is a symmetric matrix, and with all entries to be IID. And let us assume, for not only for this matrix but for all the other matrices, that the entries all have mean 0 and they have variance 1. So in other words, they are all standardized. So this is what this slide shows the simulation of the eigenvalues of a Wigner matrix. So what I have done is I have taken a 400 by 400 Wigner matrix with standardized Bernoulli entries, and I have simulated it 15 times. So that is 15 into 400 many eigenvalues, and then I have plotted the histogram of or in other words, I have plotted the empirical spectral distribution of the eigenvalues. And you can see that there's a very nice curve emerging out of all this, and this curve is nothing but what is known as the semicircle law, and one can show that this is the limit of the bulk for the Wigner matrix. This is also known as the free Gaussian law because it has exactly same kind of properties as the standard Gaussian law in probability, in free probability or in non-commutative probability. And it's also known as the semicircle law because of its shape. It's not quite a semicircle, but it's a scaled semicircle. You can also see that there are no eigenvalues beyond -2 and +2, and that can actually also be proved rigorously, that the extreme eigenvalues which converge to -2 to +2 from within from inside, not from outside. So almost all eigenvalues lie within -2 and +2. That can be as n goes to infinity. So next example, the Topi's matrix. So the Topi structure is a structure where you assume that the values in any given diagonal are all same. In addition, in this matrix, I have assumed that the entries, the matrix is symmetric. So if you look at the main diagonal, it has x0, and then upper diagonal of that is x1 and then x2 and so on. And because of the symmetry, the same thing happens in the lower diagonal. This is connected to the Topli's operator and a huge, very long history since the early 1900s. So this is a simulation of the Topli's matrix. So unlike the previous simulation, here I have still taken the 400 by 400 matrix, but for every such simulation, I have drawn the curve separately. So there are actually 15 different curves here, and each of them is a simulation of a 400 by 400 Topli's matrix. And you can see there's a nice shape emerges. It also shows that the convergence is almost sure. In other words, almost every curve will tend to this particular curve that you see in the picture. And the LSD is universal in the sense that the distribution of the entries do not matter. And that is the same story for all the matrices that I'm going to mention today. And the distribution, it looks like a Gaussian distribution, but it's not. And it has not been identified, but by moment calculations, you know that it's not a Gaussian distribution. You can actually see that this is more peaked than the Gaussian distribution. It's more concentrated around 0 than compared to the Gaussian. The variance of each of these curves is 1 anyway. So similarly, the Hankel matrix is a matrix which is also a symmetric matrix, but here you assume that the anti-diagonals or the anti-diagonals have the same value. So for example, you start with x0 and then x1 in the first diagonal, x2 in the second anti-diagonal, and so on. So this gives rise to the Hankel operator. And this is what happens if you simulate this matrix. Again, 15 different realizations with Bernoulli entries. Again, the LSD is universal. And you can see the very clear bimodal shape of this distribution. But you'll be surprised to know that there is no theoretical proof that the limit is indeed bimodal. There is a simple proof to show that the limit is not unimodal. That does not require that's a very simple moment matrix calculation will tell you that. But to show that it is indeed has exactly 2 modes, that proof has not been done yet. Okay, the circular matrix, that is very useful or important, or people are familiar to people who work in design of experiments, for example. So you start with the sequence x1, x2, xn, and then you shift that row to the right. So you start with xn in the next row, and then you move with x1, x2, xn, so on, so on. And so the last row will be x1 at the last position. So this is this is known as the circulant matrix. You can also circulate it the other way, but that's a different story. You can also circulate it by moving 2 or 3 or given fixed number of k places at a time. So that can also be done. So now you can, as you can see, that this matrix is a non-symmetric matrix, and so it has complex eigenvalues. So now the plot will be a 2-dimensional plot because you have the complex part and the imaginary part of the eigenvalues. You can still define the bulk of the empirical spectral distribution of the matrix, no problem. You have to use 2 variables, the imaginary part and the real part. And this is what happens for the circular matrix. Now you can see a very nice Gaussian looking, small Gaussian looking than the previous one, and it is indeed the Gaussian distribution that you see here. And again, the limiting spectral distribution is universal and is complex Gaussian. The proof of this is relatively easier because for circular matrix you can write down explicit formula for the eigenvalues. Even then you have to do a little bit of work to get to the limit. And this is how the simulation looks like. Then we go back to our example of sample covariance matrix. So this is the empirical spectral distribution of the sample covariance matrix. Here the entries are IID normal 0, 1 with n equal to 1000. And what I have done here is I have changed the dimension to the sample size ratio. In one I have taken it to be 0.25 and the other is 0.5. And as you can realize immediately that if it is more than 1, then there will be a lot of 0 eigenvalues, so you get a mass at 0. So I have not done that case here, but the main message is that first of all the spectral distribution is bounded, and the range of the distribution seems to depend on the ratio p by n. It is sort of increasing with the ratio p by n, which is true, and the maximum value is depends on the ratio anyway. It is also known as the compound free Poisson law because in non-commutative probability it happens to be the analog of the usual compound Poisson law in probability. Okay. And then next example is our familiar IID situation. So if I have a matrix, all whose entries are independent and identically distributed, means your invariants want to have a standard situation. And so this is how it looks like. So if you take p equal to n equal to 800 on the right, and p equal on the left, and p equal to 1000 on the right, as you can see, it's a completely dark, no shades of gray here, which really means that the distribution is uniform on this disk, you can also see the absence of the scantness of eigenvalues beyond the disk. So just like the Wigner matrix, one can actually prove that there are, with probability 1 as n goes to infinity, there are no eigenvalues outside the unit circle. So this is known as the uniform law, and this was a very hard result to prove, and many researchers have worked on this, and they proved different versions of the result. And so now it is known that if you have an IID matrix with a mean 0 and variance 1, then this is how the distribution looks like. It is a symmetric matrix, but it's a it's a square matrix because you take p equal to n, but it's not a symmetric matrix. Remember that the corresponding symmetric version of this would be the Wigner matrix, where you assume symmetry on the matrix, and that has the semicircular law. So it's like almost very similar kind of. You could probably guess this result from the Wigner result, but it's extremely hard to prove this. Okay, and finally to the matrices that I'm going to spend maybe 20 more minutes here. So this is the autocovariance matrix. Again, this would be familiar to people who work in time series. In any case, this is really the variance covariance matrix of a particular vector. Let me explain. So suppose that x1, x2, xn is a real valued, mean 0, stationary stochastic process. So stationary means that the distribution of x1, x2 and the distribution of x2, x3. So in other words, if you have a time shift, then they remain the same no matter what combinations you use. Okay, in that case, I can take xt and xt plus h. So that's the h is usually called the lag. So at the lag covariances are defined as or denoted as gamma h. And since we have a stationary process, this covariance gamma h does not depend on t, but depends only on h. Of course, if the xi's were IID, then gamma h would be 0, except for the case where h is equal to 0. Now, if I consider the vector x1, x2, xn, so that's a random vector, and look at its variance covariance matrix, then what you get is the sigma n that I've written down there, and you can immediately see that this has a covariance, as a Topli's structure. So, for example, the covariance between x1 and x2 and x3 are same, which means that that covariance is gamma 1, so that will be on the first diagonal, and so on. And gamma 0 is the variance of xi, so that is the main diagonal. So this is, of course, a Topli's matrix, but unlike the Topli's matrix that we encountered here, this is, first of all, this is a non-random matrix, and if I replace these autocovariances by their estimates, sample estimates, and that would be a random Topli's matrix. But unlike the previous Topli's matrix, there would be very strong dependence between the entries. All right, so sigma n was the population autocovariance matrix, as you can see here, because nothing is random here. I have taken the expectation, so I have substituted the expectation in this as the entries. Now, if I decide to estimate these gammas by their corresponding sample versions, then that's what I have written here. Gamma hat h is the, so you take products at lag h and you sum and you average. I have used the average in 1 by n for all of them, ignoring the fact that you have lesser and lesser number of terms in the sum when h increases, but that would make the matrix positive semi-definite. Otherwise, you will lose the positive semi-definity. Then we get the random sample autocovariance matrix gamma in x, and you can realize that as you move away from the main diagonal, there are lesser and lesser observations, so that your estimates are less and less stable. Anyway, this is known as the sample autocovariance matrix in the literature, and we have proved with two former students of mine. So this was a part of their master's project. So Anirban Basak is now in ICTS as a faculty, and Shanchan Shen is now in IISc Bangalore Math Department as a faculty. So we proved that the limiting spectral distribution exists. Its properties are not known, unfortunately. It's a very complicated distribution, but it is connected to the spectral density of the process which is understandable because the spectral density captures all the properties of the sequence exercise, and the limiting distribution, unlike the sample covariance matrix where you had an upper bound, this limiting spectral distribution is unbounded, even when the exercises are IID. Okay, now having explained that, what happens in the when you have real valued time series, let me move to the setup where I have a time series whose at the time point t whose observations are vector valued. So the dimension of the vector is p, as I mentioned in the data matrix. So suppose that xtp is a p-dimensional vector valued time series. P will also eventually go to infinity. That's this theoretical construct that we have to deal with it. When you apply, you just assume that the P is large. So for a real valued time series, we had one sequence of autocovariances, gamma h equal to expected value of xt times xt plus h. But now xt is a vector xt comma p, and so you have xt star. So then gamma h now itself becomes a matrix, right? So now for every like h, we get a matrix. So the sample autocovariance matrix of order I of xt is the p by p matrix, which is defined as. So this is exactly like the real valued case, except that now I have a matrix because I have the value at t and I have the value at t minus I, but xtp is a vector, x star t and xt minus ip is also a vector. So I have taken transpose. So that makes it a matrix, which is a p by p matrix because xtp is p by 1 and x star is 1 by p, so that makes it p by p, and you take a sum over all possible combinations, and you define gamma hat I as a sample autocovariance matrix. Now you can imagine that taking a cue from the one-dimension case. In the one-dimension case, the sample autocovariance matrices gamma hats, small gamma hats, are the crucial ingredients if you do a time domain analysis of any time series. So likewise, it is the gamma hats I here in this equation, which should be the building blocks of any inference procedures. So the broad goal with which we started was to study the properties of these sequences, including the joint convergence as Pn goes to infinity. So I can, to begin with, I can try to look at the bulk distribution of gamma hat I for any I. And then I can also study the joint distribution of gamma hat, let's say 1 and gamma hat 2. I'll not go into details of how you study those joint distributions because now you have matrices instead of vectors, and you want to do everything in terms of eigenvalues. So as you know, eigenvalues of A times B is not equal to eigenvalue of A times eigenvalue of B, or any other notion of addition or etc. and do not apply. So studying the joint distribution is a or formulating the problem of joint distribution is not trivial. So anyway, I will not go into that, but I'll study one matrix at a time and mention what some of the results that we have obtained. So I have made some progress with Monica Bhattacharjee, who did a PhD thesis with me in 2016. She is now in IIT Mumbai, math department as a faculty. And Walid Hashem, who is in Paris, and started this work with him in 2018, Walid and myself. And then we had plans to rope in Monica, but in 2019 the pandemic hit us, so all our plans have been shelved for now. So anyway, so I'm going to report some of the results that that we have been able to achieve with these two co-authors. So before I do that, let me make remarks. If the entries XTP are IID, then gamma hat 0 reduces to the standard sample covariance matrix, as you can see from here. So you will get if t equal to, right. So if I equal to 0, then you get xt star, and that is precisely the definition of the sample covariance matrix. Okay. Even in the all IID case, the sample autocovariance matrices of other orders have strong dependency in the entries. Okay, because you are using the lags here, so there will be very strong dependency between the entries of the matrix. Except for I equal to 0, all the matrices are non-symmetric, because for I equal to 0, you get by the sample covariance matrix, but for any other I, this matrix is non-symmetric. Non-symmetric random matrices are hard to analyze, and one may resort to symmetrizations such as gamma hat I plus gamma hat I star, or gamma hat I times gamma hat I star, and so on. But that would entail some loss of information. And finally, for wireless communication applications, it is important to consider the case where XTP are complex valued. Even though complex valued time series, for finance and other applications in economics, people are satisfied with having a real valued time series, but for wireless communications, you need these complex valued entries. Incidentally, having complex valued entries and having real valued entries, the study of these two situations are quite different, and so one may be able to prove results for the complex case, but not for the real case. So somehow this complex case may actually turn out to be simpler. Okay, some points to note. So some sort of structural assumptions or models need to be imposed on the XT if I want to state or prove any property of this gamma hat highs. Of course, here now the variable p is going to go to infinity along with the sample size n. And the Gaussian case is expected to be easier. Well, Gaussian cases are always easier compared to the other cases, because as you know, the Gaussian distribution is determined by the first two moments, which in any case we have assumed to be 0 and 1 in this case. And so, Gaussian expectations of Gaussian functions, you have nice integration by parts formulas and other things. So that's why the Gaussian case always is easier than the other case, especially for matrices. So here is my model. As I said, I'm going to use some model. So here is a model which is there in the literature. So this is one of the high dimensional time series models that is used. So this is called the MAQ model. So moving average of order Q. So it's like the usual linear case of moving average models, but unlike them, now I have the observations are vector valued, and the dimension of the vector will also increase. So I assume that xt is equal to is a sum of psi j epsilon t minus j. So it's like a moving average of epsilons. But now the psi's are also matrices, and the epsilons are vectors. So psi's are p by p matrices, non-random, and the epsilons are IID with mean zero and variance covariance matrix IP. Of course, one can look at the situation where the variance covariance matrix is something else, and some things you can do with that, some things are more difficult, and so on. I don't want to go into those details here. And you assume that P is such that P by n goes to gamma, and gamma is allowed to be between 0 and infinity, including the value 0. 0 is a special case. We'll see that a little bit, but I have excluded infinity because you can use the fact that the eigenvalues, the non-zero eigenvalues of A star and A star A are same, right? So one can use that and convert the gamma equal to infinity case to the gamma equal to 0 case. All you have to do is throw away a lot of zero eigenvalues, and you can look at the rest of the eigenvalues. And if Q is equal to 0, that is the IID process. So there is no other psi j's, only one, which is assumed to be the identity matrix. So xt is equal to epsilon t. So this is the IID case. So that is the MA0 case. Okay. So let us keep those notations in mind. All right. Now, I will not be precise in when I state the theorems, because I think it's nobody would remember anyway. But I'll sort of hand wave the assumptions a little bit so that you get a feel of what kind of assumptions are made. And I'll also hand wave the theorems a little bit so that you can get an idea of what kind of results can be proved. This is appeared in a long list of papers with Monica. The number one, the limiting spectral distributions for symmetrized autocovariance matrices of all orders exist, but it is not possible to write them down explicitly. So that's kind of a meta theorem. You give me actually for any polynomial. So symmetrized means I can look at gamma 1 plus gamma 1 star or I can actually look at gamma 1, gamma 2, and then symmetrize that itself. And so, in other words, any polynomial polynomial matrix which is a symmetric matrix and which can allow any number of autocomplete matrices, any finite number of autocomplete matrices of any order, they all exist, but it is not possible to write them down explicitly because understandably the distributions are quite complicated. One can write down some kind of recursion equations for the limit moments, or can write down some recursion equations for the corresponding Stieltjes transform, but these are very complicated to state. The limiting spectral distributions can be described in terms of free variables. So that is like the concept parallel to independent variables in statistics. Sometimes you cannot write down the limit distribution explicitly, but you can express that in terms of independent random variables. For example, the non-central limit theorem in new statistics. So that is a weighted sum of chi-square random variables, where the chi-square variables themselves are independent. You cannot write down the distribution explicitly, but you can say it's a sum of linear combination of IID chi-squares. Okay, so something like that can be done in this case. So instead of IID variables, you have what are known as free variables. The joint convergence holds when we have several independent time series, which means if I have, so I have said xt, so if I have another yt which is independent of xt, and then I look at the autocovariance matrix of y and of x, and then mix them up in any way I like, and then look at their traces or average value of the eigenvalues of any power of those matrices, then they also converge. So that is usually known as the tracial convergence. Finally, for statisticians and for time series people who quite often use this trace of some sample matrix as a test statistics for all kinds of things, this result is interesting. Trace of any combination of the sample autocovariance matrices is asymptotically normal. So, for example, if I take the trace of gamma 1 times gamma 2, or gamma 1 times gamma 3, or plus gamma 1 times gamma whatever, so any polynomial combination, if I just take the trace instead of looking at the eigenvalues, then this trace is asymptotically normal. So that's again a sort of meta theorem, and this can be used in applications in statistics. And the technique for proving these things is you embed these autocovariance matrices into IID matrices, and then polynomials of IID and deterministic matrices. And then we use the moment method along with asymptotic freeness properties of the IID and the deterministic matrices. Okay, so that's all I'm going to say about how you prove this. These are non-trivial results anyway, and very quite technical. Okay, so here is a demonstration of how it can be used in statistics. So I have in this slide I have taken the MA0 model. So xt is epsilon t, which means the xt's have been taken to be IID, and then I have formed this symmetric matrix gamma u times gamma u star. So as you can see, that is a symmetric matrix, and u I have taken the lag, I have taken to be 1 to up to 4. In other words, I am simulating 4 matrices here. Having simulated the xt values, I have constructed these 4 matrices, and I have plotted their empirical distribution function. So of course, because these matrices are all symmetric, all their eigenvalues are real. So I can, instead of plotting the histogram, I can also plot their empirical distribution. So that is what is being done in this curve. Now you can see that there is only one curve, even though I have 4 matrices, and that is because these curves overlap each other. So that this legend really does not make any sense. So because all the curves are really superimposed. I'll explain why that is so. So that is what happens if I have the MA0 model. You could also take gamma 10 times gamma 10 star. That would also have the same distribution. There's something to do with the order of dependency in the matrix, which is in this case is 0. There is no xt and xt plus 1 are independent of each other. Okay. So as I said, promised I will explain it. So recall the parallel situation for real valued IID random variables. If eta I are IID with mean 0 and variance 1, then if you look at the cross products, with lag t, eta I times eta I minus t, then they're all asymptotically normal. not very hard to prove because, as you can see, they are already uncorrelated, and and so there is very weak dependency between these summands. Not only that, for different values of t also they are uncorrelated. So each of them will be actually IID normal 0, 1. So it does not matter, and this is a reflection of the fact that eti's are IID. This will not be true if the variables are independent. Okay, so now let us see a similar example here. So this is model 1b, x is equal to epsilon t plus ap epsilon t minus 1. So A is a matrix. I have taken it to be a very simple matrix, namely the constant times an identity matrix. And this model has a dependency of order 1. And you can see that quickly the empirical distribution picks that up because there is one curve which separates out, namely u equal to 1, and the other curves, they have no dependency, so they all have the same kind of distribution. So in other words, you can very quickly judge the degree of dependency by plotting these similar values of gamma u. Okay, similar kinds of plots you can get if you use other kinds of symmetrizations. All right. So that was about the symmetric case. So my autocovariance matrices were non-symmetric, but I forced them to be symmetric by symmetrizing them in some way or the other. Now, of course, symmetrization entails a lack of loss of information, because if instead of looking at the matrix gamma 1, I'm looking at gamma 1 star. So they, of course, singular values and eigenvalues are not the same. So there is a loss. And so let us see what happens to the original non-symmetric autocovariance matrices. So as I mentioned earlier, this problem is much more difficult. So let us look at gamma 1 hat, which is x summation xt minus 1 star. So I have dropped the suffix p here, so just to make the notation simple. I have taken the MA0 model. In other words, xt's are IID, but you can see that the summands xt minus 1, they are dependent on each other, even though they have yeah. Okay, so now this is what happens when you simulate that. So it's a p-by-p matrix, and it also depends on the value of n. I think n, yes, I have taken n to be 500. So in one, this is the p by n ratio is half. In the other, p by n ratio is 1, and of course the plots depend on the ratio. But you can see there's a nice plot, nice pattern emerging out of that. So in other words, there is a hidden result on the limit distribution of this matrix. Okay, so as I mentioned earlier, non-symmetric matrices, the tracial convergence does not yield existence of the limit spectral distribution. So the methods that you use for symmetric matrices are not directly applicable to non-symmetric matrices, even though you can borrow some of the ideas from symmetric matrices there. But the harder parts of the proofs have to be done with a lot of labor. So one of the major steps in the proof for any non-symmetric matrix is to establish suitable bounds for the smallest singular value of the matrix. Unfortunately, I cannot go into the details of the proofs, and I should not also because it's very technical. But I'll point out this fact that the smallest eigenvalue problem of a non-symmetric matrix is a problem on its own. In other words, if you are given a matrix which is non-symmetric, and you want to say something about the smallest singular value of that matrix. So all kinds of probability bounds or deterministic bounds are known for the smallest singular value. And it can be shown that the study of the bulk of the original non-symmetric matrix is one of the key steps is to get a nice behavior of the smallest singular value of the corresponding singular values of the matrix. So that is why this smallest singular value problem is a distinct and important problem in matrices and also random matrices. So here are my assumptions. So let me look. So this is a very limited result. I'm assuming that the XTs are independent, IID, and but I'm still looking at the autocovariance matrix of order any order. The P by N data matrix X consists of IID random variables with a non-trivial complex part. So here I've assumed that the entries are genuinely complex and with appropriate moment condition. This is fine for applications in wireless communications and signal processing, not acceptable for time series applications. And this assumption is due to the application of a Bayesian bound as a tool in one of the steps in the proof. So that's a very technical thing. here is some notation here. So S0, S1, S2, Sn minus 1 will denote the singular values of a matrix. We assume that suppose A is a matrix whose minimum eigenvalue or minimum singular value and a maximum singular value, they are bounded away from 0 and infinity. So here, as the dimension changes, the identity matrix trivially satisfies this assumption. The circular matrix also satisfies this assumption. Its empirical spectral distribution converges to the uniform distribution on the circle of unit radius. That's very easy to prove actually. Okay, so having given that matrix, so here is a general smallest singular eigenvalue result which we proved, and this was then applied to study the behavior of gamma 1 hat. And I'll just state this theorem and spend 30 seconds on it. So look at x star minus z times p. So these are auxiliary matrices that come out in the main proof. So you have to study this particular matrix for any arbitrary non-zero complex number z. And you show that the smallest singular value of this matrix has this probabilistic bound. And norm x less than or equal to c, that you see that will automatically follow from the uniform distribution result that I showed you in the beginning. So norm x is anyway bounded with high probability, so that is not a big deal, and the constant depends on certain objects. Okay, so we do not yet have the result for matrices with real entries. Remember that this is being proved only when the x's have a genuine complex parts in the entries. Okay, and I will probably skip this slide. It says that the limiting spectral distribution for gamma 1 hat exists, and that spectral distribution we have expressed explicitly, and in that expression, this function g comes up. So that's why the importance of this. So here is the theorem. So it is very much like the IID uniform theorem. So maybe I'll skip the exact statement, but I'll give you a couple of simulations, maybe one simulation. Okay, so this is what happens. So if so capital N should be P, unfortunately I made a typo here. So as I said, if P is larger than N, then you have some zero eigenvalues. So then you have a hole there. So there are no eigenvalues. So there is so there are a lot of eigenvalues at zero, but there is a separation. The rest of the eigenvalues is separated out from the zero eigenvalue, and that's what you get. In the second case, where P is smaller than N, there is no such problem. So you have a nice smooth, actually a density in this case. Okay. Yes. So any questions? All right. So may I take 5 more minutes? I have 5 slides actually. I'll need 2 minutes. Okay. So instead of the MA0 null hypothesis case, we now assume that it's a stationary Gaussian process. So I have removed the assumption of the IID, but I have added another assumption here. I have said that it should be a Gaussian process. As I mentioned earlier, Gaussian processes are easier to tackle, and we have not been able to prove it for a non-Gaussian case. We assume that the spectral density of the process is well behaved. For example, it is bounded away from 0 and infinity. And then one can again show that the now it is not for the gamma 1 hat, but for any gamma hat L, because now any different gamma hat L's will have different distributions, unlike the IID case. And so this is the kind of probability bound that we could prove, and then we could use that to so maybe this, I'll skip this one, and we could prove that to get to the following theorem. So this theorem does not really give you the limiting spectral distribution. However, it comes very close, and we are still working on it. It says the following. So suppose mu p is the empirical spectral distribution, and mu bold p, I should have probably used a different notation, denotes some specified deterministic probability measure. So mu p is a random probability measure, mu bold p is a non-random probability measure. So this theorem says that there exists such a sequence of measures such that mu p minus mu bold p converges to 0. In other words, and the sequence mu p is tight, but we don't know whether mu p itself converges or not. It should, but we have not yet been able to prove it. So these kinds of theorems are known as deterministic equivalent theorem. You cannot prove that the mu p itself converges, but you can show that mu p is close to some other non-random probability measure mu bold p, and that's it. That's where you leave it, and you try to prove that mu bold P converges, which we have not been able to do, but we have been able to show that mu bold P is tight. Okay, so we are of course working on the convergence of mu bold P, identification of the limit, and the relaxation of Gaussianity. All of these are very difficult problems. Okay, so here are some selected books that the students especially might be interested in. When I came into random matrices, there was only one book, and that was by a physicist, written in physics language. But now it's heartening to know that there are a lot of random matrix books which you can consult if you are interested in this area. Okay, thank you very much.
Thank you very much, Arup. That
Thanks.
was really very nice lecture. Very interesting.
Thanks.
Material, beautiful slides.
Thank you.
Congratulations.
Thank you.
We have maybe a minute or two for questions if there are any. Anybody willing to calculate a couple of eigenvalues? That was really very nice, and there was new thoughts for me.
Okay.
So let
It
us
is very
thank.
informative with lots of resource informations.
Exactly. So let us thank Arup in a traditional way.
Thank you.
Okay, I will close the session, and the next speaker will continue. Thank you again.
Thank you.
Raksha? Over to you. Raksha?
Hello.
Yes.
Thank you, Professor Arup Bose, for delivering the talk. I also thank Professor Simo Puntan for chairing this session. Next session will start exactly at 3 o'clock. Bose, if you can please stop sharing your screen. So welcome back to the next session. In this session, we have with us Professor Abraham Berman from Technion Israel Institute of Technology, Israel. The Department of Mathematics at the Technion became his professional home from the beginning as a senior lecturer until his retirement as a professor and holder of the Israel Pollock Academic Chair and continuing now as Professor Emeritus. He also held a parallel position of a professor in the Department of Education in Sciences and Technology at the Technion. His list of publications include papers on linear inequalities over cones, stability, proper splittings, completely positive matrices, transmission control protocol, sign patterns, minimum rank, etc. Today he will be delivering a lecture on completely positive matrices. Another speaker of this session is Professor K.C. Shivakumar from Indian Institute of Technology, Madras. His topic of interest is infinite linear programming, generalized inverses of operators over Hilbert spaces, non-negative generalized inverses, generalizations of matrix monotonicity, linear complementarity problem, generalized inverse of matrices over indefinite inner product spaces. Today he will be talking about some generalizations of P property for operators on the space of real symmetric matrices. Moderator of this session is Professor Balaji Ramamurthy from Indian Institute of Technology, Madras. I now request Professor Balaji to take over. Over to you, sir.
Can you hear me? Hello? Hello, can you hear me? Hello? Hello, anyone? Berman to give you to start his presentation. Welcome, Professor Berman, please. Professor Berman. Hello? Yeah. Thank you.
Good morning. It's my pleasure to be again, almost be in Manipal. Hopefully next time it will be a real visit. And the talk is on completely positive matrices. In 2003, Professor Shaked Munder and me published the book Completely Positive Matrices, and at that time it included most of the knowledge on the topic, but since then there were many developments, and in very recently, we published a new version on copositive and completely positive matrices, and the talk will be based on these two books. What are completely positive matrices? We know, of course, that if a matrix is positive semi-definite, if it can be decomposed as A equals B times B transpose, or equivalently, if it is symmetric and the quadratic form X transpose AX is non-negative for every vector X. Now, if we, in addition to asking that A is B transpose, we require that the elements of B are non-negative, A is B transpose where B is a non-negative matrix, then A is completely positive. On the other direction, if we relax the condition that X transpose AX is non-negative for every X, and only ask that it is non-negative for every non-negative X, then A is co-positive. So we have two classes of matrices, completely positive matrices and co-positive matrices. The completely positive matrices are a subset of the positive semi-definite ones, and the co-positive matrices include the positive semi-definite matrices. The name completely positive was coined by Marshall Hall, and the name co-positive was coined by Theodore Motzkin. And there is a very interesting, important relation between the two classes. First of all, both of them are cones. The set of n by n completely positive matrices is a closed convex cone. We denote it by CPN. The set of n by n co-positive matrices is also a closed convex cone, and we denote it by COPN. There is a duality relation, and with respect to the inner product, A inner product B is a trace of A times B in the vector space of symmetric n by n matrices. The cone of positive semi-definite matrices is self-dual, dual to itself, and the dual of CPN is COPN, and the dual of COPN is CPN. This is an important relation, particularly because, as we will see, of the importance of these matrices in optimization, because we have dual programming problems. Burger showed that every quadratic problem with linear and binary constraints can be written as a linear program over the cone of completely positive matrices. So on one hand, what we get is, this is true even if the quadratic problem is not convex, and then it's very difficult to solve it. And so we make it linear program, which is easy to solve. However, we have to know if the given matrix that we find is completely positive. There's interesting, important surveys on co-positive programming and completely positive programming, and I write it together as COP by Miriam Dur and by Manuel Bonzi. We had in Oberwolfach in 2017, we ran a workshop that was a good meeting between matrix theorists and between experts in optimization. And here are the organizers of the workshop. On the left is Emmanuel Bonze. Next to it is Naomi Shafed Monderel, and right to me is Miriam Dur. How do we tell that a given matrix is completely positive? The comparison matrix of a non-negative matrix is obtained by multiplying the off-diagonal entries by -1. We keep the diagonal entries and put minus before the off-diagonal entries. And there is a theorem, important theorem by Drew, Johnson, and Levy, that says that if A is symmetric and non-negative, and if the comparison matrix is positive semi-definite, then A is completely positive. This is an important sufficient condition. It is not necessary. If we consider the 3 by 3 matrix of ones, it is clearly completely positive because it's a product of the column of ones by the row of ones. But if we look at the comparison matrix, we have ones on the diagonal, -1 off diagonal, and -1 is an eigenvalue. So the comparison matrix is not positive semi-definite. So and it says that if a matrix A is completely positive, it must be positive semi-definite. It follows from the definition. So we say that a matrix that is non-negative element-wise and non-negative in the Leibniz sense, we call such a matrix doubly non-negative. And so the necessary condition is that if A is completely positive, it must be doubly non-negative. For small matrices, Maxwell and Min showed that if for n less than or equal to 4, that the two conditions are equivalent. A is completely positive if and only if it is doubly non-negative. In some way, fortunately, because otherwise it wouldn't be interesting, this is not true for bigger matrices. For n equals 4, we have an example of the matrix A, which is B times B transpose. B is a matrix on the left. So this matrix is positive semi-definite. It is element-wise non-negative, so it is doubly non-negative. but we will see that it is not completely positive. To see that and to understand when the necessary condition is sufficient and when the sufficient condition is necessary, we consider the graph of a matrix. If we have a symmetric matrix of order n, its graph has n vertices, v1, v2 up to vn, and we have an edge between vi and vj if and only if aij is non-zero. And we say that in this case, the matrix A is a symmetric matrix realization of G of A. If we look at the examples that we had, the matrix 1, 1, 1, 1, 1, 1, 1, 1, 1, its graph is a triangle. If we look at the graph of the 5 by 5 matrix, its graph is a pentagon. And indeed, Drew and Johnson and Levy showed that if A is completely positive and the graph of A does not contain a triangle, is triangle free, then the comparison matrix is positive semi-definite. So in this case, if the graph of a matrix does not have a triangle, is triangle free, the sufficient condition is necessary. This also helps us to understand why the 5 by 5 matrix that we had is not completely positive, because its graph is a pentagon and it does not contain a triangle. Since it does not contain a triangle, the comparison matrix had to be positive semi-definite for the matrix to be completely positive. But if we look at the comparison matrix and we put one off diagonal, we see, and this is true not only for 5, it's true for n greater than 5 as well, we see that the determinant of the comparison matrix is -4. But this, of course, means that the comparison matrix is not positive semi-definite, and this explains why the matrix is not completely positive. In a paper with Nomi, we showed that the triangle-free property is in fact equivalent to the fact that the sufficient condition is also must be necessary. It says that a graph G has a property that for every non-negative symmetric matrix realization of A, the comparison matrix is positive semi-definite if and only if A is completely positive. This is the property of the graph, and this holds if and only if G is triangle free. So this property is equivalent to the graph having no triangles. It's a characterization of the graph having no triangles. When is the necessary condition sufficient? So we say that the graph is completely positive if the necessary condition is sufficient. That is, we say that the graph is completely positive if every doubly non-negative matrix realization of G is completely positive. And the question is, of course, when a graph is completely positive. And the following theorem that was obtained in the thesis of Natalie Kogan says the following: a graph G is completely positive if and only if it does not contain an odd cycle of length greater than 4. It's interesting to compare the result on triangles with this result. We can say that a graph G is completely positive if and only if it does not have a long odd cycle. A long odd cycle is an odd cycle of length greater than 4. Does not have pentagons, does not have septagons, and so on. On the other hand, if we look at triangles free, we can say that the triangle is a short odd cycle. So we have these two conditions together. And in fact, if we put the two conditions together, we get the characterization of bipartite graphs. A graph is a bipartite graph if both conditions held. This is Natalie Kogan. This is Danny Hershkovitz. With Danny, we proved the one direction of the theorem. With Bob Gron, we proved the theorem for bipartite graphs. And as I said, the full theorem was proved by in the thesis of Natalie Kogan and also by Ando. Here is an interesting application to quantum information. And maybe I will skip the details and just say that in quantum information, we want to know if a state is entangled or separated. And there is a condition by Asher Perez that says that a state that is not entangled must satisfy properties that we call positivity under partial transposition. In a paper of Tura and his colleagues, they formulated the separation problem for a specific class of states, the diagonally symmetric states. And for these states, they defined a one-to-one correspondence between a state and a matrix, between a state rho and a matrix M of rho, that its entries are between 0 and 1, and they sum, their sum is 1. And they showed that for these diagonally symmetric states, rho satisfies the Perez condition, the Perez criterion, if and only if the matrix is doubly non-negative, and the state is separable if and only if the matrix is completely positive. So we see that we have here the states that we know for completely positive matrices, that being doubly non-negative is a necessary condition for being completely positive, but not sufficient. And for small matrices, and this is true also in the case for the symmetric states, it's equivalent. The name completely positive is not, and I hope Marshall Hall would forgive me, is not an excellent name, because there are many similar names defined for related for other classes of matrices. For example, a matrix A is totally non-negative if all its minors are non-negative. And the matrix A is totally positive if all its minors are positive. The two classes are different. Completely positive matrices have to be symmetric. Totally positive matrices do not have to be, are not necessarily symmetric. And there are other differences, but there is a theorem of Markham, and he showed that for every symmetric non-negative matrix, there is a non-negative triangular matrix, L, such that A is equal to L transpose. So this is in fact a Cholesky decomposition. And so in this case, we see that although completely positive matrices and totally positive matrices are not the same, symmetric non-negative matrices, symmetric totally, sorry, there is I have to correct it. Symmetric totally non-negative matrices are completely positive. So please correct for yourself the last sentence. Symmetric totally non-negative matrices are completely positive. This is Ando, and I put his picture here also because he has two interesting monographs, one on totally positive matrices and one on completely positive matrices. And this is Tom Markham that I just mentioned. Another class is that is not completely positive, but has a similar name, is completely positive semi-definite. We say that a matrix, an n by n symmetric matrix A is completely positive semi-definite if there are positive semi-definite matrices P1, P2 up to Pn, such as the Ij entry of A is a trace of Pi times Pj. This is also a closed convex cone, and we denote the set of n by n completely positive semi-definite matrices by CPSDN. And CPSDN is between CPN and DNNN. Every completely positive semi-definite matrix is doubly non-negative. Every completely positive matrix is, of course, completely positive semi-definite matrix. But for n greater than 4, the inclusions can be strict. And another class of matrices that are not completely positive but have similar name is completely positive maps. And there is an important paper of Choi on completely positive maps. And the maps have very important application. Completely positive maps have important application in quantum theory and in quantum information, because we can because the quantum channel is what is called a trace-preserving completely positive map. I don't want to go into details on this, but I want to emphasize that although completely positive matrices are different than completely positive maps, both classes have applications in quantum information theory. This is Mandu and Choi, and I want to move to another important concept, which is the CP rank, the completely positive rank. We recall that completely positive matrix can be decomposed as A equals BB transpose, where B is a non-negative matrix. But this can be done in many ways. The smallest number of columns of B in such decomposition is called the CP rank of A. Why do we call it rank? Because it is the smallest number of rank 1 completely positive matrices that sum up to A. And we denote it by CPR of A. So by the definition, it is obvious that CPR is greater than the rank, greater than equal to the rank. The inequality can be strict. Here is a 4x4 matrix with CP rank CP rank 4 and rank 3. The CP rank is also bounded from above by Carator-Lorry theorem. The CP rank of an n by n matrix is less than equal to n times n plus 1 over 2. But we will see that this is an exaggerated bound. We can bound it by much better. What can we say about the CP rank of matrices of rank R? There is a theorem of Hanna and Laffey that says that if A is a completely positive matrix of rank R greater than or equal to 2, and N is a maximal number of zeros in a non-singular principal submatrix of A, then the CP rank of A is bounded by R times R plus 1 over 2 minus N. With Barioli, we slightly improved this result by showing that the CP rank of R is bounded by R times R plus 1 over 2 minus 1. And we had examples that the bound is tight. For small matrices, n less than or equal to 4, Maxfield and Min showed in the beginning when the theorem started to be developed that if A is an n by n completely positive matrix where n is not more than 4, then the CP rank of A is less than equal to n. In other words, the composition can be squared. The matrix B can be squared. But this is not true for n from 5 and above. Drew, Johnson, and Levy conjectured that if A is an n by n completely positive matrix n greater than equal to 4, then the CP rank of A is less than equal to n squared over 4. We observe that this, and also the results of Hannah and Laffy and Barioli and myself, are much better than the bound by Caradori. The Drew-Johnson-Levy conjecture is true in many cases. Let us say that the matrix is special if the graph of A is completely positive, or if the graph of A is triangle-free, or if the comparison matrix is positive semi-definite, or if the rank of A is less than equal to 2. So again, we say that the matrix is special if its graph is completely positive or triangle-free, or its comparison matrix is positive semi-definite, or its rank is less than equal to 2. And for special matrices, the VGL conjecture is true. The CP rank of A is bounded by n squared over 4. It was proved by Drew and Johnson in '96 when the graph of A is completely positive. It was proved by Drew, Johnson, and Levy in the original paper in '94 when the graph is triangle-free. It was proved by Nomi and myself for when the comparison matrix is positive semi-definite. And it is true when the rank of A is less than equal to 2, because in this case, the CP rank and the rank are the same. Okay, let's denote by Pn the maximum of the CP rank of A when A is an n by n CP matrix. So again, Pn is the maximum CP rank for an n by n CP matrix. So the VJL conjecture says that Pn is less than equal to n squared over 4 when n is greater than equal to 4. This is not true in general, but it took about 20 years to disprove it. It is true for n equal 4 because P4 is equal to 4. It is true for n equal 5 because by a paper of Nomi, Sheked, Monderer, Bomse, Yare, and Schachenberg, P5 is equal to 6. But it is not true for n equal to 6 because P6 is between 9 and 12. I'm sorry, I want to go back. It is not known if it's true for n equals 6. What is known is that P6 is between 9 and 12. So if P6 is indeed 9, then the VJL conjecture is true. But if it is more than 9, then it is not true. And this is one of the interesting open problems. For n equals 7, it was shown that P7 is greater than equal to 14. And if we compute a 7 squared over 4, we get a smaller number. We get 12 something, which is smaller than 14. So for n equals 7 and for n more than 7, the conjecture is not true. I want to remark that in 2000, this was only proved in 2014. I want to remark that in 2002, Francesco Barioli announced an example of a 7 by 7 completely positive matrix with CP rank equals 14, which would be a counterexample to the conjecture, but he never published his example. This is Francesco Barioli. And now I want to consider some special classes of completely positive matrices. we say that a matrix A is completely positive over the rationals if it can be decomposed as A equals B times B times B transpose, where the matrix B is a rational non-negative matrix, and the matrix D is positive diagonal rational matrix. So again, A is completely positive over the rationals if it can be written as A equals DBB transpose, where B is rational and D is a positive diagonal rational matrix. We could take D to be I, and it is true that A equals BB transpose, and this follows from Lagrange four-square theorem. This is the remark in the end of the slide. But we want to keep the definition as written. A is D, BD transpose, where D is positive diagonal rational matrix, and B is a non-negative rational matrix. And the smallest number of columns in B in such decomposition is called the rational CP rank, and is denoted by QCPRA. QCPRA is greater than equal to CPRA, of course, from the definition, but the inequality can be strict, as this example shows. And here is a natural question. Is every rational completely positive matrix completely positive over the rationals? So we have a matrix that is completely positive. Its elements are rationals, its entries are rational, and we want to know if we can factorize it over the rationals. And Dutour, Sikirik, Schurman, and Valentine proved that the answer is true if we know that the matrix lies in the interior of the cone of completely positive matrices. So if every rational, it proved that every rational matrix that lies in the interior of CPN is completely positive over the rationals. And so this is a very nice result, but it leaves open the question when the matrices in question are on the boundary of the cone. And this makes the study of the cone, or study of the boundary of the cone, important and interesting. There are other cases, there are some cases that we know that the condition is, the theorem, not the theorem, the answer to the question is true, is yes, even if the matrices are on the boundary. Recall that we say that the matrix is special if the graph is completely positive or triangle free, or the comparison matrix is positive semi-definite, or the rank is less than equal to 2. And Shaked, Mulder, and Du and myself showed that for special matrices, the answer is also true. Every matrix is completely positive over the rationals. The following discussion shows that the answer to the previous question is not obvious. We can say that the matrix is completely positive over the integers if we can decompose it as A equals B, D, B transpose, where B is an integral non-negative matrix and D is a positive diagonal integral matrix. So the same definition, but as we had with the rational case, but here we want the matrices to be integer. The smallest number of columns in B in such decomposition is called the integer CP rank of A, and we denote it by Z CPRA. Again, by Lagrange theorem, we could take D to be I, but then the number of this will change the definition of the CP rank, and we say that the smallest number of columns of B in A equals BB transpose, where B is integral, we denote this number by ICPRA. And it can be, again, by Lagrange theorem, 4 times bigger than the ZCPRA range. But as we will see, it is more interesting to study ICPRA than ZCPRA. Anyway, ZCPRA is greater than or equal to QCPRA by the definition, but this equality can be strict. And as I said, in this case, ICPRA is 7. So here we have the question, is every integral completely positive matrix completely positive over the integers? And here the answer is no. If we look at the matrix AAB, where A and B are integers greater than or equal to 2, this matrix is completely positive, but it is not completely positive over the integers. Another example that doesn't have zeros is the matrix where D is 2, 3, 1, 3, 4, 5, 3, 1, 3, 5 plus D, where D is a non-negative integer. This matrix is completely positive, but not completely positive over the integers. And in fact, we can show that if the matrix, for every matrix of order 2, there is an example of an n by n integral completely positive matrix that is not completely positive over the integers. We can state it in terms of graphs. Let G be a graph on n vertices with at least one vertex of degree greater than 1. In other words, a graph that contains a path of length 2. Then there is an integral completely positive matrix realization of G that is not completely positive over Z. But Laffy and Smigosh proved that every 2 by 2 integral completely positive matrix is completely positive over the ratio. Again, this is a mistake. It's true, but what they proved is that it's completely positive over the integers theorem. And the question is, what can be said about the rank? And they showed that if A is a 2 by 2 integral completely positive matrix, and then we know that it is completely positive over the integers, then ICPR of A is less than or equal to 11. There is an example, is I see that ICPR of 8118 is 9, but the question, if there are matrices with rank equals to 10 or 11, is still an open problem. So again, let me emphasize the correction in the beginning of the slide. The theorem of Laffy and Smigosh is that every 2 by 2 integral completely positive matrix is completely positive over the integers. This is Tom Laffy, and this is Elena Smigosh. And Elena is one of the organizers of the ICLAA meeting in Galway in June. Hopefully, it will be possible to go there in person, but we will have to wait and see. This is again the ICLAA meeting in Galway, June 2022. And then another class that I want to consider is 0-1 matrices. We want to consider completely positive over the set of 0 and 1. A matrix A is completely positive over 0, 1 if it can be decomposed as A equals BB transpose, where B is a 0, 1 matrix. Here, of course, D is I because it has to be 1 matrix of 1. The smallest number of columns in B in such decomposition is called the 0-1 CP rank of A and is denoted by 0-1 CP rank A, 0 CPRA. A is completely if A is completely positive over 0, 1, then of course it is completely positive over the integers, and Z, 0, 1 CPR rank is greater than equal to the Z CPR rank, and again the inequality can be strict. The natural equation is every integral completely positive matrix completely positive over 0, 1. It's not really natural because the only 0, 1 matrix that is can be decomposed over 0, 1 is a direct sum of blocks of ones. So the natural question, okay, let me state it again. I didn't ask if every 0, 1 completely matrix is completely positive over 0, 1, because the only 0, 1 matrices that are CP over 0, 1 are blocks of ones. So the natural question is every integral completely positive matrix completely positive over 0, 1, and there are results of that I have with XU, champion XU. One example shows that AII must be greater than equal to all the entries in the row and in the column. It's symmetric, and also that diagonally dominant integral symmetric non-negative matrices are completely positive over 0, 1. And in this case, we showed that the 0, 1 CP rank of A is a trace of A minus 1/2 of the sum of entries of A. This is XU with its daughter, and I want to mention another set of completely positive matrices, CP01, where 01 is a superscript. Dahlen-Haufmann introduced this set of completely positive matrices. They say that a matrix A that can be written as B transpose, where the entries of B are 0 or 1, and D is positive diagonal real matrix. The entries of D can be any non-negative, any positive real numbers. They call such matrix CP01 matrix. And the set of such matrices is also a closed convex cone and is denoted by CPN with superscript 01. And Dahlen-Haufmann used results of the theory of polyhedral combinatorics of Disa and Loran, and written in the book of Disa and Loran in 1987, and they characterized the CP01 matrix of order less than 5. This is Gal, and Dahlen-Haufmann showed that the integral matrices in CPN01 are the n by n matrices that are completely positive over 0, 1, only if and only if n is small, if and only if n is less than or equal to 4. But this allows them to use the result mentioned in the previous slide to the problem of being of the composition of a 0, 1 for small matrices. Not every integral CP01 is completely positive over 0, 1. For n less than or equal to 4, we know that it is, but for n equal 5, this is an example of a matrix that can be written as 1/2 times a matrix B times B transpose, where B is a non-negative 0, 1 matrix. But the matrix cannot be decomposed as B transpose, where B is 0, 1. And Dahlen-Haufmann proved and extended the result with that I had with XU for the cases n equals 2, 3, and 4, actually they improved the result when n equals 4, because with SU we only proved it for matrices that have a zero entry, and their proof is general. They also proved that if A is a symmetric non-negative integral matrix, such that G of A is triangle free, then A is completely positive over 0, 1, if and only if A is diagonally dominant. So the property of being diagonally dominant is strongly related to the graph of A being diagonal free. And in fact, this is a characterization of triangle free graphs. And if we combine it with the result on the comparison matrix that we had before, we conclude the talk with the following theorem, which puts together the result of Wood, Johnson, and Levy, and Nomi, Shafet Monder, and myself, and Dahl and Hartman, that says that the following properties of the graph G are equivalent. G is triangle free. G contains no triangles. If and only if, for every integral non-negative symmetric matrix realization A of G, A is completely positive over 0, 1, if and only if it is diagonally dominant. And this is equivalent to, for every non-negative symmetric matrix realization A of G, A is completely positive if and only if its comparison matrix is positive semi-definite. So this concludes the talk. Thank you very much. Regards from Haifa.
Balaji, you are muted.
Any questions from the audience, please?
Yeah, it seems Professor Ajit Iqbal Singh has some query.
Yeah. Professor Ajit Iqbal Singh, please go ahead. Professor Ajit Iqbal Singh. Yes, Professor Ajit Iqbal Singh. Professor Ajit Iqbal Singh, please.
He is muted.
Okay.
Yeah.
Sir, I think it's getting time, so shall we start? Shall we start the next talk?
Yeah, we will.
Okay, thank you, Professor Berman, for your wonderful talk. Professor Berman, thank you. I don't know whether
in case he wishes to talk something, let him.
Yeah, please. Professor Berman, thank you.
You want to say something? You are muted.
Thank you. Thank you.
Please.
No, I didn't hear. Were there any questions? If there are,
no.
Otherwise,
there was one hand raised, but finally she didn't turn up.
I couldn't understand you.
Okay, Professor Ajit Iqbal Singh tried to talk, but she couldn't get connected. Anyway, Balaji, you can conclude by saying thanks.
Okay, thank you, Professor Berman. Okay, let us thank the speaker. Okay.
Thank you.
Thank you. Yeah. Can you please leave and then let us start the next talk? Sir, first, I think he has to leave, right?
No, it's all right.
Okay. Okay, thank you, Professor Burman. Okay, so next talk is by Professor K.C. Sivakumar from IIT Madras Mathematics Department. So let me invite Professor Sivakumar to give his talk. Thank you.
Shivakumar, are you on the screen?
So Professor Shivkumar has some internet issue, so he may not be able to. Yes, sir. So with Professor Balaji's permission, we would like to play his recordings.
Yes, yeah, please, please. Yes, please, go ahead.
Oh, he's here. You want to say something? Okay, it is his lecture.
I don't know, some network problem, I don't know.
It appears that he had some network issue and won't join. And we are playing his record.
At the outset, I would like to thank Manjunath Prasad for inviting me to participate in this conference. I hope I'll be able to participate next time in person. So let me share my slides here. Yeah, so the title is Some Generalizations of P Property. P property is known for operators on the space of real symmetric matrices. I'm especially looking at the case when the operator concerned is not necessarily invertible. This is a work in progress, and what I'm presenting are some preliminary results in this direction. What is the motivation? The motivation, main motivation for this talk comes from the property that holds for Z matrices, which are also M matrices but are singular. These are called singular matrices with singular M matrices with property C. Now, singular M matrices with property C have some properties that are analogous to what are satisfied by invertible M matrices. So I am looking at possible extensions of this result for the case of Z operators on the space of real symmetric matrices. So let me first give a motivation to the problem that we are considering. So this first part is almost like a survey are known to arise very frequently in many application problems. For instance, the finite difference approximation of boundary value problems, Leontief input-output economic models, linear complementarity problems, etc. Any such matrix, a matrix whose off-diagonal entries are non-positive, can always be written in the manner Si minus B. So let's call A as a Z matrix. Then A can be written as Si minus B for some real number S and for especially a non-negative matrix B. So A is Si minus B, where B is non-negative, by which I mean all the entries of B are greater than or equal to 0. Now, if there's a relationship between the number S and the matrix B, for instance, if the spectral radius of B rather is less than or equal to the number S, then such a matrix is called an M matrix. And this matrix has been studied in the past about 6 to 8 decades. So this notion was introduced by Minkowski and was further investigated by Ostrowski. They looked at an M matrix with the property that it is strictly diagonally dominant. And so what follows is that it's invertible and that the inverse is non-negative. Inverse has the property that all the entries of the inverse are non-negative. This is the theoretical result, but it has implications to convergence of iterative methods to solve the system Ax equal to B. these have several interesting properties. I'm looking at the non-negativity property of the inverse, which I also mentioned just now. What follows is that by the Perron-Frobenius theorem, if this number S is strictly greater than the spectral radius of B, then A is invertible, and there is this infinite series expansion for the matrix A. And so from this, it follows that A inverse exists, and A inverse has all its entries non-negative. Now, if S is equal to the spectral radius of B, then it's not singular. Just refer to such a matrix as a singular M matrix. I'll give you a couple of examples, but before that, here is a characterization for invertible M matrices. So take a Z matrix, then there are many conditions that are known in the literature that are equivalent to A being an invertible M matrix. The first one is A is a P matrix, by which I mean all the principal minors of A are positive. A is a P matrix is equivalent to saying that the linear complementarity problem defined by the matrix A for any Q has a unique solution. The second statement for a Z matrix to be an invertible M matrix is that it's a semi-positive matrix. Semi-positivity here means that this condition B holds. There exists a positive vector such that AX is also a positive vector. By a positive vector, we mean all coordinates are positive. Of course, we are looking at when this Z matrix is invertible, and so these statements are equivalent to A being an invertible M matrix. I've also included 3 more statements. The next statement is stating that A is monotone. Monotone, this terminology was coined by Collages when he looked at numerical analysis of such matrices and numerical solutions of differential equations. So a matrix A is said to be monotone if AX non-negative implies X non-negative. Irrespective of whether A is a Z matrix or not, it is known that a monotone matrix is invertible and that the inverse is non-negative. And this is equivalent to stating that the equation AX equal to B has a unique solution, has a unique non-negative solution for every non-negative vector B, the requirement vector B. And so this again is equivalent to A inverse being non-negative. I'm stating A inverse I'm stating the next equivalent condition as A being invertible and A inverse non-negative, and also including this one little condition which is equivalent to A inverse being non-negative. This inclusion condition will be referred to a little later also, just to bring a proper perspective to this nomenclature. So A inverse non-negative especially means that A inverse leaves the cone Rn plus invariant. Okay, so A inverse Rn plus is contained in Rn plus. Okay, so let's look at some examples of M matrices. The first one that I'm presenting here is an example of a singular M matrix. Note that it is an M matrix because you can write this matrix as identity minus B, where B is this non-negative matrix. And also observe that the spectral radius of B is 1, and so this is a singular M matrix. We'll come to this example a little later also. Whereas if you look at the next matrix, this is an invertible M matrix. What is the reason? This is a Z matrix, that is clear. And this Z matrix has the property that its row sum is positive, for example. And so by the one of the equivalent statements that I stated just now, it follows that this is an invertible M matrix. Okay, let's get back to the matrix 1 minus 1 minus 1 1, the singular M matrix that I stated before. This matrix comes under what are called as singular M matrices with property C. So here is a general the definition of such a matrix. Again, look at a Z matrix, look at an M matrix. So you have A as Si minus B. If you can make a choice where this S is of course positive, together with the condition that B by S is semi-convergent. So the matrix B by S is semi-convergent here means that limit K tends to infinity, B by S to the K converges to a matrix. it's convergent to a matrix with, of course, with constant entries, then such a matrix will be called an M matrix with property C. Now, such matrices were introduced by Berman and Clemens in their quest to extend results that are known for invertible M matrices, and also to solve problems that they encountered looking at singular M matrices that come from real life applications. If you look at this definition closely, if you observe that for an invertible M matrix, this B by S in fact converges to 0, then it will be clear as to why this is an extension of such a notion. So B by S being semi-convergent extends the fact that B by S is convergent to the 0 matrix in the case of an invertible M matrix. Okay. So the matrix A that we have encountered earlier as well, this is a singular irreducible M matrix with property C. You can actually show that this is equal to Si minus B, where S is strictly greater than 1. You make a choice for S to be greater than 1, then you rewrite it in the manner Si minus B, then one can show that B by S converges to a constant matrix. The limit of this B by S also has some interpretation in terms of the group inverse of the matrix A. Okay, this is an example of an M matrix with property C, whereas the next matrix is not an M matrix with property C, even though it's an M matrix. It doesn't have property C, is not very clear, but if one recalls the equivalent condition for an M matrix to possess property C, then it will be immediate that this is not such a matrix. So what is that equivalent condition? I will state that next. In order to state this condition, one must recall the group inverse of a square matrix. Given a matrix A with possibly complex entries, one looks at a matrix A of the same. One looks at a matrix X as having the same order as the matrix A, asking for X to satisfy these equations. Now, it is known that these equations in general do not have a solution, but if there is a solution, then such a solution must be unique, and such a solution is denoted by A hash. A hash is what is called as a group inverse of the matrix A, and a necessary sufficient condition for the group inverse to exist is that a range of A is the same as a range of A square, or range of A and null space of A are complementary, which is again equivalent to stating that null space of A and null space of A square are the same. Now we can go back and look at the problem of characterizing M matrices with property C. Then this is the result that Berman and Clemens proved. If you take an M matrix, then it can be shown that it possesses property C if and only if the group inverse exists, and that, more importantly, the group inverse is non-negative on the range space of A. So what is the meaning of the group inverse being non-negative on the range space of A? Take those vectors that belong to range space of A that are also non-negative, then the action of A hash on such vectors results in a non-negative vector. So one must look at this as an extension of the condition that Rn plus is invariant under A inverse. This condition should be reinterpreted, rephrased as Rn plus intersection range of A is invariant under A hash, the group inverse of A. Okay, we are looking at possible extensions of the results for both invertible M matrices as well as singular M matrices, namely M matrices with property C, to the case of operators on Sn. In order to be able to do that, we will collect a few preliminary notions. The first one is that of the semi-definite linear complementarity problem. So Sn will denote the vector space of all real symmetric matrices of order n. We use this greater than or equal to 0 condition to denote that W is positive semi-definite. This is the successor relation. If it goes the other way around, then it is negative semi-definite. We will denote Sn plus to be the subset of Sn consisting of all positive semi-definite matrices. Then this Sn plus is what is called as a proper cone. Now Sn can be viewed as a Hilbert space with a trace in a product. Now let's look at the notion of the linear complementarity problem. Fix a symmetric matrix Q and a linear operator L on Sn. Then one looks at the problem X non-negative, Lx plus Q non-negative. Now again, non-negative here is to be interpreted as saying that these are positive semi-definite matrices. So one seeks X to be positive semi-definite, Lx plus Q positive semi-definite together with the condition that the trace of the product is 0. And this is the semi-definite linear complementarity problem. We'll refer to this as SDLCP defined by L and Q. Observe that if X and Y are positive semi-definite matrices and their trace is 0, then this is the same as saying that the product XY itself is 0. This is a necessary and sufficient condition for the trace to be 0, insofar as positive semi-definite matrices are concerned. Okay. In the case of operators on Sn, and especially in the context of solutions, unique solutions of linear SDLCPs, some of the well-known transformations that are studied are given by the Lyapunov transformations, the Stein transformation, and the multiplicative transformation. For our context, we will need the Lyapunov and the Stein operators, and here is the definition. So the Lyapunov, for a fixed matrix A, the Lyapunov operator is AX plus XA transpose, where X is a real symmetric matrix of order n. And the Stein operator is defined as X minus AX A transpose. These two operators have some special property which we will refer to as the Z property. In particular, these will be called as Z transformation. So what exactly is that property? These two operators, if you denote them by L, then L satisfies the following. So this is the condition that L satisfies. If L is either the Stein operator or the Lyapunov operator, X is positive semi-definite, Y is positive semi-definite, the trace is 0, then the trace of the product Lx and Y is also 0. Whenever L is a Stein operator or the Lyapunov operator. This can be thought of as extending the notion of a Z matrix, because note that A is a Z matrix if and only if this implication holds. X non-negative, Y non-negative, the dot product is 0, implies that the dot product of AX and Y is less than or equal to 0. So this is satisfied as equality in the case of these two operators. So one looks at this extension to the case of Sn and refers to an operator satisfying such a condition as the Z property. All right, so thus both these operators could be thought of as extensions of the notion of Z matrix, extension to the case of Sn. Okay, next let's look at the P property extension to the case of operators on Sn. Again, the context is SDLCP. There is an equivalent condition for a matrix to be a P matrix, which is that it satisfies the sign non-reversal property. That is, if you look at X star A, you look at the Hadamard product. This is also a vector. If X star AX is less than or equal to 0, then A is a P matrix if and only if it implies that X is equal to 0. This implication must be true for a matrix A to be a P matrix. So one looks at such an extension of that condition to the case of operators on Sn to give this definition. That X is an Sn, X commutes with Lx, you need this commutativity property for operators on Sn. So if this product is a negative semi-definite negative semi-definite matrix, the only way that can happen is that X is 0. So if L satisfies such a property, then it is called as a P operator. And here is a natural extension of the result for M matrices, invertible M matrices that I stated before, to the case of P operators, especially for the Lyapunov operator, which was proved by Gowda and Song, and the Stein operator, which was proved by Gowda and Parthasarathi. So one must look at this result as an extension of the result for invertible M matrices. I'll also explain why this kind of an interpretation is valid. So for the case of SDLCP, this is what we have. The Lyapunov operator, remember that it's always a Z operator. And so the Lyapunov operator has the P property. This is the same as saying that the operator LA is a semi-positive operator. That is, there exists E positive such that LA is positive. This is also equivalent to stating that the equation LAX equal to Q, whenever Q is positive semi-definite, has a positive semi-definite solution X. In terms of the matrix A, these statements are equivalent to A being positive stable, meaning that all the real parts of the eigenvalues of A are strictly positive. For the Stein operator, we have a similar result, and I think I'll skip this for the moment. However, the condition on the matrix A is that all the eigenvalues of A lie in the open unit disks. That means that spectral radius of A is strictly less than 1. Why are these results analogues of the invertible M matrix theorem? So if you look at the last statement that SAX equal to Q or LAX equal to Q, having a positive definite solution X whenever Q is positive is the same as showing, it's equivalent to showing that L is invertible and that L inverse Sn plus is contained in Sn plus. So Sn plus is left invariant by the operator L inverse, where L is a Z operator, and that is the reason why we are looking at these as generalizations of the results for invertible M matrices to the case of operators on Sn. Of course, in this case, the SDLCP has a unique solution for every symmetric matrix Q. Before looking at extensions of the M matrix with property C case to the case of operators on Sn, one must observe that the Stein transformation indeed looks like a Z matrix, because the Stein transformation can be written as I minus MA, where MA is the so-called multiplication operator which satisfies the condition that it leaves Sn plus invariant. So MA could be thought of as a non-negative operator, and we have written SA as I minus MA. However, this kind of a representation is not true for the Lyapunov operator, and I have given an example to illustrate that fact. So if you take A to be this matrix 0, 1, minus 1, 0, then the Lyapunov operator LA of X is given in this manner. And if LA can be written as I minus B, where B is a non-negative operator, then Bx has this formula in terms of the matrix X, which is symmetric. Then one can easily verify that this positive semi-definite matrix U is taken to BU, which is not positive semi-definite, and so B is not a non-negative operator. However, it is known that if T is a Z operator on Sn, then T can be written as a limit of a sequence Tk, where each Tk can be written as alpha Ki minus Bk, where Bk is a non-negative operator. So this case of Lyapunov operator is a little more subtle than the case of a Stein operator, which has an immediate analog, for instance, to the case of a Z matrix representation wise. All right. In order to obtain extensions of the results for P operators to the case of singular operators, one looks at a notion called P hash operator. The reason for the notation hash will be clear in the next slide. So what is a P hash operator? Look at the definition for a P operator. Ask the X not to be varying over the whole of Sn, but only restricted to the range space of the operator L. Then the revised implication gives you the definition for a P hash operator. So X belongs to the range of T, X and Tx commute, and the product XTX is negative semi-indefinite, holds only for the case of the 0 matrix X. Then such an operator is called a P hash operator. What are some examples? Look at the matrix A, a simple example here. Then one can show that both LA as well as SA are P hash operators. Whereas if you look at the matrix B, then LB is a p-hash operator, whereas SB is not a p-hash operator. Why is it not a p-hash operator? One way of looking at why this is not a p-hash operator comes from the next slide, which gives a necessary condition for an operator to be a p-hash operator. But first look at this statement A, which states that if L is a p-hash operator, then L hash, the group inverse exists, and the group inverse also has the p-hash property. The second condition statement rather is if LA is a p-hash operator, then LA hash exists, of course, by the first part, but it also implies that the group inverse of A exists. Whereas for the case of the Stein operator, the group inverse of I minus A exists. And so if you go back to this example of B, one can show that I minus B is an nilpotent operator, and so it does not have group inverse. For the case of a p-hash operator, one can ask when a rank 1 operator is a p-hash operator, and here we have a result, a necessary condition, necessary and sufficient condition for a rank 1 operator to be a p-hash operator is that if the operator L is defined by means of the matrices U and V in this manner, then L is a p-hash operator if and only if the trace of the product UV is non-negative. Remember that there cannot be any counterpart of such a result for the case of P operators because P operators are invertible. We have now come to the part where we are looking at natural analogues of the case of the Lyapunov operator and the Stein operator when the matrix under consideration are either positive stable or Schur stable. We are looking at non-negative stable as well as generalized Schur stable. So I'll look at first the Stein operator case. For the Stein operator, I'm calling these as singular analogues for obvious reasons. We are looking at the group inverse of the operators under consideration. Take the Stein operator, assume that the group inverse exists. Now this will impose some condition, of course, on A, which is that I minus A hash, the group inverse of I minus A hash exists. The group inverse of I minus A exists. So if SA has the group inverse, then a necessary and sufficient condition for SA to have the p-hash property is that the spectral radius is less than or equal to 1. Spectral radius of A is less than or equal to 1. A special instance when the group inverse of SA exists is that when A is idempotent. So when A is idempotent, what follows immediately is that SA is also idempotent, in which case the group inverse of SA is itself. And so one has a property that is similar to the property for matrices that have property C. M matrices having a property C, we have an analog of such a property, which is that we are referring to that property as a range monotonicity property. The range monotonicity property is given here. Especially this is equivalent to the property that SA hash is non-negative on its range space. All right, so this is an analog, an extension of the necessary and sufficient condition for a singular M matrix to possess property C. This is for the case of the Stein operator. We also have a result for the Lyapunov operator. Again, we are looking at the situation of the Lyapunov operator when the group inverse of such an operator exists. Then one can characterize the p-hash property of LA to A being semi-positive stable. And the situation when this can be applied is given by the instance when A satisfies the conditions that it is both Q-symmetric, of course, of even order, as well as A square equal to minus I. In this case, LA is, of course, a singular p-hash operator because identity belongs to the kernel of LA. And LA turns out to be trivially range monotone. Trivially range monotone here means that if X is a positive semi-definite matrix belonging to the range of L of A, then L of A hash of such a matrix X is equal to 0. So this is what we call as a trivial range monotonicity. And this is, one can think of this as a possible extension of the result for singular M matrices with property C for the case of the Lyapunov operator. Now, this is an ongoing work, and so we expect more results to come out of this work. With this, I would like to stop my talk. Thanks a lot, Manjunath, once again. Let me just give you the references. Gowda Song, Gowda Pathasarathi. These two papers concern the linear complementarity problem connection to P property. Jayaraman, Kavita Bish, myself, which is the extension of P property to the case of P hash operators. Some preliminary results were obtained in this paper. And also Tau's paper, which contains WP properties for linear transformations. There are connections between WP properties and P hash operators, which I had stated in my abstract, but I did not have the time to present here. Thank you for the attention. I am ready for questions.
Okay, let me thank Professor K.C. Sivakumar for this excellent talk. Is there any question, please, from the audience? Audience, any question? Participants, is there any? Yeah, anybody who is raising the hand? So, who is that? Professor Prasad? No. Anybody who wants to ask some question?
Any questions, sir?
Okay, then we will thank the speaker for the excellent talk. So, okay, thank you. Prasad.
Thank you, Professor Balaji, for chairing the session.
Yeah, thank you. Yeah.
I also thank Professor Burman and Professor Keshav Kumar for delivering the lecture. So if there are any questions regarding this session, please send it to Karam's mail. We will communicate it with the speaker. Now we shall have a short break. So we will be joining back exactly at 5:20.
Hi, Manjunath. I'm not able to hear you.
Let me unmute. Yes.
Yeah, I am able to join.
You're back. Okay. Then, anyway, we managed because of your recorded talk.
Okay.
Hopefully, if anybody like to ask something, they will mail you.
Okay, fine. Yeah. See, I do not know what happened here. So if this problem persists tomorrow, then it will be difficult for me to chair that session.
Yeah, I can understand.
Yeah, I've sent a mail just now.
Yeah, I saw the mail. At that same time, I saw you.
Okay. Oh, I just thought I'll try again and it
Okay,
worked.
you try tomorrow. In case you don't turn up, I'll ask somebody to be ready.
Okay, fine. Yeah. So good work, Manjunath.
Don't know.
It's good. You're able to organize this so frequently and also getting
yeah, maybe
so
the
many
last one.
to participate. Why? You will still be there, right, with Karams? So.
Yeah, I'll be there around, but tired enough.
Of course, yeah. Finance will be a big problem, right?
That is also an issue.
Okay. So who are
this time we are managing without any financial support. Only National Medical Council that supported one foreigner. They don't. That money cannot be used for somebody else. Either foreigner or NRI members can utilize that amount for their local hospitality and local travel.
I see. Okay.
So apart from that, there is no other support. So I'm managing with my Kerams fund.
I see. Okay.
Some amount that is available in my matrix fund and other things are little for that thing. This thing I am using it and
yeah. Difficult to pull in money.
At the same time, I am not hosting too many here. No, that's how I could manage.
Yeah. So it has helped some of us not coming there.
Yeah, most of the cases it is waived off. It is not only 40-50 members have paid registration. That is nominal one, and that is not enough even for food for volunteers.
I know. Yeah. Okay. So tomorrow morning I'll try and join. If it works, fine. Otherwise, just keep someone as a staff.
Okay. Fine.
Yeah. Thanks a lot, Manjunath.
Okay. Bye. Stan is delivering a lecture. You can join at that time.
Professor Ramesh C., we invite Professor T.S. Raghavan to deliver a lecture on computational game theory.
Main idea is to give the introduction to game theory and show some examples where it's being applied and how it is related to matrices. And the more importantly, how one can actually compute what you are really looking for. That's also very important. I have to tell you the story of my own way, how I entered into game theory. I joined the Indian Statistical Institute as a PhD student in 1962. And Professor C.R. Rao told me, first 3 years, don't do anything, be studying. Okay. But anyway, I was previously in my MSc in statistics from Presidency College, I was interested in Wald's statistical decision functions. Abraham Wald, the famous statistician, tried to view the whole subject of statistics as a game between nature and statistician. Nature tries to hide the information. Statistician wants to extract the information. Nature is not fully willing to reveal what its true state is. All it does is it allows you to spy on itself. So think of this as the following. I don't know what is the average height of students in the campus. Okay? That average height is some unique number. So what you are allowed to do is you are allowed to spy on the true number by collecting random observations. So I collect say 10 observations and I get the average height from those 10 observations and think of this as my guess of the true value. You got me? The average height of the whole campus can be quite different from what I am getting from this particular sample. If I change a sample, I may get a different answer. So from sample to sample, it's going to be different. And so your issue is, what is the best way to estimate the true value? So that is the game which is being played. And Wald said, if theta is the true value, theta is the true value, the true average height. Theta hat is spied value based on a sample, on a random sample. Based on a random sample. So, nature said, he viewed, if you take theta hat minus theta square, that is the penalty which the statistician pays to nature. Think of nature as another person, statistician as a second person, nature as first person. The first person is hiding the information theta. The second person is trying to guess the theta value based on a sample, random sample. And once he guesses it as theta hat, this will vary from sample to sample. If some other person took another sample of size 10, it will be a different number. Each time it will be a different number. So this itself is what I call a random variable. Agree? So it's when I take this thing and its expectation, its average, and that is what I call I call it as a risk function. This is called the risk function. So if theta is the true value, theta hat is the procedure by which you get the estimate, and there is a risk involved, and that is measured by this number. So one person the statistician wants to make it as small as possible. Nature wants to make it as large as possible by hiding the information theta. So this is the approach which Abraham Wald took to reduce every statistical problem, every statistical procedure as purely a game. So he achieved significant progress and showed whatever is our intuitive solution which we get is the same as this solution, effectively. So this was something very inspiring for me. So I said I'm going to work on statistical decision functions. So I took the book of Abraham Wald on statistical decision functions. And then the second chapter is called zero-sum two-person games. Okay? You have two players, and now he quit entire statistics. He concentrated mainly on the study of zero-sum two-person games. And when he came to that, myself and my colleague T. Parthasarathy, we were studying paper after paper, everything. And then I realized we couldn't fully grasp that level of mathematics. It had deep topological statements which, with our background, we couldn't follow. So we were struggling, and we were blessed with three outstanding probabilists. One was V.S. Varadarajan, another person was S.R.S. Varadan, and the third person was K.R. Parthasarathy. Varadarajan had come just from US. He was itching to get good students to work in his area. And Varadan was finishing his PhD thesis just at that time. As you know, Varadan is perhaps the most outstanding living probabilist now. No one is anywhere close to Varadan. And so he was just finishing his thesis, and he was going to teach everything, all basic mathematics like metric spaces, topology, analysis, everything. And Varadarajan was also teaching many of the subjects, especially on Hilbert space, etc. That's how we got deeply into the right direction. But then there was a short paper which we could understand, and this paper is by one Kaplansky, Irving Kaplansky. It's called A Contribution to the Theory of Games. It's a just 5-page paper written purely based on matrix theory. Purely based on matrix theory. And even to this day, its appeal is phenomenal for us. It's remarkable, actually. It's a remarkable paper of 5 pages. And then we decided that I'm not going to work anymore in the statistics side. I'm going to work only on the game theory side. That's how I entered game theory. Okay? But the true inspiration was this paper work. I will come to it when I formally discuss the game theory part. And then, little later, only after finishing the PhD, in my PhD area at that time, Varadarajan was a very great inspiration in analysis. He was, and K.R. Parsarthi was giving lectures on Markov chains, okay, in matrices. So we kind of appreciated that matrix theory is sitting at the center of many of them. And whatever you do in matrices, you extend it to the infinite dimension, you are at the functional analysis, nothing more. Okay? So the spirit of it is seen only in matrix theory. So it's, for a while, that was our initial inspiration. And slowly I also realized when we were studying papers after papers, we faced some special problems. And one of the problems is the following. I just give the example. Here is a balloon, and two guys are walking towards the balloon. Two guys are walking towards the balloon. The one, I mean, the closer a person goes to the balloon, he has greater accuracy. You follow me? See, when you go closer to the balloon, to hit the balloon, you have greater accuracy. Suppose each one has one pebble in his hand. So there are two players. One has one pebble. Two also has one pebble. Two also has one pebble. So with this pebble, you try to hit the balloon. So when I go closer, my accuracy is higher. Agree? Then, so now the question is, the one who hits the balloon wins. Wins 1 rupee from the opponent. Okay? Now look at this problem in two ways. First is, what is the accuracy? You need to define what is the accuracy. So a simple function can explain that accuracy. For example, if I travel a distance x, and assume that this whole distance is 1 unit. 1 unit. If I travel a distance x, my accuracy is x. The probability of hitting this is x. If I travel half the distance, my accuracy to hit the balloon is half. If I travel 3/4 the distance, my accuracy is 3/4. If I travel the whole distance, I'm sure to hit the balloon. Agree? This is for me. For the opponent, this is for x, for player 1, y for player 2. Y for player 2. So now the thing is, suppose x is less than y. X is less than y. What does it mean? Player 1 wants to use the pebble slightly before player 2. Agreed? But they are not talking to each other. You remember? They are not talking to each other. I am only writing it as though a third person is watching it. Okay? So a third person has been informed by the two players. Player 1 says, I am going to hit at the point x. I will travel a distance x and hit. Player 2 says, I will travel a distance y and hit. Now the third person knows this, x is less than y. Neither one of the players know. Lack of information is very critical in all game theoretic analysis. Okay. Now, if he hits, he's going to win 1 rupee. Agree? So the chance he hits is x. With probability x, he makes 1 rupee. Okay? With probability 1 minus x, he will not hit. Agreed? With probability 1 minus x, he will not hit. Now, this pebble or the stone can be of two types. One visible, another invisible. Suppose it is a visible stone and you are watching the opponent and he lost it. Now you are player 2. You know already he has lost his pebble. Agreed? So what should you as player 2 do? Even though you plan to use the pebble at Y, why should you? You could as well go closer and hit the balloon. Agreed? So, with probability 1 minus x, once this fellow fails, the other fellow is sure to hit the balloon by going closer to the thing. So, with probability 1 minus x times 1, player 1 will lose 1 rupee. Agreed? So, I can write it as a function kxy as 1 times x plus minus 1 times 1 minus x, which is 1 minus, 2x minus 1, when x is less than y. This is only when x is less than y. It doesn't depend on, as long as x is less than y, for all such y's it's the same number. So similarly you can write down the expression for various things, and then if it is a visible thing, common sense says they both should shoot from the center at half the distance. That's the best strategy for both players. So it's such a small thing it's a very simple problem, but it can go quite technical. Now, if it is invisible, this function will be a more complex function. And then this was the thing which was interesting to me, and as a student. So I went through a famous paper of Schiffman, and I realized it is tied to the theory of positive operators. It led to the theory of positive operators. I didn't know the head or tail of that. So then I realized that there should be I talked to Professor Varadarajan. He said, why don't you study non-negative matrices? It seems related to that. That was his simple suggestion. And that's how I got into this non-negative matrices, the study of non-negative matrices. And it was triggered by this example. Very often, you really do not know, even if you're a PhD student, you don't know where your problem is going to be. It could come from any strange place. It's something which triggers you, something which tickles you. So you need to look for that tickling thing. Not by going through paper after paper, but when you go, suddenly you will find something very inspiring. And you go deep into it, you grind it, then you have all the skill to do it. You go around that topic and learn more and more. So that's what I used to do in ISI. And then there we had a good system. The students, the PhD students, they were imposed to give seminars. You have to give seminars. And one day Varadarajan simply said, I don't know what is a convex set, I said. And then he said, from next week onwards, you are giving a course of lectures on convex sets. There were no proper books also at that time. And then the other students, graduate students will sit and they have the freedom to ask you, toss you, tear you to pieces. And that advantage is there when you are in a group of similar people. That was the thing which helped me. Okay, helped me. And that's how you add up. you realize that convex sets are related to game theory. You slowly realize these connections. It's a slow process, always. It's a slow process. And that's how I came also into non-negative matrices. And I realized many connections to all of them lead to deep theorems in functional analysis. Many deep theorems in functional analysis. I used to lecture for a whole year. Every week, one seminar, and then it will take a whole week to prepare for the next seminar as a student. So I knew exactly theorem 2.1 is what, 3.1 is what, like that. It used to be like that. But anyway, so those were the things which kind of led me to get properly into game theory. And then I started seeing them that those theorems can be proved by game theory. Many of those theorems of Krein and Rootman and all of them can be proved by game theory. I slowly recognized them. That was part of my thesis activity. Then I immediately went to England to give lectures as a lecturer at the University of Essex. There I was given the task of teaching linear programming. I have never learned linear programming before. I knew nothing. I knew how to, if I have given a problem, it was always grinding, but there was no formal way of solving a problem. I didn't know. So I struggled through by teaching the course. By teaching the course, I struggled through. So then I started respecting the computational side of this field. Almost all these fields, the computational side for a long time was neglected. Within even game theory, there are more theorems, there are more theories, but fewer computational tools for a long time. And while they were emerging, computer science also became a part of mathematics. It wasn't recognized fully as part of mathematics by regular mathematicians. They were not willing to even accept probability as part of mathematics, pure mathematicians. So that was the struggle which was going through. And finally, the computer science and its usefulness has wiped out, has told the people that here is something which is quite deep and useful, and you better learn this field. Okay? The same way, even game theory, for a long time, was considered purely as an esoteric mathematical kind of tool, and the economists who were supposed to use it didn't care much about it for a long time. But it all came into an important place when auctions were developed. How to develop good auctions. That led to understanding the so-called Nash equilibria in game theory. I'm going to talk about all of them formally, but I'm just telling. It was auction theory which triggered all economists to get into game theory. If you take any worthy economics department anywhere in US, you will have a sizable number of game theorists sitting there. They may be doing game theory, but may put it in the language of economics. The whole microeconomic theory is written in the language of game theory. And then the same way, the biologists, what is called evolutionary biology. And that's also another place where game theory enters. And the third one is what is called ethical way of dividing and cooperation. And that is another area which also is an important area. Now let me start with a few slides. Okay. So for example, in a business school where I taught something, what modern business is not just outsmarting competition, market share, fighting back, beating opponents, locking customers. All these things are not good strategies. Listen to customers, work with suppliers. With a lack of cooperation, you can lose all you made for. So you need cooperation is also an important aspect of playing games. See, what is a game? Game means a bunch of people, they follow certain rules and then they are acting according to the rules. It's a business, one such. So you're dealing with customers as well as suppliers, etc. For example, US Airlines lost all the profits made until 1990 during this period in a tough price war. So when you go on a price war, one can lose. Okay. You succeed only when others also succeed, is the theme. Our scriptures say, Sarve janaste sukhino bhavantu, samasta san mangalani santu. In other words, let all people live in happiness, let there be peace all around. Okay. So what is business then? For example, why am I talking about all these things? It's also tied to the game theory. That's the reason. It's just like running a good family. Parents and children cooperate to create the best pie. They fight and compete to share the fruits of cooperation. In a sense, modern game theory can as well be dubbed co-opetition. That means there is a cooperation and competition. Okay. Players in business are both Mr. Jekyll and Mr. Hyde. There is a Tamil song, Konjam Nilavu, Konjam Niruppu, Konjam Mirugam, Konjam Kadavul. That means sometimes she is cool as a moon, sometimes ferocious as fire. Sometimes she is an animal, at other times she is an angel. Okay, so that's the kind of thing. Okay, where is game theory applied? Winning elections, resolving legal disputes, apportioning environmental costs, measuring the importance of factors that contribute to the spread of diseases, choosing one's mates. The most recent work of my PhD student is on studying choosing mates. Okay, and maybe I could choose that one first to give an idea. Okay, how something can be very recent, it's tied to the matrix theory, and at the same time it is quite difficult. Let me start with that one, because I am only trying to motivate where game theory is found. Okay, suppose there are, say, 5 girls. Call them as G1, G2, G3, G4, G5. There are 5 boys, B1, B2, B3, B4, B5. I'm going to fill up this with a matrix of only zeros and ones. Okay? If I put a 1, it means the girl 1 likes boy 1 and boy 1 also likes girl 1. Assume they are all of the marriageable age. Assume they are all of the marriageable age. G1, B1, if I put 1, which means the girl 1 and boy 1, they like each other. If I put 0, this means sometimes both of them don't like each other. Sometimes it may be a one-way traffic. Okay, the boy may like the girl, but the girl may not care for the boy. So in which case I put a 0. Agreed? So I fill up this whole thing with 0, 1, 1, 0, 1, 1, 1. Okay. I have filled up this with a 0, 1 matrix. Okay? Now, what is the maximum number of marriages that can take place? 5? So can you suggest one such? Along the diagonal, G1 likes B1, G2 likes B2, G5 likes B5. Okay? So this part is clear. So the coalitional, what I call as, for the society, the maximum number of marriages possible is 5. Agreed. Because there are only 5 people and they are able to also find correct mates. Okay. Now, the next step is the critical step. G1 and B1 are married. Let me make it this way, for example. Suppose, change it to this, okay? G1 and B1 are married. G2 and B2 are married, etc. Now, G1 and B1 as a family, I want to measure who is the dominant person. Is G1 the dominant person or B1 the dominant person? Huh? B1 or G1? B1. Why B1 is the dominant person? He has more choices. Okay, he has more choices. Whereas G1, if she doesn't get married to this guy, she has to remain a spinster for the rest of her life. That's the situation. So G1 and B1, when you say, G1 is the dominant person. Its dominant is just ranking now. Agreed? But I want to measure exactly. Suppose their whole power is 1 unit. What is the relative power of B1 and what is the relative power of G1 in this? One has to have some measure. How to measure that is also part of game theory. Okay? And my most recent PhD student, John Hadwick, his thesis was on a very efficient algorithm to measure the relative power of the married couple. Who is stronger of the two? It doesn't necessarily mean this one is 3 and this one is 1. It is not like 1/3, 1/4, 3/4 like that. It's much more complex than that. How to do this one? Okay, and this is what is called study of cooperative game theory. It's called cooperative game theory. And in this sense, here I'm writing it as purely matrix, etc. A more general situation is what is called the so-called marriage problem. Okay, and I can get into it, but it will be, I have to do it a little later. Right now I have to postpone it. In fact, it was a marriage problem which won Nobel Prize for Lloyd Shapley and Alvin Roth. Only in 2012 they won the Nobel Prize in economics for their work. It is a 3-page paper in American Mathematical Monthly. I can tell you that much. So the fundamental work is always, it takes a while to be recognized. Let me see what I have, the next one. What is it? Oh. Is it the one? Okay. Now I am starting with something quite formal. Okay? There are, when game theory was studied, it was studied with no secrecy. People are playing this game. What is the game? You have 4 baskets Agreed? The first basket has 69 apples. The second one has 54 apples, 18 apples, 46 apples. Okay? There are two players. There are two players. Player 1 can choose any of this basket and remove at least one. He has to remove at least one, and also even the entire thing. You can even empty the whole basket, but at least one you must remove. Then once player 1 has done it, then it is 2's turn. You follow me? 2 has to remove at least one or whatever he wants. But each time the choice is only from one basket. This game continues till all the baskets are empty. The one who is responsible for emptying the very last basket, all the other baskets were empty. There was one basket which had some. The one who was responsible for emptying the very last basket is the winner of the game. Follow me? The winner of the game. So, this was studied as a paper in the most prestigious journal of those in mathematics. Any mathematician will agree, Annals of Mathematics is the journal. In Annals of Mathematics, even before game theory was actually formally developed, this guy studied this game and gave a beautiful solution. I talk about this in all
Welcome back, everyone. So in session 5, we have a invited talk from Professor Rafiqul Alam. Professor is from Indian Institute of Technology, Guwahati. He is very much interested in the field of linear and numerical linear algebra and spectral perturbation theory. He was awarded as Boyce Cast Fellowship from DST, Government of India, and he is a visiting fellow from TIFR Bangalore. Today he will be delivering a talk on a trace moment based method for solving holomorphic eigenvalue problems. Welcome, Professor. To chair this session, I request Professor Ramesha C. from Manipal Institute of Technology, Mahi, Manipal. Over to you, sir.
Thank you, Raksha. I'm happy to get associated with this lecture by Professor Rafiqul Alam of Indian Institute of Technology, Guwahati. He'll be speaking on the topic, a trace moment-based method for solving holomorphic eigenvalue problems. Now let us start the session. I invite Professor Rafiqul Alam to start his lecture. Manjunath, do you want to speak anything?
Nothing. Whether Professor Alam is there?
Yes, I am here.
Okay, I didn't see you. Okay. Oh, okay. You are with your camera off. Okay.
Yeah, my camera is off.
I just want to say welcome to you.
Yeah. Okay, I'm here.
Okay.
Okay.
How are you?
Yeah, fine. Fine.
So, with your permission, your recorded talk will be played.
Yes, sure. Yeah, please.
Raksha, please.
Good morning. At the outset, I would like to thank the organizer for inviting me to deliver this lecture. And special thanks to Professor Prasad. Professor Prasad, thanks for everything. The main topic of my lecture is nonlinear eigenvalue problems. More specifically, I'll present a method for solving holomorphic eigenvalue problems. This is a joint work with my PhD student, Algebra. Okay, so let me start with a special case. So I'll consider linear eigenvalue problems. So given two matrices A and B, square n-bind square matrix are given. So then I can consider two eigenvalue problems. So this first one, this is called the standard eigenvalue problem. Okay. And the second one is generalized eigenvalue. So these linear eigenvalue problems have been studied extensively. Its theory is well understood. And there are robust numerical methods for solving these problems. So the standard methods used for solving this linear eigenvalue problems were lambda here approach is this. You choose a solution of this form, okay, in terms of exponential. So this is V is a vector, which is unknown, and lambda is a scalar. If I put this solution in this equation, that will immediately give me this eigenvalue problem. Okay. So if we can find this scalar lambda here, if you can find lambda and this vector V, non-zero vector V, then we'll have a solution. Okay. So in this particular case, this T lambda here, this is the function that I have, matrix valued function. So this is holomorphic. This is one example where we have holomorphic eigenvalue problem. And there are many applications where we encounter this general holomorphic eigenvalue problem. So MATLAB toolbox, this NLEVP, has a very good collection of nonlinear eigenvalue problems for they have collected it from various applications. So with this motivation, let me formulate the problem. So I'll consider here T, okay, given this U simply connected domain, I'll consider T to be a function from U to the set of all n by n matrices. So this is T is basically a holomorphic matrix valued function. I'll assume that this is regular. Regular means that this determinant, okay, there is at least some complex number lambda in the domain U such that this is non-zero. So this is invertible matrix. And then our task is to find lambda from U and a non-zero vector V such that this happens. Okay. So this system is basically we have to solve. This is our holomorphic eigenvalue problem. The spectrum of T lambda, I'll denote by this sigma T. Okay, so this is collection of all complex number from U such that this determinant equal to 0. So given this, I can define algebraic multiplicity of an eigenvalue. So mu is an eigenvalue. Then the multiplicity of mu is the multiplicity of 0 as multiplicity of mu as a 0 of this analytic functions. Okay, so that's the algebraic multiplicity. And geometric multiplicity is usual, the dimension of the null space. All right. So what is our main task? Our main task is to find eigenvalues, eigenvectors of T lambda. The main difficulty here is that a Schur-like decomposition does not exist for this nonlinear eigenvalue problem, T lambda. And therefore, development of a robust numerical method for solving nonlinear eigenvalue problem becomes a challenging task. Okay. So there are many methods have been proposed over the years. This is still, this is a very active area of research and methods are still evolving. I'll particularly mention one method, which is based on contour integration. This contour integration based methods have become very popular now. So I'll particularly mention one method because the method that I'm going to describe takes some of the ideas from here. So in a nutshell, I can describe the method proposed by Bain and also slightly a different method, but essentially ideas are the same by this Sakurai method. Okay. So here, suppose gamma is a simple rectifiable closed curve. Okay. So gamma will be a curve here in the domain. And suppose it encloses some eigenvalues. These are the eigenvalues. Okay. And then given such a curve gamma, I'll consider this matrix moments. Okay. Take this for p equal to 0, 1, and so on. These moments we calculate. And then consider this block Hankel pencil. Okay. So this is the Hankel matrix. This is Hankel matrix. And this is called shifted Hankel matrix. So this Hankel matrix has a property that its rank, okay, is always less than equal to m. M is the total algebraic multiplicity of the eigenvalues inside this curve gamma. So this is my curve gamma. And if m is the total multiplicity, then the rank of this Hankel matrix is always less than equal to m for all k. So the main task is you find k, the smallest k, for which rank is exactly equal to m. Okay, the rank, and that's a difficult task to find. Determine this m. Nevertheless, one can follow trial and error method and then calculate that. So once this k is determined, so this is called minimality index, then one can show that the finite eigenvalues of this pencil, as I've already mentioned, a pencil can have infinite eigenvalues, infinity can be an eigenvalue, and in this particular case for this Henkel pencil, infinity is always an eigenvalue. So the finite eigenvalues of this pencil are precisely the eigenvalues which are sitting inside this curve gamma. Okay, but this pencil is never solved for eigenvalues. So it is further, this infinity eigenvalues are deflated, and in fact this pencil can be reduced to standard eigenvalue problem through singular value decomposition. One can consider singular value decomposition of this matrix and then do some operations, and then infinity, this eigenvalue problem can be reduced to a simple eigenvalue problem, this standard eigenvalue problem. Okay, so this is the method that has become quite popular now. So I'll present a new method which will be true not only for this matrix holomorphic eigenvalue problem, but for infinite dimensional problem. Okay, so now I'll switch to infinite dimension. So this is my notation. X is a complex Banach space, and Lx is the Banach space of all bounded linear operators. So I'll consider this operator valued holomorphic function. W is, I'm taking a using a new notation instead of T. So this W is a holomorphic function from omega. So this omega is a simply connected domain. So consider this holomorphic operator valued function. Okay. So I'll define its spectrum as before. Spectrum of W is equal to collect all those lambda for which this is not invertible. And the resolvent set is the complement of sigma in this set omega. So that's the resolvent set. So this will be my standing assumption that W lambda, this is always regular. Okay, means its resolvent set is non-empty. So there will be some lambda in the domain where this W lambda is inverted. Okay, so this assumption I need to make. Okay, so next, the method that I'm going to propose, okay, that will work only for discrete eigenvalues. Okay, the spectrum of this W can be very complicated set, so we'll concentrate only on discrete eigenvalues. So the discrete eigenvalues, the definition of discrete eigenvalues is this. So I'll take this as definition. So mu is an eigenvalue. That means this W mu will have non-trivial null space. So if mu is an eigenvalue, then you say that this is discrete. Okay, this is discrete. If mu is an isolated point of the spectrum and W mu is a Fredholm operator. Okay, that means the null space has finite dimension, the range space is closed, and the dimension of this quotient space has finite dimension. Okay. So there are other ways to define discrete eigenvalues, but I'll consider this. And its various properties and characterization, for example, can be found here. It's very simple. And set of all discrete eigenvalues, I'll denote by this set. Okay, so this is the discrete spectrum. So for the rest of my talk, I'll always assume that the operator valued function W, it has discrete spectrum is non-empty, and I'll always assume that the discrete eigenvalues are isolated from the rest of the spectrum by some simple closed curve gamma. So I'll choose a curve gamma. Okay, it will be simple, closed, rectifiable, positively oriented, and so on. Okay, and it will contain only discrete eigenvalues of the operator valued function W lambda. So that will be my assumption also. Okay, so next I need to define algebraic multiplicity. The standard definition of algebraic multiplicity for an operator, okay, is through spectral projection, which we cannot use. So this is this theorem can be used to define algebraic multiplicity of a discrete eigenvalue of W. So this theorem was proved by Goldberg and Siegel. So here the assumption is that the screen is getting blocked. Okay. Right. So this is actually this right hand side. You see, this is an operator analog of argument principle that you know for analytic functions. So number of zeros of analytic function inside a curve gamma that is given by argument principle, and this is just the operator analog of the argument principle. Okay, so this is the curve gamma. So assuming that mu is only a discrete eigenvalue inside this curve gamma, and then gamma will always assume that this is a subset of the resolvent, so that this inverse always exists. And then we can calculate this, and the trace you take outside because this operator need not be trace class. However, after taking these integrations, we'll have a finite rank operator for discrete eigenvalue. So this is algebraic multiplicity. All right. So if I take a special case, so suppose A is a bounded linear operator, and W lambda is lambda I minus A. So this corresponds to standard eigenvalue problem. So then if you look at this one is just equal to this, which is just the definition of spectral projection, right? And so the trace of this, okay, is just the rank of P, and which is the definition of algebraic multiplicity of a discrete eigenvalue of a bounded linear operator A. Okay, so we have this. So this is a generalization of this idea. Okay, so with this much preparation, now I am ready to present our first result. So again, I'll assume that this is the set consisting of discrete eigenvalues. Okay, so this is the set sits inside this curve gamma. So int means this, this is the curve gamma, right? This is the curve gamma. By int gamma, I mean that the region enclosed by this curve gamma, right? So the sigma is sitting inside here, and the rest of the spectrum, sitting outside. Okay. And so this is spectrum of W minus this. So that's my assumption. Okay, and the total algebraic multiplicity. So let M be the total algebraic multiplicity of the eigenvalues inside this set. Okay. And I'll denote by this mean sigma, that's the arithmetic mean or weighted mean. So weighted by the individual eigenvalues, their algebraic multiplicities. Or you count the eigenvalues in sigma, okay, according to their algebraic multiplicities, and then take the mean. So that's the arithmetic mean. This is the weighted average of the eigenvalues in sigma. Okay, so sigma can be a set, lambda 1, so these are the eigenvalues, and take corresponding multiplicities will be there, and then we multiply by this column. This is M1, that's the multiplicity, ML, the multiplicity of this. So this I'll add M1 lambda 1 plus M2 lambda 2 and so on, and then divide by M1 plus M2 and so on. So that's the weighted average. So this weighted this mean of this eigenvalue, it has this integral representation. Okay, this is the representation. And this one, I can write this without calculating this way. I can simply, this is computationally better. So you calculate the ratio, and that will give the mean. So without knowing the eigenvalues, through this integration, we can calculate the mean. So if we can approximate this integral by some quadrature, right, so that will give an approximation of the mean of the eigenvalues in sigma. Okay, so this is the mean of the eigenvalues, but in order to calculate individual eigenvalues, we still have to do some work. So I'll define a symmetric bilinear form. Okay, this is the ring of polynomials. So a symmetric bilinear form, I'll define here phi and psi. These are two polynomials. So I'll define, the right hand side is given here. So this one can easily see that this is a symmetric bilinear form. And as I've said, that this curve gamma always contains the discrete eigenvalues of W. That's my standing assumption. So this is a symmetric bilinear form. So with this new notation, so I'll call this is a scalar product. And with this new notation, the multiplicity of the total algebraic multiplicity of sigma can be written as the scalar product of 1 with 1. And the mean of the eigenvalues is basically the ratio of the scalar product. Okay. So now I want to use the scalar product to define a formal orthogonal polynomial. Okay. A monic polynomial of degree L is called a formal orthogonal polynomial, or simply FOP, if this is orthogonal to all these monomials of degree up to L minus 1. In other words, this file is orthogonal to the subspace of polynomials of degree up to L minus 1. So this is a formal orthogonal polynomial, and it will be clear why I'm defining this formal orthogonal polynomial. So one question is whether this orthogonal polynomial exists, and if it exists, how to utilize it. So this is the main theorem. The main theorem is this. So suppose sigma consists of L distinct eigenvalues, lambda 1, lambda 2, lambda L, and Nj is the multiplicity of the eigenvalue lambda. Okay. Then I define trace moment. So the title of my talk says the trace moment. So this is the trace moment. Okay. So SP, the pth order moment, is just the scalar product of 1 with z to the power p. That's the trace moment. Okay. So I'll define this. All right. So this is the trace moment. Once I have this moment, I'll calculate this k by k Hankel matrices. So for all k equal to 1, 2, 3, and so on. So you have, this is the Hankel matrix. Okay. And this is called shifted Hankel matrix. This is a shifted Hankel matrix. And this now, if you see this method that I have described, the integral base method by Bain and Sakurai. So they have block Hankel matrices. But here I have just Hankel matrix of size k by k. So there it was k by k block Hankel matrices. So this Hankel matrix has beautiful properties. So this is the first result. So the rank of this HK is always less than equal to L. That's the number of distinct eigenvalues inside the curve gamma. So this is my curve gamma. Okay. And we'll have this eigenvalues sitting inside, discrete eigenvalues. So their number, the distinct number of eigenvalue, okay, is so the rank of this k can be infinite, doesn't matter 1, 2, 3, 4, and so on. So in other words, with k equal to 1, 2, 3, and so on, the rank of this will increase, and then it will stop at L. So L is the number of distinct eigenvalues. Okay, so this is something you don't have for block Hankel matrices. So this is so this L. So when you try to compute eigenvalues, of course the number L will not be known. Even the eigenvalues are not known. We have to calculate. So how many eigenvalues are there inside the curve gamma? I can compute just by computing rank of this. But then we cannot follow this trial and error method. Okay, as in the previous case, in order to determine minimality index, you have to calculate k there. Okay. So here what you can do is that, well, you take this S naught. What is this S naught? That is the total algebraic multiplicity. Then you know for sure that before we go to this S naught, the rank must have been L somewhere, okay, for some index. So what we'll do, we'll just calculate S naught and then consider this corresponding Hankel matrix, calculate its rank, and that rank is precisely L. So before we compute eigenvalues, we'll first determine how many eigenvalues are there inside this curve gamma just by considering this Hankel matrix corresponding to this index S naught, okay, which we calculate from here, from this integration. Okay, and that will give us the number of distinct eigenvalues inside this curve gamma. Now, once we have this number L, okay, I can determine the formal orthogonal polynomial file as follows. So this is a monic polynomial. So the coefficient ages, okay, this coefficient ages are actually solution of this linear system. Now HL is L by L Hankel matrix of rank L. So this is invertible, okay? And so we can solve this linear system, okay? So these are the moments. We solve this, that will give us this coefficient, and that will give us this formal orthogonal polynomial. Moreover, we can prove that the roots of this polynomial are precisely the eigenvalues which are sitting in the inside the curve gamma, the distinct eigenvalues. Okay, so this polynomial of degree L, it has L distinct eigenvalues. So these are n distinct roots. So these are the roots are all simple. So these are lambda j's. Okay, the eigenvalue. So in principle, I can calculate the eigenvalues. Okay, by finding roots of this, but that's not a good approach because we know that the roots of polynomials are extremely sensitive to perturbation of these coefficients. Okay, and this system, when you solve, there will be some error. So the small error can create problem. Okay. So this is the formal orthogonal polynomial, nevertheless can be used to compute the eigenvalues. So the next result is this. Once you know this L, I'll consider this L by L Hankel pencil, okay? And we can prove that the eigenvalues of this are precisely this L, distinct eigenvalues inside the curve gamma, right? So actually, we solve, instead of this roots of this polynomial, we'll solve this Hankel eigenvalue. This is matrix eigenvalue problem, okay? Of size L by L. What's unique about this particular result is that it doesn't really matter what are the multiplicities of these eigenvalues. Okay, all other known methods are affected by the multiplicities, right? But here it is independent. So we have started with, say, infinite dimensional eigenvalue problems. But if we have a curve gamma that contains only L discrete spectral values, we always solve L by L, generalized eigenvalue problem, irrespective of the multiplicity. And this is something good because we know that the multiple eigenvalues are problematic from the point of view of computation. So this is something independent. So it doesn't matter. This is the Baynes method that I have described. Those are the block Hankel pencils. And those pencils are dependent on, it's very big size. One cannot, for infinite dimensional problem, those pencils will be, this Hankel pencils with entries are operated. So that doesn't help. In this particular case, this our method, everything reduces to this L by L generalized eigenvalue problems. And this L depends on this number of distinct eigenvalues. All right. What about the algebraic multiplicities? So if M1, M2, ML are algebraic multiplicities of these eigenvalues, right? So I can calculate that by solving this linear system. So now we know that these are, once we have found these eigenvalues, we know this is a Vandermonde matrix, which is non-singular. And I can solve this linear system and get the multiplicity. Okay. I'm not aware of any method, not even QR algorithm that I have described, that will give you multiplicity of computed eigenvalues. So here, at least in theory, we can calculate multiplicity of the eigenvalues, okay, sitting inside the curve gamma. So this is the theorem that I use to develop an algorithm, okay. So the algorithm is pretty simple. Wherever we have this, the trace moment, I approximate this integral by some numerical quadrature. So this is the quadrature. So Wj's are the weights, and these are the nodes. Okay, these are the nodes. So if we choose weights and nodes and approximate this integral by this quadrature, okay, and calculate this, okay, this approximate trace moments for p equal to 0, 1, 2, and so on. For example, when gamma is a circle centered at A of radius r, the trapezoid rule the trapezoid rule works very well, and in fact, it converges exponentially fast. So this is very well studied method. So the trapezoid rule for this special choice of the curve gamma, okay, reduces to this. So one can calculate like this. So these are the nodes, and these are the weights. So with this, in my theorem that I have just presented, I'll replace the trace moment by this approximate trace moment. So replace this integral by this quadrature formula, and then form those Hankel pencil, solve the eigenvalue problem. Okay, so this is my algorithm. So given these nodes, Zj and Wj and the weights Wj, this algorithm returns the eigenvalue lambda j and Vj of this particular pencil. Okay, so the first step is to compute S naught. Okay, so I'll calculate this sum. Okay, and then of course in theory it should be an integer, but we need to take this integer version of this because in computation there may be some small error. And so, so this once we have this S naught, okay, I'll calculate this moment SP of order up to 2 S naught minus 2. So this many moments I require to construct this Hankel matrix HS naught. Okay. Once I have computed this matrix, I'll calculate its rank, and that is L. Okay, I'll calculate this rank, and that's L. So once I have this L, I'll consider this Hankel pencil, and then find the eigenvalues. Call this MATLAB and get the eigenvalues of this. So this will give us the eigenvalues, whatever this L distinct eigenvalues and their corresponding eigenvectors. This eigenvector Vj's are unique up to scalar multiple because these lambda j's are simple eigenvalues. So once we have this eigenvalues and eigenvectors, now I'll show you how to recover eigenvectors of the original. So, so here I'll come back to this matrix moments. So once we know this L, consider this moments AP. Okay. So here I have considered these are not operators. These are finite dimensional problem. That's why I have switched from the notation W lambda to T lambda. So this is matrix valued map. So this algorithm here, I'm assuming that we have matrix valued map, holomorphic function. So calculate this and define this fat matrix. Okay, these are the block columns. This is the fat matrix. Once I have this, we can prove this. Suppose this lambda j, okay, if this lambda j is a semi-simple eigenvalue of T lambda, so without this assumption, the recovery becomes very difficult. And in fact, others also make this assumption. So suppose that this is semi-simple, okay, eigenvalue of T lambda. So the algebraic multiplicity of lambda j is equal to geometric multiplicity. In that case, I can show that this matrix is V, multiply that with this Kronecker product of Vj with Ia. So this amounts to taking linear combination of A naught AL with this, the scalar coming from the components of the vectors. So this matrix, its range space is precisely equal to the null space of this. And similarly, for this one, the null space of T transpose. So if I compute singular value decomposition of this, that will give us an orthonormal basis of this null space. And singular value decomposition of this can be used to compute an orthonormal basis of this. That will give us right and left eigenvector. So this is how we can compute the eigenvectors of the original problem, okay, from this Hankel pencil. So this is all about my theory, okay. So let me consider one example and then see how it works, okay. So this is one, okay, 3 by 3 holomorphic matrix valued function. One can show that this looks very nasty, but it is equivalent to this matrix. So eigenvalues, eigenvalues are basically zeros of the sine, cosine, and here. So we know the exact eigenvalues in this case. So let's try to test the computer eigenvalues with this exact eigenvalue. So this is First, I have considered a circle here of radius 2, okay, centered at 0. And I have computed the eigenvalues using quadrature rule, the trapezoid method. The first one, okay, this blue star, these are exact eigenvalues, okay, that is plotted there. And computed eigenvalues with 100 nodes are denoted by this round circle, 200 nodes with these stars, and 1,000 nodes with this cross. Now you can see that I have plotted here the eigenvalues. Our method computes because there are inside 4 eigenvalues. So we solve 4 by 4 Hankel eigenvalue problem. And then you can see that this exact eigenvalue and computed eigenvalue, they are all very close to us. Visually, you cannot really distinguish them. Okay, so even the small number of nodes can give quite accurate solution. Now, if I increase the radius of the circle, then we have more eigenvalues inside. So there are now 6 eigenvalues. Okay, there are 6 eigenvalues inside. And again, I have considered 100 nodes.
Hello.
Okay, and 1,000 nodes. And then again, it shows the computed eigenvalues, exact eigenvalues. Okay.
Hello.
So this is
हाँ,
basically
वो मैंने तुम्हें ना एक ईमेल भेजी है जो जानी साहब ने कॉरेस्पॉन्डिंग ऑप्शंस को लिखी थी उसमें उनके ईमेल एड्रेसेस हैं तुम उनको इनवाइट कर लो
are usually very ill conditioned, and then what you do to deal with if you have a large number of eigenvalues inside this curve gamma, so the strategy would be to split the domain into multiple domains, smaller subdomains, and then solve parallelly the smaller size Hankel eigenvalue problems and calculate eigenvalues of this. So this is all about our method. There is some papers that I have cited in the slide. The first one, here we talked about the discrete eigenvalues and so on. This is the Bynes method that I presented. And this is Gobar paper where they presented operator analog of this argument principle. Thank you.
Hello. Probably you are hearing me. Hello. Yeah. Thank you, Professor, for your nice presentation. Any questions on this topic? I hope there are no more questions. I think we thank Professor Rafiqul Alam for the good presentation. Thank you, sir.
Thanks a lot, Professor. Thank you, Professor Rafiqul Alam, for the wonderful session. I think Ma'am Ajit Iqbal Singh was trying to say something. Ma'am, do you have any doubt?
No, she didn't realize. Muted.
Okay, then. So the next session is the last session of IWMS 2021. So it will be the first international mini symposium on mathematical philately. Speakers of this session are Professor George P.H. Stein, Professor Simo Puntanen from Tampere University, and Professor Gary Carlock Chu from Dawson College, Westbound, Canada. Professor George P.S. Stan has a long and honorable career in mathematics. He has served on editorial boards of many scientific journals. He is a member of International Editorial Board Research Group on Mathematical Inequalities and Applications. He was joint editor of European Aviation News, Overseas Civil Register News, and the list goes on. His research interests are matrices and statistics, with particular emphasis on canonical correlations, canonical efficiency factors in experimental design, Cauchy-square inequality, etc. Another speaker of today's session is Professor Gary Carlock Chu from Dawson College, Canada. As an ambassador to deliver mathematical concepts in an easy fashion with the primary goal to help students understand basic principles. He explores well-known and interesting daily life probability questions in his statistics classes. He applies his technical knowledge to develop a course to help students appreciate the relationship between math and art in a recreational way. His research interests are magic squares, Latin squares, philatelic Latin squares, magic card puzzles, etc. And also, we are happy to have Professor Simo Puntanen again in this session. I welcome all of you, and I request Professor George Stan to organize this session. Professor Stan. Professor Prasad, I think Stan has not joined. Sir, please unmute your mic. Professor Prasad, please unmute your mic.
Yeah, sorry. Am I audible now? Yeah, I hope so. Yeah, you can invite Simo to come forward and speak. Then later you can start with your recorded talk. Simo, please.
Oh, me?
Yeah.
Oh.
Stan, George is yet to come, I think.
George is, I understood it so from Carlock's tapes that George could not get connected. And so Carlock has recorded all the talks. So he will be the main actor in what we will soon see. So you remember through 2012, George was performing online far away from Canada. Right. Those were the days when people still traveled, but he could not make it then. But he was then giving an online talk, much before this modern lifestyle. Right. But now he was, as far as I understand, he was unable to have a connection, and I think Carlock too is explaining George's case in the beginning of his presentation. So you may just put.
Yeah, I'm looking for Carlock too.
He also, I read from his email that he said that he may not be available for connection this time of the day. That was an email to you, and it was CC'd to me also. Okay.
Yeah.
And if you don't see him listed there, so he may be greeting his students.
Then shall we proceed with their MS?
Yes. You can go ahead with the tape recording.
Yeah. Raksha, please proceed.
Welcome to this International Mini Symposium session. We would like to present the highlights of our research called Mathematical Philately Souvenir with extended abstracts for the International Mini Symposium on Mathematical Philately in the 20th International Workshop on Matrices and Statistics by Carl Chu, Simo Puntinent, and George Stein. So this presentation is composed of 3 Beamer files, represent illustrated extended abstracts with keywords and phrases for the following 3 Beamer files. The first one, a further introduction to philatelic lattice grids with 4-sided stamps. The second one, more breaking news for when math meets art, illustrated philatelically and with emphasis on tangrams and Japanese classical poetry. The third one, an introduction to the randomized tour on a rectangular chessboard, illustrated philatelically and with emphasis on Markov chains and Edgar Allan Poe. So what is When Math Meets Arts? So this is a course that I'm teaching now at my college. First of all, I would like to deliver the following greetings on behalf of Professor George Stein. I would like to start with a warm welcome to everybody at this mini symposium on Mathematical Philately, Session 16 at the 20th International Workshop on Matrices and Statistics. This mini symposium is organized by Gary Carlock Chu, Simo Puntinent, and George Stein, and is to be held at the Center for Advanced Research in Applied Mathematics and Statistics, Manipal, Academy of Higher Education, Manipal, India, Wednesday, December 15th, 2021. Many thanks to Gary Carlock Chu for trying to arrange a Zoom meeting on Friday, December the 10th, 2021 in Montreal for George to give you this welcome. Even though he tried to connect, he was unsuccessful. So now we begin the presentation with breaking news about a new extensive resource of mathematical philately in the MacTutor History of Mathematics Archive. So there are recent changes to the MacTutor History of Mathematics Archive that includes a new extensive resource of mathematical philately. Indeed, MacTutor has taken over Jeff Miller's website, Images of Mathematicians on Postage Stamps, now entitled Jeff Miller's Stamps and Other Content and Other Math Stamps. MacTutor now also hosts personally designed postage stamps of mathematicians. Personally designed postage stamps were not officially issued by the countries of postal services, but could be used to send letters. Later, we are going to show you stamps that are personally designed. In addition, MacTutor now also hosts Stamps for Mathematica, a page of stamps from the mythical country of Mathematica. So now this is the homepage display of MacTutor History of Mathematics Archive. So now you can see that, okay, the MacTutor homepage is built from an 8x7 detail. So we are going to enlarge the 8x7 detail on the next page. So now this is the 8x7 detail, okay, of MacTutor History of Mathematics Archive homepage. Now you can see that there are 56 mathematicians here. So we have not identified all 56 of them here. So maybe you can help us to do so. So you may go to the web page in order to identify all the mathematicians here. So below, we are going to present some sheetlets, okay, that are related to mathematicians. So this sheetlet is called World Science, Greek Mathematics by Ukraine 2017. So now you can see a list of mathematicians here. So in the first row, you can see Euclid, Pythagoras, Fibonacci, Bayes, Newton, so on and so forth. Row number 2, Gauss, Fourier, Poincaré, Laplace. So now you can see a list of great mathematicians here. So now on the next page, you will get a similar sheetlet. So it's also World Science, Greek Mathematics. So it's also by Ukraine, 2019 and 2020s. So now, as you may notice, some mathematicians are repeated here. So now you can see Euclid is repeated here. Fibonacci is also repeated here. So now you can see some of them. They are repeated also on this sheetlet. So following a comment by PS Bhaskara Rao Kopati on December 17th, 2020, represents a philatelic introduction to Fibonacci. So now you can see several stems here of Fibonacci. So in the first row, the 4th stem, you can see the Fibonacci sequence. You can also see the golden rectangles and the golden spiral. On the 5th stem, you can see the snail shell, which is related to the golden spiral. And then also you can see the golden spiral on the bottom right-hand corner. Also on the 2nd row, you can also see that the Fibonacci sequence, and then also the golden rectangles with the golden spiral. So now what I'm doing is teaching the students at my college about these topics too, in the course called When Math Meets Art. So what is a personally designed stem? So in the personally designed stem, display number 7, left panel. So you can see A.A. Markov. The year 1886 should be 1856. So in the stem from Mathematica, display number 7, center panel, the featured book is by A.A. Markov, translated from the Russian by Heinrich Lippmann. In the personally designed stem, Markov and Markov, display number 7, right panel, is also featured Andrei Markov, a Russian-Canadian former professional ice hockey defenseman who played from 2000 to 2017 with the Montreal Canadiens of the National Hockey League. So now we finish the introduction part of the presentation. Thank you. So now I'm going to share the first Beamer file, a further introduction to philatelic lattice grids with 4-sided stems. So we built on a short introduction to philatelic lattice grids, PLGs with 4-sided stems by Karl Chu, Simo Puntinen, and George Stein, published in the farewell issue of Philomath, a journal of mathematical philately, volume 41, number 4. We define a philatelic lattice grid, PLG, as a grid with H 4-sided stems and N vertices. This is similar to a magic square, but we use corners instead of cells. So our PLG is defined by a grid of Saturnian stems, as in displays 10 and 12 below. Our PLG problem is adapted from the hexagonal turtles problem, HTP, posed and solved by Choi Shok Jung, 1646 to 1715. In choice HTB, each of the integers from 1 to n is assigned one integer each to the n vertices of the grid. So in our PLG with H four-sided stems, the 4 vertex entries in each stem box add to the same magic sum m. Often, the central magic sum m bar equal to 2 times n plus 1. So in display number 10, left panel, is our Korean scientist phyllalatic strip of H is equal to 3 four-sided stems, and n is equal to 8 vertices in the Science in Korea series 2019, and a PLG paired solution with central magic sum m bar is equal to n plus 1 times 2, which is equal to 18, and paired entries 1, 8, 2, 7, 3, 6, 4, 5, each pair adding to n plus 1, which is equal to half of m bar, which is equal to 9. So on the right-hand side of display 10, you can see that 1 plus 2 plus 8 plus 7 is equal to 18. 2 plus 3 plus 7 plus 6 is equal to 18. 3 plus 4 plus 6 plus 5 is equal to 18. So our study of PLGs was motivated by the HTB first posed and solved by Korean mathematician Choi Shuk-jung. In Choi's solution 11 to his HTP, each of the integers from 1 to 30 is assigned one each to the 30 vertices and to the 6 vertex entries in each of the 9 hexagons, so that the 6 vertex entries all have the same magic sum m. Here, m is equal to 93, which is equal to 3 times n plus 1, which is equal to p times n plus 1 all over 2, with p is equal to 6 here, since hexagons are 6-sided. It seems that Choi's HTP is still unsolved in general. Indeed, we believe it received no attention until 1986 with the publication, properties, and solution finding algorithms of turtle-shaped diagram by Kim Dong-jin and Ong Yung-hwan. So a larger example of a PLG is defined by the recent 10 stems booklet, display 12 left panel, featuring cartoons by 5 Canadian editorial cartoonists, issued by Canada in 2021, with each of the 5 stems appearing twice. So now on the left-hand side, you can see the actual booklet, and on the right-hand side, then you can see the solved solution. So our PLG solution with 10 stems and 19 vertices has central magic sum m bar is equal to 2 times m plus 1, which is equal to 40. So now you can see that 1 plus 8 plus 17 plus 14 is equal to 40, and so on and so forth for the remaining 9 boxes. We are not going into details how we solve the PLG, but we've developed a systematic way to find the solutions. So another example, 95th birthday of Her Majesty Queen Elizabeth II. So our PLG example with 11 stems and 20 vertices is given in the sheetlet, display 13 here, in celebration of the 95th birthday of Her Majesty Queen Elizabeth II, devoted to your service, issued jointly by the following countries. So now you can see that the PLG solution 14 has central magic sum m bar, which is equal to 2 times n plus 1 is equal to 42. So now you can see that you have 2 plus 19 plus 21 plus 1, that will be equal to 42, and so on and so forth. So in the addition to the joint sheetlet display 14 above, in celebration of the 95th birthday of Her Majesty Queen Elizabeth II, devoted to your service, we have features philatelic items from several other countries. So now, the following countries, you can find it in our actual Beamer file. So below are the keywords and phrases from the first Beamer file. If you would like to have the original copy of the report, so please contact Professor George Steyer. Thank you. Before we go to the next Beamer file, I would like to share some art projects by my students. So my student Cyril, she used different tessellations as the background. So you can see that you have uniform tessellations, you have non-edge to edge tessellation, etc. On the top, she tried to use the Sierpinski triangle, and then also try to have some string arts, and then the magic square, in order to highlight the topics that I have taught in this course when math meets art. So now my student Malika created this piece of art. I will give you some time to think about or to guess what is this piece of art. So now what I'm trying to do is I will just try to flash it, and then you can see the numbers behind. So now you can see the numbers behind, and then you can see once again the number behind. And then actually the number behind this piece of art actually is a magic square. So this is an 35 by 35 magic square constructed using the Lalubert method. So she tried to construct this one and use 6 hours in order to color them. So you can see some of the color is in red, some of the color is in light blue, and some of them is using his mini portrait. So now she used red in order to cover all the even numbers, and she used light blue in order to color all the odd numbers, and then she used the mini portrait of herself in order to cover all the multiples of 5. So now I will just try to go back, okay, to the original piece of art to let you enjoy. So this new course, When Math Meets Art, was developed by Carl Chu, Claudia, and Professor George Steyer. And the students were from visual arts, child studies, communications, business administration, graphic design. So the course was designed into 3 parts: the math and art, architecture and STEM part, and the math and dance part, and then math and music part. So now as you can see that for this piece of art actually consists of 2 Sierpinski triangles. One is in the usual orientation, and the other one is in the upside down orientation. So Sabrina, she tried to construct those 2 colorful Sierpinski triangles in order to contrast using the background of black and white curvy lines. Next one is by my student Mandy. She tried to start with a magic square and then gradually increased the size in order to create the Fibonacci's golden rectangles. Then now she used the idea of tessellation in order to replicate it, in order to generate a periodic tiling. The last one, but not least, is the golden wave by Jennifer. So she tried to use the golden spiral in order to construct this golden wave. So hope you enjoy all the art projects by my students. Now we will go back to the next Beamer file. Now we are going to discuss the second Beamer file, more breaking news for when math meets art, illustrated philately and with emphasis on tangrams and Japanese classical poetry. So now you can see two items here, philatelic tangrams with the same 7-polygon configuration. So on the left-hand side, you can see that is the tangram from Finland, year 2000. So now you can see the Sierpinski triangle in the middle. The right-hand side, you can see the tangram from South Africa, 2010. So 5 stems for Southern Africa, small letter. Here you can see the tangram on the left is from Hong Kong, China, 2009. The 23rd Asian International Stamp Exhibition. So now inside the tangram, you can see various shapes built, okay, from the tangram. So what is a tangram? So a tangram actually is a geometric puzzle consisting of a square cut into 7 pieces that can be arranged to make various other shapes. So now you can see that, okay, on the left, the tangram can make into various other shapes. So now on the right will be the stem sheetlet, okay, from Netherlands, 1997. So it's the World Stamp Exhibition Pacific, 1997. So now you can see 12 stamps featuring the signs of the Chinese calendar. So you can find all 12 animals that can be seen from the Chinese calendar. So now we put all the tangrams together. So now you can see that all of them have the same 7 pieces. So Dudeney's 2 monks 10-gram paradox, 1997. So what is a 10-gram paradox? Actually, it's a dissection fallacy. So 2 figures composed with almost the same set of 7 pieces, with one set seeming to be a proper subset of the other. So one famous 10-gram paradox displayed in 16 is that of the 2 monks attributed to Henry Ernest Dudeney, which consists of 2 similar shapes, one with and the other without a foot. So the area of the foot is compensated in the footless body by a subtly larger body here. So overlaying the bodies shows that the footless body is larger by the foot's area. The change in area is often unnoticed as √2. So now this is the set of 12 10-gram friendly advertising stamps. So now in the first row, you can see the 10-gram designs, women skating, maybe a squirrel, chicken, candle. The second row, goose, the hatter, women with headdress, teapot. The third row, you can see rooster, cat, messenger, and running person. So as observed by Fox, Epstein, and Uehara, 2014, and by Katsumata and Uehara, 2015, in their excellent recent survey, articles, the 10-gram, and Sei, Sonagond, Chi, Noita are 2 popular dissection puzzles. each consisting of 7 pieces. So now on the left, then you can see the 10 gram, and in the other 2 panels, then you can see the Sei, Sonagond, Chi, Noita. So now you notice that all of them are in the square configuration, but cut into different pieces. So now for details about these 3 different puzzles, so you can consult the following reference: the convex configuration of dissection puzzles with 7 pieces. Here is the philatelic introductions to Sai, Sonagond, featured in 21 here. In each of the 5 rows are a label and 2 stems. So for row number 1, Murasaki Shikibu is the novelist, poet, and lady-in-waiting, best known as the author of The Tale of Genji, widely considered to be one of the world's first novels. And we go to row number 5, Izumi Shikibu, so considered by many to have been the greatest woman poet with 242 poems. Here are the keywords and the phrases in the second Beamer file. So hope you enjoyed the second Beamer file. Now we are going to present the third Beamer file, an introduction to the randomized tour on a rectangular chessboard, illustrated philatelically, and with emphasis on Markov chains and Edgar Allan Poe. So in a personal communication from Awani Kumar to George Sion, December 11th, 2020, Awani commented that a joint article on nice tour is a nice idea. To the best of my knowledge, there has been no published work on random walk of knights, much akin to the well-known problem of random walk. All the literature on random tour is anything but random tour. As the name suggests, random walk of knight is random jump over boards of various sizes, and its means distance from the starting cell after a particular number of jumps. Average number of jumps needed to reach a particular distance, etc. Later, it can also be extended to 3D or even higher dimensions. So in this report, we now begin with references for Markov chains underlying a nice random walk. So what is a Markov chain? A Markov chain is a stochastic model for a sequence of possible events in which the probability of each event depends only on the state attained in the previous event as defined by its transition probability matrix. The earliest reference that we have found for Markov chains underlying a nice random walk is dated April 22nd, 1996. So it is referred to a nice random walk as a classic homework problem. So we will try to see this problem on the next page. So here is a classic homework problem for an undergraduate Markov chains course. So start a knight at a corner square of an otherwise empty chessboard. Move the knight at random by choosing uniformly from the legal knight moves at each step. What is the mean number of moves until the knight returns to the starting square? So it is a good question, because if you don't know Markov chain theory, it looks too messy to do by hand. Whereas using Markov chain theory, it becomes very simple. So now the knight is performing random walk on a graph. So the 64 squares on the vertices and the possible 9 moves are the edges. So it is not hard to check that the graph is connected and the mean return time is 168. So now let us just try to examine the smallest rectangular chessboard, a 3x4 chessboard. So this is an example of the Markov chain with 12x12 transition probability matrix P and 3x4 coding matrix Q. So you can see matrix P and matrix Q on display 23. So now the 12x12 transition probability matrix P is central symmetric since Pij is equal to P n minus I plus 1 and n minus j plus 1. So our knight starts at a cell I and can move to cell J with probability Pij. Then, assuming the probabilities of leaving a vertex along a particular edge of the underlying graph is independent of the edge chosen, so it follows that if our knight starts as, let's say, cell 1, then it can move to either cell 7 or 10, each with probability P17 and P110 is equal to a half. So now we can extend it to an 8x8 chessboard. So the Markov chain underlying the knight's random walk on an 8x8 chessboard is reversible with 64x64 central symmetric transition probability matrix P. And then you can see that on display 24. So you can see that is an 8x8 block matrix with central symmetric submatrices P1, P2, P3, and then P4, P5, P6 that you can see on the screen. So in Markov chains, or the game of structure and chance, from complex networks to language evolution to musical compositions, we found random tours of the knight on a chessboard starting from a corner square. And then you can see in figure number 1 and display 25 here, and their solution to the famous knight tour problem. So now the expected number of steps before the knight passes through the same corner square equals the number of edges in such a graph. So it's equal to 168. So now we notice that Markov chains provides us with a very powerful tool for studying the structure of graphs and databases in detail. In addition to random tours of a knight on a chessboard, starting from a corner square, Blanchard et al. In Markov chains or the game of structure and chance observed that in the story, The Mystery of Marie Roget, 1842-1843, Edgar Allan Poe based the details of a real crime and post-detective character, the Chevalier C. Auguste Dupin, used his analytical abilities and the proper newspaper reports to get into the mind of the murderer. The meager light of information, practically confined to times of visits, and the approximate duration between the successive visits of characters was enough for the detective to unravel the mystery of the assassination of a young girl named Marie Roget. It was not surprising that the affair was regarded as little less than miraculous, acquiring for the Chevalier's skill of ratiocination the credit of intuition. So there are several stamps of Edgar Allan Poe from Bulgaria, Hungary, Monaco, USA 1949, USA 2009. So in 1942, Universal Pictures produced the film The Mystery of Marie Roget, based on the Edgar Allan Poe story. Although some 40 countries issue stamps commemorating the 50th anniversary of Interpol, 1923 to 1973, the International Police Organization, most issues were of a single stamp with the Interpol symbol or a picture of the headquarters building. Only Nicaragua issued a large set with fictional detectives, the 12 most famous fictional detectives. Henri-Émile Benoit Matisse, 1869 to 1954, a French artist, was known for both his use of color and his fluid and original draftsmanship. Awani Kumar, in a personal communication to George Stein, gave us this interesting and challenging to compose nice tour. So from the diagram below, we can see that the first 8 perfect squares in red ink, so they are 1, 4, 9, 16, 25, 36, 49, 64. So now they are in clockwise direction from cell number 1. So they are also all in a nice move apart. All odd perfect squares and all even perfect squares are equidistant from the center of the 7 by 11 board. And we have a question to ask you. What game is being played on this 7 by 11 chessboard in Matisse La Famille du Peintre, 1911? Awani Kumar give us this closed semi-magic nice tour for the 6 by 10 chessboard. As you can see that on a clown's case on the right. So there is no magic tour on the 6 by 10 board. The smallest rectangular board on which a magic tour is possible is 4 by 18 or 6 by 12. That is a 72 cell board. All column and row totals are semi-primes. All column totals are 1830 divided by 10, which is equal to 183. And all row totals are a prime multiple of 5, with 1830 is equal to 60 times 61, or divided by 2 is equal to 6 times 305. So here are the list of keywords and phrases that you can find in the third Beamer file. So in our Beamer files, we feature philatelic items from the following countries. Thank you very much for your attention. Merci.
Hello? Hello? Am I audible? Hello?
Hello. Am I audible? Hello. Hello. Hello.
He's having connectivity problem.
Hello.
Hello. Hello, Professor George. How are you?
Hello, Prasad.
Yeah.
How are you? Good
Can you
morning.
see me?
I can see. Yes, you even have a mask on, and I don't.
Yeah, let me remove. I was there just outside to see Susmita Datta. So I was with the mask. So.
Okay, so this is it. The meeting continuing, or are you going to dinner now, or
Now
what?
it is the time for valedictory after listening to you for some time.
Say that again.
Yeah, it will be time for valedictory.
Time for
valedictory.
Oh, valedictory. Yes, yes, yes. Okay, I know what you mean. Yes, so you go ahead with the valedictory.
Anyway, in fact, you are most welcome to put up a few words from your end later. Yeah, we'll call you. Within few minutes, we'll start that valedictory.
Okay.
We can see only your forehead. Can you lift so that we'll have a glance? Professor George.
Are you continuing?
Yeah, what I'm trying to say that we are seeing only your forehead.
Oh, yes, I see. Yes, that's right.
Yeah, you'll have to change the angle of. Yes, I could see your face. Thank you. Yeah, you look as angry as you are.
Yeah, I moved the screen because I was putting on my clothes from my pajamas earlier, and now I see what I didn't do that. Okay, so now you should be able to see me and my shirt.
No.
I have to tilt the screen, but I still see
That's gone
you,
up too much.
and yours is really very good. Very good image.
Simo?
There is Simo Kopanen.
Who else? In the darkness. Yes, in the darkness of Nokia, you can see it's almost fully dark here by this time.
Hiding, I think.
If you were in India or in Finland, but I see that you're in Finland.
Right. Very nice to see you, George. I was not sure whether you will show up in person.
Well, I had great difficulty at the beginning, and then they changed the link. And then I tried the new link, but in between I had to go check the email to get the new link. But once I got the new link, it worked.
It's great.
But the bottom line is that this is a real miracle after all these years that I'm sitting here in the corner of my villa and I'm talking to you and Prasad
That's right.
It really is a miracle.
And now if I tilt this a bit more, you can see that I have not shaved, but I have at least put on my clothes.
Yes, I was a little bit nervous when you first came to the picture. I was praying.
Well, before you put the thing onto the YouTube, you should do some editing.
No, it was not at all dangerous, George. In these modern times, it was absolutely perfectly okay.
Are you sure?
Absolutely.
I have to go and get myself a cup of tea because, as you know, it is 8:20 in the morning. I got up at 6:45 to get everything going. And here's my tea that I'm now drinking.
Cheers.
Anyway,
cheers for your tea.
And cheers for your coffee. Very nice coffee mug. By the way, Simo, we use your coffee mugs from Marimekko that you gave us in sets, but only on weekends, special.
Good.
So shall we head for valedictory?
On my behalf, we can have a go.
I'll ask Raksha to request a participant to put up their words, if any.
Fine.
Then later you can give your closing remark. Then George also can come up and say a few words. Then I'll offer my thanks to all.
Shall I now close my camera and...
Yeah, you can put on your camera. Raksha will make announcement. Raksha, please.
Yes, sir. Am I audible?
Yeah, you are audible.
So let me first welcome Professor Stan, Professor Simu Puntanen, and Professor Gary for the wonderful session. So we have come to the end of 28th IWMS 2021. Now the platform is open for suggestions, opinions, or remarks. Participants who wish to give feedback, please raise your hands and allow us to unmute.
I'm back.
Nobody is volunteering. In fact, Professor Susmita was there just outside. She would have come. Anyway, Simo, it is your turn.
Okay, thank you very much, Prasad. Yes, the time has come, so we are about to complete the IWMS part of this 5 days adventure, and the ICLAA group will continue two more days. And now I should say something very deep, and I have to figure.
Do you mind to put on your camera?
Oh,
so that we can have group photo.
Oh, I have several screenshots which will do nicely. One thing what I would like to say as an observation is that the topics of this latest IWMS, they are rather different from those that they were 31 years ago, George, as you remember. I don't know how much you have had opportunity to listen to the talks, but you know the program to some extent, and we can. The fact is that the times change, and the main topics of this matrix workshop series, they have to change as well. And our group, our old gang, we have to compete with many attractions. The old old guys, we have different attractions as the youngsters. They have many more attractions, and we have to try to be somehow popular. We have to compete. We have to get them into our society. And so, therefore, it's clear that topics change, but yet there is room for old school stuff. Like if you try to invert a 2 by 2 singular matrix, it is still not doable. And I mean that one cannot avoid the old school stuff. What else? One thing that we have learned over the last 2 years is that what is the difference between online and in-person meetings? Can you imagine that students, they only experience online meetings? It is very strange world. It's like knowing that there are some movie stars. This is not to be taken literally. We know that they exist. The old guys, we do exist. But the students, they may not believe. They see us only on the screen. And as we know, some guys can be very good online persons, but rotten live persons. And if we all remember our old young days, we extremely well remember how important it was to talk with people in person. Your heroes were living. Now they may be just virtual guys who are very well performers on the screen. I am now going so deep that I am unable to get up. But let's try. The final thing what I have to say is that I wish to express my deepest gratitude to the organizer, Professor Prasad, and his team. They have taken the task, which is not at all trivial. And but if we compare, if we did not have even these online meetings, what would be the life after that? If there would not be even these. So these are better than nothing. And Prasad again has a very nice meeting on his belt, which is getting bigger and bigger. I was able to attend in Manipal meetings in 2012, 14 and 17, and a year ago there was an online meeting, and they have been very pleasant experiences. So thanks go to organizing team and then to the invited speakers to take the trouble to prepare lectures. I know personally from my experience that it is much harder work to prepare an online presentation. You have to almost practice it word by word. When compared with the old-fashioned style that you go into the front of the lecture room and start talking. And contributed speakers and other participants. It's the organizers and the participants that always make a conference. Thank you, everybody.
Well, I want to just say again, as Simo has said, many, many thanks to Professor Prasad for his excellent organization. And I am amazed that he's able to organize not just one of these workshops, but 3 of them all in a row. And I do not understand how you have such talent. Many, many thanks, Prasad.
Thanks for your good words. So, shall I offer my thanks for everyone who worked for this particular conference?
Please,
meeting?
please.
Well, I just wanted to make a small comment.
Yeah, please.
The topics that Simo mentioned from centuries ago. Very, very recently, like yesterday, I got an email from Oscar Baxolari, who is a regular supporter of our workshops. And he had a very interesting question about postage stamps and a conference that took place in 1927. And so there are some things that do go back in time, and postage stamps certainly go back in time. So I hope that this is just, we had one now mini symposium on postage stamps. Maybe we will have another one in, I guess, Sweden in 2023.
Yes, I would. I want to say that I forgot to mention that Martin Singul from Linköping, Sweden, has expressed his willingness with Dietrich von Rosen to organize IWMS in 2023 in Linköping, Sweden.
Hope that we'll have normal conference by that time.
Yes.
And he is young.
Oh, boys.
Older.
What can we do?
You cannot turn the clock back. I guess one disadvantage of the online business is that I cannot now taste your upcoming dinner and what your menu is.
You are quite right.
I love Indian food, and unfortunately, near where we live, there are no Indian restaurants, but there are some good French restaurants. But with the COVID pandemic, we have not, until very recently, even allowed access to that. And there was a scare yesterday, I think, on the news that Omicron has now even arrived in India.
Yeah, it caused attention to us, but somehow we are getting rid of that tension. Life is somewhat normal, but we are still cautious.
I think you're making vaccines for COVID
Yes.
in India, aren't you?
Yes, I had my vaccine, both the shots long back. Now we are looking for a booster dose.
Yeah, we are looking forward to the booster as well. It's due in a couple of days. And by the way, Simo,
yes,
today is Soile's birthday, isn't it?
You are not joking, George.
So if Soile is watching this, or you can convey that we, Evelyn and I, both wish Soile a happy birthday.
This is an online greeting, quite remarkable. Thank you, George. Unbelievable.
Okay, then let me offer my thanks. Thanking words. Dear friends, we are coming to an end of 28th IWMS. Being the convener of a scientific advisory committee, it is my duty to thank everyone who contributed to the success of this conference workshop. This workshop should have been held in December 2020, but for the reason you all know, we have rescheduled it to December 2021, hoping that life situation would be very normal. Unfortunately, the situation remained uncertain, though we found some improvements. So we have continued with the decision of organizing this meeting in a hybrid form. Though the meeting in this format is not comparable with the normal format, we have got the opportunity to see one another on the screen and share our thoughts and developments of the subjects. I must thank Professor Simo Puntanen and all IOC members for offering an opportunity to organize this meeting and timely guidance. I thank Scientific Advisory Committee consisting of Ravindra B. Bapat, Steve Kirkland, and Simo for appropriate time-to-time advice. Altogether, we had 2 mini symposium, 12 invited talks, 13 contributory talks. This consists of 20 invited speakers, 20 invited speakers, 13 contributory speakers, total 33 speakers. I thank all the speakers for joining us and delivering their work. Particularly, I thank Professor Susmita Datta, who made physical appearance in Manipal in spite of present pandemic situation. I thank National Medical Council of India for providing a grant to support Datta's local hospitality. Other speakers in the IWMS are Steve Haslett from New Zealand, Arup Bose, SK Niyogi, SK Singh, Anish Sarkar, and Somadev Lahiri from India, Simo from Finland, Beatrice and Martin from Sweden, Katarzyna and Augustine from Poland, George Stan and Gary Kalakchu from Canada, Arni Srinivas Rao from USA. I thank Mahe administration for supporting us. I thank Director of MIT, Manipal Institute of Technology, and the administration for providing meeting place and all the required facility. Also, I thank Department of Data Science, PSPH Mahe, Department of Mathematics, MIT Mahe, Department of Mathematics, SMIT Mahe, for their association with the KRMs. Particularly the respective HODs, Dr. Asha Kamath, Dr. Sudhakara, and Dr. Anjanara Chaudhary. I thank the faculty of these departments and other speakers for chairing different sessions. I thank all the participants making this meeting successful. I thank Professor Ramesh, Srimati Maya, Vasudeva Guddattu, Vinay Madhusudan, Biswajit Dev for being a part of a local organizing committee. I thank the research scholars Savita, Raksha, and Uma Shankara for working hard continuously from the beginning of start preparing for the meeting. I thank David Michael for his support in handling the web page. I thank Anuruddha, Pooja BS, and other research scholars from MIT for their supports. I thank Department Data Science Office staffs, Sudhamani, Vasant, and sorry, I have forgotten her name. I hope that she will excuse me. For this moment, I didn't get her name. For their assistance. I thank Transportation Department, Fortune in Valley View for their support. So I might have missed some names. I hope that they will excuse me for not taking their names. Thanks one and everyone. Yeah, these are my few words of thanking Simo.
Okay, thank you very much, Prasad. That was very nice and kind of you.
So this meeting should come to an end, though we don't want.
Yes.
Raksha, like to conclude?
Yes, sir. Thanks a lot, professors. So this is an end of IWMS 2021. Thank you all the delegates and participants for joining, sorry. So second day of ICLA will start sharp at 9 o'clock tomorrow morning. Thank you.
Yeah, Steve Kirkland will be delivering his talk early in the morning, 9 o'clock. It may be evening for, late evening for George and people in the Canada. Okay.
Thank you.
Okay. Okay. Bye, Simo.
Okay.
Bye-bye.
Nice to see you
Are you
on the
still there?
screen.
All I see is SP.
I don't know. Why is he hiding?
Yeah,
I think he's ready to switch his camera off.
I'm still here, but
Okay. We'll
Okay.
discuss for our dinner. Maybe you are getting ready for your breakfast or lunch.
Let's see if we can click on that. No, that doesn't work. And I never did work out how to get rid of that bar.
Okay. Bye, Simo.
bye.
Okay, bye, Simo. You've gone.
Bye,
All right.
George.
Okay. Talk to you again soon.
Sure.
All righty. Bye, Prasad. Many thanks again.